Hello, everyone. Welcome to the Quantum Engineering Workshop 2022. As some of you may be aware that we had another workshop last year, 2021 in May, and the recording is available. If you would like to see the last year workshop, the recording is available for that. This year is a one-day workshop. I just give a very general introduction about our distinguished speakers. And then we'll start the first talk at 8:40. Okay, so we have over 400 participants registered for this event, and we welcome you to this event, and I hope that you can benefit from these amazing talks who we have from the distinguished speakers. Okay, so we'll start at 8:40. The first talk is by Dr. Marco Quadrelli from Jet Propulsion Laboratory, Caltech. The title of the talk is Exploring the Intersection between Robotic Space Exploration and Quantum Technology. At 9:30, Professor Prem Kumar from Electrical and Computer Engineering and Physics Department of Northwestern University will talk about engineering challenges for the emerging quantum networks. At 10 o'clock, Professor Stephen Girvin from Physics and Applied Physics at Yale University will talk about progress and prospects for the second quantum revolution. At 11 o'clock, we have Professor Edoardo Charbon from Advanced Quantum Architecture Lab, EPFL, on cryo-CMOS qubit control from a wild idea to work in silicon. 11:30, Dr. Cathy Ann Brickman Soderberg from Air Force Research Lab, talking about quantum networking at AFRL. At 12 o'clock, we have a 30-minute break. And 12:30, Professor Tryphon Georgiou from University of California, Irvine will talk about density transport and the Lane-Bald equation. Okay. At 1 o'clock, Professor Clarice Aiello from University of California, Los Angeles. The talk is from nanotech to living sensors. 1:30, Professor Britton Plourde from Syracuse University, protecting superconducting qubits from environmental poison. At 2 o'clock, we have a 30-minute break. 2:30, Dr. Alexey Gorshkov from University of Maryland talk about quantum sensor networks. At 3 o'clock, Dr. Joshua Bienfang from National Institute of Standards and Technology talk about a single photon detection systems for advanced photon counting. At 3:30, Dr. Neil Zimmerman from NIST. His talk will be on challenges of distributing entanglement over a quantum network. At 4 o'clock, Dr. Thomas Gerrit from NIST will talk about optical quantum metrology from component characterization to quantum network metrology. At 4:30, Dr. Aditya Sharma from NIST will talk about precision enhanced displacement measurement using correlated photon pairs. My name again is Farbod Khoshnut, and please let me know if you have any question after this event. You can contact me by this email. And I would like to make an announcement that we have a special issue of quantum engineering for autonomous vehicles. This is the first time or first publication that trying to bring really quantum engineering to mechanical system domain. So as everyone knows, we have a lot of amazing work going on related to quantum computers, quantum computing, advanced sensors, quantum sensors, detection, networking, and communication. But really, as a mechanical engineer, I would like, or we would like to really collaborate and contribute to how we can bring all these amazing technologies to mechanical systems domain, especially, for example, autonomous vehicles. So, for example, in terms of autonomous vehicles, we know that security is very important. So how we can really take advantage of these technologies that is in quantum domain that is fast growing, and how can we bring these technologies to mechanical system domain. Okay. So that's one of the first publications or special issue in autonomous vehicles that trying to bring quantum technologies. And we would like to invite you to contribute, please, or think about if you could contribute original research in this area. And you're very welcome to do that. I'll also post the link of this page in the chat, just in case. But I will also make an announcement after the event by email, so you have access to the link for submitting your paper. Okay, we will have 3 minutes until the first talk. I will go back to show you what is the first talk with Dr. Marco Quadrelli. Okay, so we will try. I will stop my I will stop this slide presentation. Stop the share. Stop share. And Dr. Quadrelli, would you like to share your slide to make sure everything is working before we start?
Okay, trying to do that right now. Is it there? You see it?
Yes, thank you. It's not in the, what is it called?
Not now?
Oh yeah, now it's in the,
okay.
No. So we wait 2 more minutes, Dr. Quadrelli, if it is
yes.
okay, and we start in 2 minutes.
Can you hear me okay?
Yes, I can hear you, thank you.
Perfect.
Just try to answer the questions in the chat, if there's any question. Thank you everyone for the notes in the chat, but I may not be able to answer all of them immediately, so please feel free to email. I post my email address again in the chat. Yes. Okay. Right, so it's 8:40. It's my great pleasure to welcome Dr. Marco Quadrelli from Jet Propulsion Laboratory. And Dr. Quadrelli's talk is on exploring the intersection between robotic space exploration and quantum technology. Okay, thank you very much, Dr. Quadrelli. Please go ahead for your presentation.
Okay, thank you very much, Robert. It's I'm have great pleasure to participate in this workshop, like I did last year as well at the first edition, and I'm very excited about presenting my presentation, but also listening to the others, because there's a sufficiently varied and different types of talks that are all, of course, relevant to this topic and of great interest to me as well. So I'm going to, let's see. Okay, so this, yes. So the vision of this work that I will present is trying to integrate, the objective is to integrate emerging quantum technologies with macroscopic robotic systems in order to enable novel space exploration. So there's three major things here. One is quantum technologies, the other one is robotic systems, the other one is space exploration. So I work at the Jet Propulsion Lab in the robotic systems section, and where I'm going to talk about that in a moment. Jet Propulsion Laboratory works on space exploration. That is the main mission, main charter of our activity. Quantum technologies there's also a lot of people working on this, but what I'm going to present to you is the results of still ongoing assessment of the state of the art from our perspective, my perspective, and its impact, potential impact, and in terms of opening opportunities into space exploration through robotics technologies. And so I'm going to give you an overview of robotics, which is my neck of the woods, robotics for planetary exploration, and what are the trends that have been emerging in this domain. I will start talking about the quantum, so I hope that I don't put you to sleep in the first 15 minutes or so. Start talking about the impact on quantum technologies in the second half, and then provide an outlook. So as I said, I work at the Jet Propulsion Laboratory, which is a NASA center, and there is also a laboratory of California Institute of Technology. And since it started many decades ago, it has flown a large number of spacecraft in space, in the solar system and beyond, and many different types of instruments. And these are some of the examples of past missions, and they are all in the public JPL website, so you can look at them in detail there. And there are some that we are working on right now, and some of them that are proposed for the future, and covering many different areas of interest for multiple customers, and I'll talk about that later. So what are the characteristics of all these complex space missions? What unifies them? Well, first of all, when you leave the Earth and you try to explore the solar system, then the moment you exceed one astronomical unit or you go beyond that, there are issues related to the fact that you cannot count on the sun to charge your batteries, for example, because your solar panels are not strong enough. You need different sources of energy, for one. Then there's the issue of the communication latency, number two, and many others. For sure, because what we try to do is autonomous robotic planetary missions. So there are Jet Propulsion Laboratory, we very rarely, almost never deal with human flight, human space exploration, only with robotics. We when we get to a planetary body, then the challenges are many, because, well, the science may be under the surface, maybe on the surface, maybe above the surface, or maybe around the planetary body. So there are multiple domains, physical domains that bring in great uncertainty because those domains are not, they are poorly characterized, not well known. And so they demand different mission modalities. For example, do a lot of remote sensing. That means flying around for a long time and collecting data in that mode, or flying by, say, Jupiter, one of the moons of Jupiter, or Saturn. And so there's a reconnaissance surveying mode that is done very fast during the flyby. The orbiter, for example, the Cassini orbiter that did a multiple tour of many moons of Saturn, and all operations above, as I said, or under the surface, including the Mars lander, the Mars helicopter, and all those. So these are all the modalities. And so again, these characteristics are to span multiple missions and regimes and domains, increasing levels of autonomy, as I said, multiple science modalities. These are long duration projects. They're very far, limited communication data, limited or none a priori information about the destination, very frequent missions, usually they tend to be one of a kind. Very tight resources are very tightly coupled and very scarce, power, computer power, and systems must work the first time because you cannot do maintenance. I'm going to mention that the directive, in order to start these missions, we get directive from Congress. And so the national academies are critical to us. National Academy reports, particularly the decadal surveys. There is one that just came out on April 19, the Planetary Science Decadal Survey, which I will discuss very frequently. There is also the Astronomy and Astrophysics Decadal Survey, which I will mention later, the Earth Science Decadal Survey, and then I'll occasionally refer to this thorough report on quantum computing that very recent, 2019, that gives the state of the art and what you can and can do when these people, all the experts in this domain, the quantum computing, they sit together for a long period of time, they come up with a consensus of the community on this topic. So let's go back to the Planetary Science, the decadal survey. And the outcome of this, the redirection that we have just received, is that there will be in the next 10 years, the effort will be directed to two major flagship missions. One is the Uranus orbiter and Uranus probe. The other one is the Enceladus orbiter and lander, Orbilander. And with less priority, a variety of other missions, including Venus, Saturn probe, and comet sampling with less priority. So this is kind of shaping the direction of autonomous planetary exploration for us. And this is a very thick report, it's like 800 pages or more. And so it took me a while to go through it. It's taken 10 years, first of all, to put it together because it's a decadal survey. And there is mention of the word quantum and quantum computing and quantum sensing quite a bit. And I wanted to bring that up because this is a very recent statement that never appeared in a planetary decadal survey. That means that the planetary scientists, they are now interested in having quantum capability on board our spacecraft so that we can make use of that for efficient science collection, and including quantum sensing, positioning, et cetera, et cetera. Similarly, the Astronomy and Astrophysics Decadal Survey does a similar job at laying out the state of the art, came out last year, and it also indicates that quantum limited detectors in various frequency bands like ultraviolet, visible, and infrared, and especially noiseless or at very low noise level detectors are critical to do this type of science. And many of these same properties are also needed at the interface of the detector technology for astronomy, astrophysics, and quantum computing and information science. So finally, there is less mention of it in the Earth Science Earth Science Decadal Survey, which came out in 2017. But there is one of the white papers that contributed to it that does mention that a quantum gravity gradiometer based on atom interferometry was recommended and would be advisable to be flown for air purposes of collecting data for air science. So you see from here that there is already a lot of interest, and the domains start to intersect. In the Planetary Decadal Survey, there are some recommendations for the technology that needs to happen, that needs to be developed for the next decade. And I'll emphasize the ones in red here: instruments, autonomy, communication systems, mission design and optimization, solar arrays, technology for system integration, because they impact all the destinations. That means all the planetary targets that are of interest. So I will focus for most of this presentation on autonomy, because this is also my area of work, but I wanted to give you this landscape. So what about autonomy? Autonomy is the discipline that enables the system to achieve its goals while operating independently of any external control, and pretty much it involves perceiving the world, deciding on what actions to take those actions for whatever systems we have. Simultaneously, there is a diagnostic phase that constantly observes, monitors the performance, and makes sure that things are appropriate. What we have seen, at least I've been at the Jet Propulsion Laboratory 25 years, and even before I arrived, there were a lot of effort in handling autonomy, and over the years, the types of missions have changed in the direction of enabling the management of unstructured environment, very poorly known environment, which enables all these super exciting missions like the helicopter and Europa lander and going to the ocean under the ice and so on, with increasing amount of onboard reasoning, and which requires machine learning, et cetera, et cetera. So increasing levels of autonomy. I'd like to mention that I'm currently updating one of these 3 reports, which you can download from the NASA website down there, particularly the Surface Guidance, Navigation, and Control report that outlines the state of the art on guidance, navigation, and control technologies, capabilities across the board. And the reason I'm giving this presentation today is because an excerpt of that is about quantum, and it involves all these domains that I have talked about. So you feel free to go there and download these reports, and they're being updated, by the way. So soon there will be a new update on those. My ecosystem is the planetary robotics ecosystem at JPL, where we do all these neat things like balloons, rovers, landers, anthropomorphic robotics, underground robotics, et cetera, for multiple customers, from civilian customers, military customers, and of course, NASA. And this is why I am showing you all this variety of scenarios. And one that has taken a lot of my career is small bodies. Small bodies are extremely challenging because there's an enormous variety of them. They are targets of scientific interest, mineralogy, water, ice, et cetera. The environment is extremely challenging because it's highly driven by electrostatic forces, extremely varied gravitational environment, if any, particularly very low levels of gravity, very difficult to move around them, and they are in constant spin, constant motion, which drives the technologies to sample them. Examples are Phobos or various different Itokawa, or the Muses C, Japanese Muses C, lander, and so on. They are all very, very challenging, and so more importantly, integration of many different types of technologies, I'm looking at the time, is needed to enable this type of missions. I would say also that I have spent most of my career on large apertures, like telescopes, primarily either monolithic telescopes, which is what you require. You need very large apertures to be able to provide the resolution you need to do exoplanet detection or imaging, for example. And because you need a very large size, those systems tend to be very heavy. So now either you do segmented telescopes in space or you do interferometers, space interferometers. So now this is where quantum technologies begin to become appealing, because this type of science requires this capability. And also I've worked in antennas, arrays, distributed systems, which are what today enables things like synthetic aperture radar, hyperspectral imaging, higher resolution spectrometry through multiple assets, for example, constellations, formations, and swarms. And I will not spend too much time on this, but I'll just tell you that this is also an area that has been growing immensely. And there's many missions in the either on the board or being under the development that use this paradigm. So what has helped thinking this making these things possible is that we have more and more availability of CubeSats, small assets, highly integrated that allow you to do, for example, heterogeneous measurements, high increased density of spatio-temporal resolution for the events you want to examine, like climate or weather. Timing and synchronization capability that didn't exist before. An example of a success of this was the Asteria CubeSat, which achieved for the first time subarc second line of sight pointing error and highly stable temperature control in the science camera, which is what enables astrophysics missions or exoplanet science. So from now on, we are in the domain of doing things better with impact to the science that I have identified. Because they are small form factor assets, miniaturized instruments are essential, and there's been a lot of miniaturized instruments, from spectrometers to atmospheric sounders to gravitational measurement devices, sensors, seismometers, ion trap spectrometers, which fit the CubeSat form factor or the small sat form factor, and they are currently being tested and developed at JPL. And these are some examples of these ancillary technologies, like the attitude control system that you can buy off the shelf, microprocessors, reflector array antennas that were used, for example, demonstrated in the Marco CubeSat a couple of years ago, Asteria again. And basically, we are in the domain now where very accurate clocks and very accurate metrology sensing can be implemented in these platforms. So we can claim, I'm summarizing the result of some of these assessments that I have done over the years. There is potential to do very good things in astrophysics and heliophysics, which are domains where tightly coupled physical phenomena require multiple points of observation, namely, again, the small spacecraft and multiples, and same thing for Earth science, where now the secondary payload adapter allows you to fly a secondary multiple spacecraft on as a secondary payload and enable this type of remote sensing missions for Earth science. And also planetary science. I'll go a little quicker here, but you get the gist, because there is a lot of instrumentation that now is enabled and under development, like spectrometers and polarimeters that fit this small spacecraft and enable this mission. So now I'm coming to the second half of the talk. So where might quantum technologies come in? Well, I would say that now we are on the third quantum revolution, but I saw that there is another talk after mine talking about this, that we are still in the quantum revolution. So I do not want to go against that. So I would say, rather than third quantum revolution, maybe we are in the second half of the second quantum revolution. Doesn't matter. It's a very exciting time for development of quantum technologies. And I would say that what I've spoken so far is in this, now if you, it is on this corner of the landscape. If you separate things between classical systems, quantum systems on the left, classical regime up there, quantum regime where Planck constant is critical below there, then all the things that I have described to you, they tend to be up here. So classical systems in the classical regime. And however, things that are now classical still, but in the quantum, there are quantum systems in the classical regime are certainly things that enable precise physics measurements like radiometry, optical clocks, Bose-Einstein condensates, gravitational wave detectors. Things like are purely quantum, exploiting purely quantum phenomena are still in development. And I will include among those quantum entanglement experiments, machine learning, quantum internet, things like that. And I would venture to say that classical systems in the quantum regime are something that we are starting to work on. For example, drone-related technology, robotics, in other words, that leverages quantum techniques. So quantum robotics, and I have a slide on this later. And these are pictures that come from Farbod's laboratory at Cal Poly Pomona, and you can ask him in detail if you want. So from the purposes of what I'm presenting here, quantum technology then is an emergent field of physical engineering that leverages those principles that have no, those properties that have no classical analog, like decoherence, entanglement, tunneling, superposition. And we know that, so in the outside boxes here is the conventional engineering disciplines, but all these disciplines in between, quantum optics, key distribution, quantum biology, quantum computing, etc., are all the disciplines that are emerging, but at the intersection. And at least three of them, quantum computing, quantum communication, quantum sensing, they kind of, I talk about them from now on, and because they are kind of the three main areas where a lot of development is happening today. And quantum computer simulation, quantum simulators, quantum networks, there's various talks about quantum network later today, and quantum sensing as well. Now, as part of my job at JPL, I do a lot of technology assessments for what is the state of the art, what can open up opportunities for new proposals, new missions, etc. And so I have to look at the technology readiness level using, for example, the NASA. That's where we use the NASA technology readiness level in various areas. And so here's some example of that, kind of summarizing also recent literature. Quantum computing, for example, we know that is starting to be mid-TRL, and there are challenges in improving the quality of the qubits, the quantum error correction, the upscaling is an issue, and there are commercial partners that have promised or are claiming that they have some capability, but it's still to be demonstrated, and so on. And so same thing for quantum communication, and also for quantum sensing. Quantum sensing seems to be the most mature area, and particularly in the area of quantum electromagnetic inertial sensing. Much less developed is quantum radar, quantum imaging. There's a lot of claims about that, but it's still something that it's in the drawing board, if not earlier. And so we need to take things with a grain of salt when we read papers, because people tend to go overboard. For aerospace engineering, which is my area of work, there's again tapping into the report on quantum computing from the national academies. Of course, there is a lot of optimism, and the people see no fundamental reason why a large, namely capable fault-tolerant quantum computer could not be built, but there are significant challenges. Many of those challenges, at least from aerospace engineering point of view, require tight collaboration with the quantum computing researchers, between the engineers and the quantum computing researchers, to deploy systems that can be used, and for which quantum the quantum advantage can be obtained. And for example, there's been a lot of claims about quantum simulation speedup. And essentially, there are three areas where the claims are made, and because there are different types of algorithms that have potential to make impact in different domains, like linear algebra, solution of ordinary or partial differential equations, and machine learning. However, there are some caveats. For example, the widely more recent and widely known HHL algorithm that is claimed to run in order log n time, exponential time, provides an exponential quantum speedup. However, the solution that when you solve a system of equations, the solution that you get is not exactly the same that you would obtain with a classical computer. You get a solution that is proportional because you get an expectation value. So how do you apply this? In what domain do you apply this type of methodology? If you go to IBM, the Qiskit quantum computer that you can use yourself on a Jupyter notebook, well, when you do a calculation, what you get is a histogram. You don't get a number. And so that histogram, you get histogram of the solution is a histogram that is the result of many realizations of that quantum algorithm through the quantum gates and so on. And how, to which problem do you apply that? This is still unclear. It seems that at least for problems like computational fluid dynamics, problems with turbulence, combustion, things like that, hybrid combinations of quantum and classical methods may have an advantage. And it seems that the stochastic nature of machine learning, data analytics techniques, the intrinsic stochastic nature of these machine learning algorithms, it seems to be well suited to this probabilistic quantum algorithm approaches. So there is no one problem that demonstrates in engineering problem that demonstrates the advantage of one technique with respect to the other, and this is still an area of research. Now, I would like to point out that 10 years ago, there was at the Caltech Institute of Space Science, a workshop that it probably has been superseded by other workshops, but I mention it because it was the first time that people sat in a room and there were people with fundamental physics background, people with precision measurement background, people with space technology background. And through a week or 2 weeks of workshop, they came up with, they tried to answer the questions, okay, what kind of quantum communication sensing measurement can we do in space? And there were some explorations of this topic, where looking at the challenges, what is well understood, what is not well understood in terms of, are we going after, can we go after gravitational science? Can we go after, put a quantum experiment on a rover on Mars, things like that. And there was a report that you can go and download, by the way. And they came up with a representative, with some numbers at least, that are representative of a quantum cryptography, quantum key distribution experiment from ground to space that seem to be meaningful. And since then, there's been some systems have been flown. The Chinese, the Germans have done this type of work. I'll say that at least from my interactions with Farbot, who has done some experiments in his lab with entanglement, that you need, and again, these are the drones where these entanglement and cryptography experiments have been mounted, that you do need a way to generate the entanglement, and the way to do that is this barium borate crystal that operates this parametric down conversion process and generates this pair of entangled photons that, however, yes, they can be received, and that you can start counting photons at the detectors, but there are many challenges related to alignment. There are challenges related to precision of the measurement, maintaining the avoiding the decoherence of that process over time. And so we are, of course, this is a research topic. We've been writing papers on this, and it's very exciting. So what are the and I have 10 minutes left or so, no, a little more. So what are the areas that are based on what I've presented so far, and now emphasizing these autonomous space missions? And some of the features are again here, like multi-asset coordination, robot control, task scheduling, data prioritization, target selection. Where do you go when you land on a planetary body to do science? So autonomously, how do you do that without human intervention? And how do you do deep space navigation to high precision with the deep space atomic clock, ensuring that that timing and synchronization of your network is maintained in space? Well, those are the things that space autonomy requires, and there are multiple. At least what emerges from my analysis here is that there are many areas, basically the subsystem areas, because a spacecraft or a spacecraft system is composed of subsystems. Some of those are control, instrumentation, actuation, state measurement, modeling simulation, etc. And some of them, for example, all of them need development in quantum technologies. For example, we don't yet have a multi-agent, multi-scale, multi-physics, high-performance computing capability that can start modeling and simulate a hybrid quantum classical system relevant to space exploration. We don't have that. So that's something to be developed. Similarly to the other areas, like, for example, state measurement and estimation, well, there are issues related to maintaining that coherence over time during the measurement, like I have alluded to a moment ago. And the actuation, that the spacecraft needs to be actuated quietly, particularly if it is, for example, an observatory. So high precision thrusters, optomechanical techniques are necessary. Hybrid classical quantum state feedback is, I mean, there are books written about it, but can we implement this on a spacecraft? This has not been done yet. Guidance, navigation, and control. I've talked about quantum detectors. One important area that I want to mention is the last one, systems engineering. So to be able to fly a spacecraft or a system of spacecraft, or an array, and explore the solar system a level beyond what we have done so far. Well, we need to be able to test our claim that we can achieve that type of science. So the verification and validation, in short, V&V process, that is intimately related to system integration for this type of missions, is inexistent today in the quantum technology domain. So I would claim that that is a necessity, and a lot of work needs to go into that. So now I'm starting to summarize based on what I've told you in the three areas: quantum computing, quantum sensing, and quantum computing, quantum communication, quantum sensing. What are the possible applications? Well, in my view, there are some that are more mature than others, of course, but the one that seems to be more mature right now is the quantum annealer to solve some problems, and maybe the quantum adiabatic computation as well. But we are looking something within the next 10 years. So there's still many issues related to the number of qubits that are still under evaluation. But it seems that if we get to a large number, to manipulating a large number of qubits stably, reliably, and especially if we are able to map a classical problem into the quantum computer problem one-to-one, or in a way that is meaningful, then we can open up advances in material, biochemistry, optimization, and many other areas. For communication, we know that quantum key distribution is the most mature. But quantum networks is still, and there are several talks later today on this, is still an area of active research. I wouldn't say it's still is fieldable yet for space, but these are the possible applications that seem to be emerged from what I presented to you. For quantum sensing and metrology, this is in a sense, quantum sensing is more advanced than others because we can do fundamental science measurements very precisely through gradiometers, accelerometers, through atom interferometry. We have the atomic clocks. And however, things like quantum antenna or quantum radar, quantum imaging, they are still areas of that require a lot of work. And so we are looking probably at least 10 years in the future. So back to the 4 areas that I indicated before that are relevant to those 4 Academy of Science reports: planetary science, air science, astrophysics, and heliophysics. For planetary and air science, well, it would seem that with small such constellations, formations, some possible measurements we can envision sampling magnetic plasma fields at multiple locations with more than 10 CubeSats. And however, and so the science, because we have the instruments that are miniaturized, have the CubeSat technology that provide the pointing and so on, there is potential for constellations, much less for formations, which tend to be much more precise systems and requiring sophisticated metrology. So anywhere that there's a very tight timings and phase synchronization is still in the future because those types of timing synchronization are where is needed for very precise metrology, intra-array metrology, for example. And we don't have the technology yet to do that. First of all, to acquire the array or the formation, and to maintain over time that metrology without decohering the photons in a catastrophic way. However, there is potential for multiple gravity for planetary gravity measurements. For example, as small bodies, where the gravity varies dramatically from the equator to the pole of some of these small bodies. Gradiometers and measure the gravity gradient, and seismometry, and clocks for a potential deep space positioning system one day in the future. But we don't have those yet. For air science, it seems that using these gradiometers and gravimeters to do mass change is possible, particularly gravitational change over time, like the tides and things like that. And so those are possible, things that are possible at least in the next 10 years. For heliophysics and astrophysics, the science is a lot more challenging because, again, astrophysics and heliophysics require big apertures, very tight resolution, which is lambda, the wavelength, divided by the baseline, the aperture. So if you want to do high energies, you're going to need very large apertures. And so you need improved quantum efficiency detectors with low noise, high resolution detectors, very stable response, more importantly, low power and cost, because these are missions over decades, and high reliability. And for astrophysics, what is been emerging is dark matter, dark energy type missions, which is a big area, a known area of science, and very exciting as well. I will now try to conclude the presentation because the things that we have been talking with Farbod is the quantum, injecting quantum technologies in the engineering curriculum, because all the things that I've talked so far will be possible only if we have the manpower. Manpower means in people capable of doing doing the work, and so they need to be trained. And so the time is ripe to train engineers in quantum technologies and prepare them. and an area, and we have published papers on this topic as well. They're up here. And mechatronics is, by definition, the most synergistic area because it integrates mechanics, electronics, control engineering, computer science, and now starts to integrate quantum technology. So this is perfect. And Farbod has already experimented with his class, and other educators are doing this across around the world, and this is necessary. I mean, it's critical because we can, so far the communities, the quantum community, the engineering community, they've been separated. This is very detrimental to achieving anything. So we need to start at the base. We need to start training people, the new generation of students in this domain early on. Again, I will not repeat what Farbod had mentioned at the introduction. There's this spatial issue that I'm also privileged to be a guest editor. So I invite you to consider these your paper as a submission. And I would say that overall, I'm very excited. I mean, thank you for the opportunity to present my work here, and I look forward to listening to the other presentations and to continue to establish a network of friends and collaborators, so to make this all these emerging applications possible. Thank you very much, and I enjoy giving this presentation.
Thank you very much, Dr. Quadrelli, for this great talk, very informative and interesting. So we have some questions in the Q&A, and please raise your hand anytime you wish, if you like to talk to the speakers or you ask your question. I will first read the questions in the Q&A, which is, can you explain how a quantum magnetometer differs from Hall effect transistor? That's the first question.
That's a very good question, but I don't know if I'm an expert on this topic. I think that there's an area that involves these detectors involved trapped ions, and so they have to do with the detection of the magnetic field, has to do with it, with these atomic systems changing level. And so that's as far as I know. So I invite you to look into the specialized literature, because I am not an expert in this type of detectors.
Okay, so we have, if anybody in the audience or also in the panelists would like also to answer any of the questions, please feel free. So another question by Ron again. What are possible future quantum sensors? I guess that's another question.
Yeah. So I have those towards the end. I think, at least from what I have seen, let me go to the let's see here. So atom interferometry based detectors like gradiometers or accelerometers, very precise accelerometers, and atomic clocks. I think those are the three that are within reach. At least I know that people are working on this type of detectors, and combination of cold atom technology and optomechanics or cavity optomechanics. They are the ones that seem to have most traction at this time, from what I've seen.
Thank you. Another question, if you suggest any book or workshop for learning more.
This workshop is perfect.
Yeah, there's another one last year that they can also 8 hours recording.
Yes.
Another one they can watch.
Well, last year, I think I attended like 15 different workshops related to quantum technologies from different sources. I mean, there's many every year. So you just, you know, if you're a member of a society, you know, I'm sure that your engineer, if you're a member of IEEE or SPIE, you know, there's many of them. So just monitor the announcements. I'm sure that there's many every year, if not every month.
Thank you. So I think we have a question also. Let's see, Dr. Zimmerman has a question. Please go ahead, Dr. Zimmerman.
Thanks, Barbad. Can you hear me?
Yes.
Yes.
Good. So thank you for your talk. You gave what I would characterize as a very broad survey talk. And in particular, one of the things that I noticed was in these slides, sort of 35, 36, 37, most of the applications that you mentioned for quantum, I would characterize as better timekeeping or better sensing. And I got confused because I really didn't understand why you think Quantum 2.0 will be helpful in robotics. So maybe I could ask you to go back to the slide where you showed generation of entangled photons with your flying drones. And could you just explain why this would be helpful for your drones, please?
Yes. Yes. So these are the experiments that Farbod has done in his lab, and I helped a little bit, but he and his students did the work. So the advantage here is that, first of all, so one of the things that we are looking at JPL is multiple spacecraft or multiple drones, and an example is so right now we have the Mars helicopter on Mars, and we are looking for the next generation, for the successor to that, which will likely be multiple helicopters or multiple drones. And so this type of work is very aligned with the desire that we have to establish a secure network, secure, stable communication network, completely autonomous on a planetary surface. And so this is the motivation.
If I can add to that, Dr. Zimmerman, I would like to add that security is one of the obvious reasons. And also, we see so much progress in the area of quantum, for example, quantum computers, communication. And from a mechanical engineer point of view, or in more general mechatronics point of view, we would like to see if these technologies becomes more accessible, what would be the integrated system that includes quantum technologies? So we are still, is like an open question, how do we integrate when this quantum communication become accessible instead of classical? How do we integrate that to our classical systems? So that's more like a question than answer for now, but that's what we are trying to do. Also in the educational point of view, we do the same thing. For example, in mechatronics, we're trying to say, okay, we have a lot of electrical, mechanical, computer that we can integrate and build a device. Now, how about if we bring the quantum technologies and also integrate that to our current mechatronic systems? Yeah.
Thank you. May I follow up?
Sure, of course, please.
So thank you for your answers. I do understand that this is somewhat of an open question, and I appreciate that. But just to follow up on this slide, as I understand it, what you've determined so far is that the usefulness would be basically in preventing eavesdroppers between the human that's controlling this and these autonomous drones, as opposed to changing how the drones actually operate in their autonomous mode. Did I understand that correctly?
Actually, it's both. It's both because we are actually working on applications of some quantum computing techniques to ensure that the system composed of multiple drones can remain stable or form a superstructure or for a super system beyond what classical techniques can achieve. So we can achieve some for example, a tetrahedron or things like that with an aerial drone and ground robots with classical means, but it would be what we are looking at is to do that with quantum techniques, because that will ensure that that network remains secure, and also has to do with the timing and synchronization for metrology purposes. So we are approaching the problem from all angles.
Yeah, so this is Prem, if I may. I think if I understood Neil's question, he's asking, how would, for example, infusing entanglement between, let's say, two drones, how would that enhance capabilities that otherwise couldn't be? So if you have a network of drones, they're communicating with light. Let's say your performance is shot noise limited at every level. What is the limit that the system has, and passing entangled photons between them will let you go beyond that? I think this is really an open question.
It is.
And
Professor Kumar, thank you for asking this question. That's very important, of course. So I always think that we should think about it from a physicist point of view and the engineer point of view. Physicist point of view, for example, is that how we can distribute quantum, for example, quantum key distribution, how we can facilitate that such technologies if there is no, for example, let's say line of sight, or we cannot really, so we can use drones for quantum key distribution. So that is using mechanical systems for advantage of quantum technologies. But then you can think about it also. So that's one of the things that we would like to contribute, one of the contribution. But the other one would be, so now we have all these quantum technologies like quantum computers and so on, and detectors. So how do we bring such technologies when they become more accessible in mechatronics, in mechanical systems? So I think, but if you ask about the clear advantage, for example, would be similar question like what is the advantage of quantum computers over classical computers? There might be still some unanswered questions that we may prove that some of the quantum computing algorithms, definitely there are some advantages over classical, but there are still many questions that we cannot really prove that quantum computing is always better than the classical. It's just more about integration of these technologies when we have access to them. How do we really integrate that, or how we take advantage of these technologies when become accessible? Thank you.
So this is Neil. Perhaps we could continue this discussion in one of the breaks. Over.
Thank you. So there is another question in the chat. I think we can answer that also. But also another question by Ron. Are we worried about Martians by hacking the helicopter? So that's
well, I will say that if you read the news last week that they found a door in the cliff, an open door, maybe the Martians will come out from there, and that's for sure. Then we need a quantum secure network.
Another question, would you be expecting quantum experiment to run differently on different drones depending on their position? So the position, I think the alignment is very important, of course. So like using the fast steering mirrors to detect or to align the source to the detectors always is a challenge that researchers, and including us, are working on. And differently, okay, I think it's more about quantum key distribution or communication, really, which can be similar to the classical communication by laser, similar technologies. Okay, so I hope I answered the questions. Okay. So it's 9:34, so I would like to thank Dr. Quadrelli again for his amazing talk. Thank you so much.
Thank you.
It's my great pleasure to welcome Professor Prem Kumar from Electrical and Computer Engineering and Physics departments at Northwestern University. Professor Kumar's talk is Engineering Challenges for the Emerging Quantum Networks. Thank you so much, Professor Kumar, for your time. Let me see, would you like to share your screen?
Yes. Can you see my screen right now?
I can see your screen.
Okay, I need to go to slideshow mode. Let's see. All right, how does that look?
Okay, that's great. Thank you so much, Professor Kumar.
Okay, so thank you for both. First of all, for giving me this opportunity. Sorry, I missed the workshop last year. I'm still in Delhi, so I hope there will be no interruption going across the globe here. I just wanted to chat a little bit about some of the work we've been doing, and also the motivation. What is the big picture where we are headed? And so I'm going to begin with that. Let's see if I can advance this. Let me get my laser pointer here. All right. So we all have been living in this so-called bit revolution. Communication with classical bits started out right after small-scale computers were on the scene, after the integrated circuit having been invented. And, you know, visionaries like Vint Cerf and Bob Kahn, they were interested in finding out what could be achieved if these small-scale microprocessor type computers could be interconnected together. And of course, back then, email was one of the big drivers, and you know, which is something that we take it for granted. And this sort of historical context captures advances in classical networking as the computers evolved, the networks evolved, and you know, right now, the fact that we're sitting across the globe and having this workshop through the amazing capabilities that are at our disposal ubiquitously everywhere. The important point here is that early adoption of small-scale computing nodes into a network allowed abstractions to be obtained because the device technologies weren't there. But at least if we could figure out what are the requirements for a network, as the devices improved, they could be incorporated. And one could start testing the algorithms, the protocols that are necessary to communicate and network in a reliable way. So taking that as a cue, today we stand at the doorstep of what we call qubit revolution. And that is being driven by the emergence of quantum computers. Again, there were some early QKD type of networks, but as quantum computers are coming on the scene, the situation today is no different than what it was, let's say, in the early days of classical computing. The capabilities of quantum computers are increasing, and clearly there are limits as to how large of a computational volume a quantum computer can have. But if you look at many of the roadmaps of companies and scientists pushing the envelope of quantum computing, networking, because of the sheer size, is considered to be an important factor. So that's why it is important that we start thinking about quantum networking from the get-go. As the quantum hardware will improve, as the technologies for increasing the reach, increasing the rate would improve, the networking aspects, for example, what should a quantum network look like and how should it operate, needs to be addressed for the same reasons that what are the important device abstractions for the quantum technologies that can be utilized to configure an efficient network that can service a large number of users, that can provide basic services, for example, teleportation, for example, entanglement distribution, and eventually lead to distributed quantum computing. We are a long ways away from that. So I want to focus a little bit on the path, and I'm sure there are lots of groups around the world working on these, and each one contributing in the same way as a community of users worldwide led to the development of the classical internet. So before I go into, I want to step back and talk a little bit about how does quantum communication per se differ from classical communication. And networking is just linking many of these nodes together in some kind of an architecture. In classical communications, one imagines a register of classical bits here on the left, and this could be the output register of your handheld device, and typically we call that analysis register of classical bits. You want to duplicate that string of bits on the other side in the possession of Bob. And long ago, courtesy of Claude Shannon, he showed that irrespective of the characteristics of this intervening channel, it is always possible to do error-free communications below a certain channel capacity. That was a very remarkable fundamental result. It took a long time to develop the efficient codes to maintain these kind of error-free communication, but the fact that we are communicating right now is a testament to the early understanding of what it means to communicate reliably over long distances. We can ask the same, and of course, today, communication, classical communication, both electronic and optical, wireline and wireless is everywhere. It's everywhere in a supercomputer where lots and lots of different cores are connected through high-speed communications. Data centers are giant interconnected classical machines, and we have a web of fiber lines connecting all across the globe. And I'm sitting right here, somewhere here, and everyone's down on this side, halfway across the world. There's so much of fiber engulfing the world that we can have this kind of real-time communication. And here I also want to bring in the role of wireless cell phone towers that also give us the edge connectivity that's needed, that you can use your handheld devices and so forth. So that is what classical communications is today. The question we ask is how can that be extended to the quantum domain? And what we envision here on the left is this quantum register, and that could be, for example, the output buffer of a quantum machine, a quantum computing device. So these string of bits are not classical bits, but they are quantum bits, which have the characteristics of superposition, and perhaps some of these quantum bits are entangled with each other, which would be the case in the output buffer of a quantum machine if you wanted to network two quantum computers that are some distance apart. So one can ask the same question, is similar kind of error-free quantum communication possible? And if one thinks about this first, naively, and then you start analyzing it, you find that the kind of classical communication I described on the previous slide actually runs into conflict with the fundamental features of quantum mechanics. There's the so-called no cloning theorem. If a register of qubits here could be passed on to Bob while Alice maintaining possession of that, that would be akin to quantum cloning. And we know that the fundamental linearity of quantum mechanics prohibits duplication of quantum states. Similarly, one could ask, could we measure and resend, kind of a fax machine type of analogy be implemented? And there also one runs into an issue that there is the Heisenberg uncertainty limitation, which says that you could not on a single copy measure the full quantum state. So these difficulties were recognized early on, but in 1993, a very clever protocol was invented by Bennett and co-workers, and that is the protocol of quantum teleportation. It required an additional resource. What they showed and has been, experimentally verified and tested, and that is what's one of the key features that enables quantum communication between two parties separated by a distance. If the two parties ahead of time pre-share a pair of qubits that are entangled with each other. So an entangled pair of qubits, often sometimes called E-bits. So this protocol shows that if Alice makes a joint measurement, a 2-qubit measurement on the qubit she wants to pass on to Bob and her half of the entangled share of qubits, that's say a 2-qubit measurement leads to 2 bits of classical answers upon measurement. If those answers could be communicated classically to Bob, then depending on the result Bob receives, he can manipulate his half of the entangled shared qubit to get into a situation where all information in Alice's possession of that qubit that she wanted to pass to Bob disappears, whereas Bob is able to recreate that qubit which was in Alice's possession. So this protocol of quantum teleportation is now considered the fundamental aspect of quantum communication. And what we are asking is to create a network in which there are entanglement sources that generate and distribute entanglement to various different nodes. The nodes have to make these belt state measurements whose results are then passed on to the communicating parties. If it is to be in a network environment, then paths have to be set up. Since quantum states are very fragile, one needs to make sure that that the paths that are set up are reliable. So in that sense, what I've listed here are the various requirements of such what often would call connectionless quantum communication, because at the time of actual quantum communication, you only are passing results of classical measurements. So, clearly you need ubiquitous sources of entangled photon pairs. You need technologies for storage and on-demand recall of those entangled bits into long-term quantum memories. And then, of course, you need technologies for these so-called belt state measurements. And that is challenging for optical qubits. And of course, all this needs to be done minimizing the loss between communicating parties. As anyone who's worked in quantum optics knows that photon loss, which invariably exists even in modern fibers that are considered to be very low loss, you do lose after going some distance. Those losses essentially means that your rate of quantum communication suffers, because we don't yet have the equivalent of an optical amplifier that really revolutionized classical communication providing a global reach. Architectures for quantum repeaters are being investigated, but we still yet don't have, even in the laboratory, a fully functional quantum repeater. Now, even if one could do classical quantum communications between two parties, as those technologies I listed on the previous page are becoming more and more available, the question still remains, how would we architect an interconnection of these quantum nodes? And listed here are some obvious questions that many have speculated. Would it have a layered structure like a classical network? How would those layers be determined? And what kind of services such quantum networks would provide? I've articulated that quantum communication can be implemented by entanglement distribution and then teleportation. So it appears at the beginning that a teleportation would be a basic quantum service that the network could provide. And of course, this has to be done in a scheduled manner in some ways. Imagine those two registers at two nodes of the quantum network, the output, a few qubits output of a quantum computing output register that needs to be teleported to the input register of another quantum computer, and then that needs to be done in some kind of a clock synchronized fashion so that one knows that such quantum communication has occurred. So there are lots of questions I've listed. I'm sure that you can read these, and I just want to move forward within the context of this half-hour presentation on some of the work that my group has done over the years. And we've been interested in quantum communication over long distances for quite a number of years. Back about almost 2 decades ago, I was interested in communicating or distributing entanglement in fibers. And so back then, the workhorse for generating entangled pair of qubits was spontaneous parametric down conversion. And I was quite intrigued by the full wave mixing nonlinearity of optical fibers. And it's a long history, but we showed that the spontaneous full wave mixing is an equivalent process that can be used in the fiber itself to create entangled photon pairs, time energy entangled photon pairs, or polarization entangled photon pairs in the same manner as one does, for example, in spontaneous parametric down conversion, this logo that we have for our center. And here in spontaneous full wave mixing, on the other hand, the nonlinearity of the fiber, if the pump wavelength is judiciously chosen, you can phase match this 4-photon scattering process where energy and momenta are conserved, but one ends up creating correlated photon pairs. And then turning that into entanglement essentially is a question of having two indistinguishable pathways, how those two photons are created. So for example, here is a way to generate polarization entanglement by embedding that nonlinear fiber inside a Sagnac loop. And with this, we even commercialized a source, packaged it up in this company that I had founded almost 20 years ago. In the early days, this is work dating back to 2006. In a post-deadline paper at OFC, we carried out this experiment of entanglement distribution over 100 kilometers of fiber, where this spontaneous full wave mixing Sagnac loop source was utilized on the ITU grid, creating signal idler photon pairs. The wavelengths are listed here. while these signal idler photons propagated through these 50-kilometer spools of fiber, classical communication was happening, passing through the same set of fibers. So this was an experiment where simultaneous. Sorry about that. So simultaneously, classical light that could sustain 10 gigabit per second communication was passing through these 50-kilometer spools of fiber at wavelengths indicated here, while at the same time using WDM technologies, we were able to mix in polarization entangled photon pairs and show that even when the photons were 100 kilometers apart, one could get high visibility two photon interference. So this way back in 2006 indicated that it is possible to do quantum communication utilizing the conventional fiber infrastructure. Of course, back then, if you are a classical communication expert, you will notice that the power that we had in this 50 kilometers of fiber was minus 10 dBm, which is fine for doing classical communication over 50 kilometer. But that's typically about 10 dB lower than what a conventional high rate data channel would be that goes over long distances. And the reason is that in fiber, when you have this coexisting classical light, there is the process of Raman scattering that occurs, and that creates uncorrelated photon pairs that gives you background. If the power is high, then the visibility of your two photon interference goes down. That has an important consequence of how one would architect a quantum network. And in recent years, we've been collaborating with our local national labs at Fermi National Lab and Argonne National Lab on this Illinois Express Quantum Network, in which various different types of entanglement distribution scenarios are being investigated. So again, the goal of this this project is not to wait for repeater technologies or transduction technologies to arrive on the scene, but to utilize what we can do today, the type of entangled photon pair sources we have, the type of single photon detector technologies that are present, utilize the conventional means of classical transparent optical networking, as well as low loss optical switches, all those technologies, software defined networking protocols, to see what can be done with the available technologies, and to do things in a way that as repeater technologies or transduction technologies arrive on the scene, that they can be incorporated into these networks, the focus being on developing the protocols for reliable networking. So the topology of this network is a metro scale topology. There is and of course, not all of this is functional yet. Bits and pieces of it are functional because of the availability of the hardware that we have on the nodes. There's a link between Fermilab and Argonne that goes through the switches, and also what we call the west leg. On the east leg, the two campuses of Northwestern University in Evanston and Chicago that are about 22 kilometers apart. We do have fiber connections going down, two pairs of fibers, so we can create a network. And so overall vision geographically looks something like this. So here's my lab at Northwestern Evanston campus, and we have a switch at the Starlight facility that provides classical communication services for high-end scientific users across the globe. And we piggyback on these nodes that already exist. So again, as I mentioned before, the goals of this project are to really arrive at some kind of a network architecture and push the limits of conventional whatever is available today to show that we can take entanglement distribution, teleportation technologies into a real world scenario, real world environment. So here I want to talk a little bit about my thoughts on, as I mentioned, teleportation necessarily requires classical communication. And I want to make the point here that future quantum networks are likely to be amalgamated quantum networks with classical networks. That is because teleportation, protocols like teleportation need classical communication to go on. One can envision, a network with dark fibers, but dark fibers are going to be incredibly expensive. Just imagine if you are a vendor providing access to leasing of dark fibers, you could lease the same fiber to a terabit class communication OEM that would provide services like that, which could generate a lot of revenue. So asking someone to lease dark fiber is going to be really, really expensive. So we need to think about architecting the future quantum network in a way that the same fiber infrastructure could be utilized for classical communication as well as for quantum communication. And so recently, those are the kind of experiments we've been undertaking. I mentioned the role of Raman scattering previously in that OFC 2006 paper. We've addressed that in the context of optical switching, work that I'm not going to talk about here. It turns out that if you designate the fiber's O band, zero dispersion point in conventional optical fibers near the 1300 nanometer window as the quantum channel, and if classical communication is maintained, you're far enough away and also on the anti-Stokes side, so that the contribution of Raman scattering actually is relatively quite small. So we've carried out recently some experiments. This is work my student presented at OFC this year, where polarization entanglement in the O band was generated in the lab, connected to fibers that go all the way down to Chicago campus and back. And then we demonstrated that one can tolerate coexisting C-band light of enough power to do a reliable classical as well as quantum communication. So here's an example of, in this case, it's not a fiber source. It turns out that spontaneous four-way mixing fiber source bandwidth is limited, at least at present, with the kind of fibers that are available. But by utilizing waveguide-based spontaneous parametric down conversion type of devices, one can achieve fairly large bandwidth of a spontaneous parametric down conversion. You can envision a multi-channel quantum communication, and that's the scenario that we're investigating here. So one photon of that polarization entangled photon pair is multiplexed with the classical C-band light and propagates this round trip distance of about 45 kilometers, and light comes back, demultiplexed, and then we look for polarization entanglement of these of the locally retained photon of the pair, let's say the signal photon and the idler that has propagated through that 45 kilometer, look for the deleterious effects of co-propagation. So here's some example results. So there's the blue is the HV basis, and this yellow orange is the DA basis. And back to back, our visibility is about 90%, and that is mostly because we're running this at quite a high rate in order to get better coincidence to accidental ratio. One has to pump the source at low enough power that multi-pairs do not reduce your coincidence to accidental ratio. But if we transmit over that 45 kilometer link without classical light being present, so in this case, the fiber is dark, there is loss in the fiber in the O band. It's about 0.3 dB per kilometer. as opposed to, let's say, 0.2 dB per kilometer in the C-band. There is a slight degradation that we pick up because of the residual noise. The count rates goes down, but nevertheless, there is a small drop in the visibility. Now compare that with C-band classical light that's multiplexed into that photon that travels to Chicago and back. And that generates Raman scattering, and up to about 7 dBm of power, our visibility dropped to about 77%, which is still higher than 71%. That's the cutoff to maintain quantum communications beyond the classical threshold. So this shows that coexistence can be achieved by designating the O band as the quantum channel and appropriately restricting the bandwidth. So the appropriate temporal and spectral filtering to restrict the amount of Raman noise that corrupts your quantum signals that are propagating in the O band, Raman scattering from the light in the C band. And 6 or 7 dBm of power is plenty enough to do the kind of classical communication one might envision for supporting, for example, teleportation protocol or any of the other communication that would be required for the quantum network. Another project that we are pushing again to engineer a quantum network is this introduction of what we call the quantum wrapper networking protocol. And this is a collaboration with Boston University. This is a collaboration with Ben Yu at UC Davis. Pardon my Boston University. That's another collaboration I have. Here, the work piggybacks on some of the label switching work that Ben had done 2 decades ago that I was aware of. And we are collaborating together to bring this so-called quantum wrapper networking protocol. The idea here is that we have this qubits that we need to transmit over long distances in the beginning without having repeaters, let's say over metro scale distances. Then it is useful to have some kind of a what we call a quantum wrapper that's utilized on as the header and the trailer, and embedded in time slots in between are the quantum bits. So it's in some ways by looking at low power classical qubits that surround the quantum bit, one can tell a lot about the health of the network. One can measure the decoherence mechanisms that might be going on. One could establish paths based on reading of those header and trailer qubits, and basically without touching, without even looking at the quantum bits, one could provide reliability onto the transport of that quantum payload. We're still in the beginning stages, but the past experience with labels where the data packets in transparent optical networking were labeled and the label information was in these headers and packets, that's a good guide for us to develop these kind of protocols for reliable networking over some distance. Again, this is a work. So these another thing, for example, every qubit that one transports from across the network over 2 nodes, that might have an entangled pair somewhere. So all that information, what packet is entangled with what qubit is entangled with, all of that information could be embedded in these wrapper classical bits that then can be utilized to, along with the conventional software-defined networking scenarios that one uses in transparent optical networking to come up with protocols for reliable transport of qubits. So here is an example of what the wrapper and the header and trailer might look like. Again, this is a project that we just started last year. Another a point I want to talk about is also collaborating with colleagues at Boston University and UC Berkeley to miniaturize sources of entangled photon pairs. As I mentioned,
sorry, I left a message for you about 2 minutes, if possible.
Yes, I'm almost done. So anyway, the point here is that our goal is to create a source of entangled photon pairs, which is completely CMOS compatible, is foundry created, and has electronics, photonics, everything is integrated. You provide a classical DC light to it, you provide DC power and some control signal, and it spits out entangled photon pairs. And we are in the process of, so we have the first set of circuits that are available. All filtering, both at the input and output, are integrated, and electronics is integrated. And so here's an example of light is coupled into these chips. And then, so this is a heater that heats up, locks the input light onto the resonance of this source ring that generates through spontaneous photomixing signal Aiello photon pairs, and one can lock on. And this would then be a technology that can be cheaply mass produced. So for example, to be placed on the drones or things like what the focus of this workshop is, how can you create small form package sources of entanglement that then could be placed on small scale devices that can move around. So I think that's where I want to stop. I've given you a flavor of what are the challenges in engineering a quantum network, and I've made a case for coexistence of classical and quantum signaling on the same set of fibers. I didn't talk about synchronization. That turns out to be an important point in classical and quantum networking. I've introduced this quantum wrapper protocol and gave you a flavor of some of the monolithic quantum electronic photonic integrated systems that some of my colleagues and I are developing. I think I want to stop here and take questions.
And thank you very much, Professor Kumar. If you would like to ask direct question, please raise your hand, or I have 2 questions in the Q&A. Networking cryptography at MAC, physical layer going to, I don't know if you can see the questions, going to the OSI layer. How would we implement cryptography in quantum communication? That's one question.
So, our goal for us, the goal is not actually quantum cryptography. I mean, we are motivated by actually linking 2 quantum machines that are some distance apart. Clearly, transduction is an important thing. So depending on what is the computing hardware on the 2 ends, there are device technologies that are needed. But if one needs to implement QKD like a protocol, there is tons of literature. People already are doing a quantum key distribution utilizing O-band as the quantum channel and C-band as the channel that does rest of the QKD protocol in terms of sifting and error reconciliation and privacy amplification and whatever else is needed to generate secure keys from the quantum data exchanges. And similar things could be done.
Yeah, thank you. And the next question, how do you make sure the entangled photon pairs are in pure states?
They certainly would not be in pure states because, as they pass through, I mean, if there was if we have let's say polarization entangled photon pairs at two different wavelengths, and if there was no noise, and then if there was only loss, then the rate would go down after those entangled photon pairs propagate through the lossy channel. But for the photons that are received, their states would be, if they were polarization entangled, the fidelity of the received state with the transmitted state would be very, very high. On the other hand, as I mentioned, there are processes that lead to noise, background photons being generated in those same bands of spectrum where your quantum signals are propagating, and Raman scattering is one prime candidate for in fibers where classical light of significant power, meaning milliwatts or tens of milliwatts exists. So then the visibility or the fidelity of entanglement would suffer if such background, that's because of the inherent nonlinearity of the fibers, is not controlled or mitigated or designed properly such that its effect is minimum, which is the reason for choosing the quantum channel to be in the O band on the anti-Stokes side of room temperature fibers that are in the field, producing phonons that predominantly scatter on the Stokes side.
Thank you, Professor Kumar. One last question is, would there be any value in employing quantum entanglement between computers inside the rack in data center?
I think it depends on what the eventual goal is. I mean, I think this is very similar to the question that was asked previously. What is that killer app scenario? And for both, you may know that I've articulated that perhaps there is something in a swarm type system. But I don't know if the answer to that question has been worked out. That imagine you have a network of drones that are behaving like a swarm, and there's a very small amount of local communication that they can do. The question is, would embedding a small amount of quantum communication even in a pairwise fashion between neighboring drones enable better planning and trajectory assessment, or whatever the task that this collective is trying to execute, which may have a link to some base station somewhere and a giant computer somewhere at the back end. If that bottleneck through this local quantum communication can be relieved, then that would be a scenario that's worth pursuing. But I'm not sure if theoretically this question has been adequately answered. The reason I say this is because there are it has similarities to quantum auctions or quantum public goods game scenarios that have been worked on previously, that even bipartite entanglement between neighboring nodes can allow scenarios in which one can come to a better this public goods game where you can come to an efficient outcome by making correlated bets, the prisoner's dilemma kind of a protocol where one could do better by infusing a little bit of quantumness into the system, even in a pairwise fashion. So I think with that insight, it seems to me that it is possible that there might be some application lurking in the network of drone space, that small scale utilization of quantum communication. potentially could be useful.
Thank you, Professor Kumar. Thank you very much for the great talk. Really enjoyed, and it was very informative. I would like to introduce our next talk by Professor Stephen Girvin. I'm sorry that we are behind the schedule, but I think we can catch up during the break later. Professor Girvin is a professor of physics and applied physics at Yale University. And Professor Girvin's talk is Progress and Prospects for the Second Quantum Revolution. Hello, Professor Girvin. Can you hear me?
Hi, thank you.
Thank you.
Is my screen visible?
Yes, I can see that. Thank you.
I'm going to figure out how to move the hide this floating meeting controls. There we go. Okay, great. So I'm going to try to give an introductory talk about quantum machines and quantum computers for beginners. And so let's start with a review of the first quantum revolution, which took place in the first half of the 20th century. And we know that quantum theory describes the behavior of matter at atomic scales, atoms and electrons. And now part of the push is to build larger scale devices that behave quantum mechanically, in which strange things happen, in which particles act like waves and waves act like particles. And there are counterintuitive effects involving uncertainty and randomness, and this entanglement or spooky action at a distance that Einstein objected strongly to because he understood how weird the implications are. So the people that invented the quantum theory a century ago were just doing curiosity-driven fundamental research about light and atoms. They were doing experiments like the one that you see here, which is an experiment even a theorist like me can do. You shine light from a compact fluorescence lamp onto a compact disc. And in addition to the specularly reflected white light, you can see the disk acting like a diffraction grating and displaying for you the discrete spectral lines of the atoms in the light bulb, which and those colors come from quantized energy levels of the atoms, which you can see in this 50-cent experiment. And this was all extremely interesting, but there were no conceivable applications. And but it actually did lead to applications and to the technological revolution of the 20th century, because the theory led to the invention of the transistor, the laser, and atomic clocks. And the people who invented quantum mechanics did not foresee these quantum devices, and even the more practical physicists and engineers who invented these devices did not at all foresee their myriad applications and the scale at which we use them today. Here's Charlie Towns in 1953 with one of the first atomic clocks. And that led eventually to a surprising realization that you could build a global positioning system and hold in your hand a device that knows what time it is to within about a nanosecond and where it is on the surface of the Earth to within a few meters. And certainly was not an application that was envisioned even by the genius of people like Charlie Towns. The people who soldered together the first transistor in 1947, you can see there's blobs of solder. Its thing is ½ an inch across, centimeter across. Pretty ugly looking, but this was the beginning of the electronics revolution. And the people who built this had a definite goal in mind, replacing the vacuum tube in computers and amplifiers. But they could not imagine this device, this computer processor, which contains a huge number of transistors, nor could they imagine the rate at which transistors are produced in the world today. It's every day, every second of every day, the world produces more than 20 trillion transistors. So this scaling up is just beyond belief, and certainly beyond the imagination, I expect, of the people who built the first one. So despite all this amazing success, we've recently come to understand that these quantum devices do not actually harness the full power that's available to quantum machines. You need to know the quantum theory to predict, theoretically, the voltage at which a transistor turns on, or to predict the frequency of light that comes from a laser. But once you have that, then engineers can treat these objects completely classically, that the voltages and currents here are classical, that the light that comes from a laser is no different than the light that comes from your local, or the radio signals that come from your local radio station, except a different frequency. But it's now come to be understood that if you could build a machine that's more completely quantum, where the voltages and currents are quantum observables, and where individual photons are important in the electromagnetic field, you have additional powers. And so the big new idea is that the very strangest aspects of the quantum theory, the uncertainty and randomness and spooky action at a distance, are not strange sort of bugs in the program of the universe, but rather features that we can actually use to build radically new technologies. So this insight is powering a second quantum revolution. And I would say, based on the examples I just showed you, we cannot possibly foresee its consequences, or even exactly what these quantum machines will be found to be good for. And there's sort of three legs to the stool: quantum materials, which I won't talk about; quantum sensing. We have a new ability to measure the tiniest signals better and better, because we have a deeper understanding of quantum measurements and how to reach the limits set by the Heisenberg uncertainty principle, and even defeat those limits in some cases. And so quantum sensing is being used to detect gravitational waves in the LIGO experiment. It's being used to search for dark matter particles in the haystack experiment at Yale, where I am. It's also been used to do nuclear magnetic resonance or MRI structures of single molecules. And the reason that quantum sensing is interesting is that certain quantum states are extremely sensitive to external perturbations. That's good if you're building a sensor. It's very bad if you're trying to build a computer or a simulator or do quantum communication. So we're currently in the era of the NIST era, noisy intermediate scale quantum era. We've invented maybe the quantum abacus, or maybe the quantum vacuum tube. But it's very early days. Rudimentary quantum computers exist. You can log into the IBM or other companies' online resources and do your own experiments on quantum computers, but they don't yet work very well, and none of them work well enough to be economically interesting. So it's still very, very early days. There's a huge amount of hype around this issue and the potential uses and the economic impact, but it's going to be, I believe, decades of basic research, and physics and engineering and a variety of fields will be needed to create really new technologies that have the potential to be quite revolutionary. So, so this second quantum revolution is giving us several things, one of which is quantum computing, which is a completely new way to store and process information. It uses quantum superposition. There's a crude and not accurate sense in which one can say that quantum bits can be both 0 and 1 at the same time, that being uncertain about whether it's 0 or 1 seems bad, but actually it can be an advantage. An entanglement, which is superposition of multiple qubit states in different parts of the computer, permits objects in different parts of the computer to have correlations that are stronger than is possible classically, and allows you to do very strange things like teleport states across the computer, or even gate operations. I can turn a knob in one part of the computer and change the state in a distant part. And this was the thing that Einstein objected to, this kind of spooky action at a distance. But there's a huge irony, which is that every morning, people that want to calibrate their quantum computers carry out these operations that Einstein said were impossible in order for them to verify that the quantum computer is actually quantum and not classical. So I think if Einstein were alive today, he would be pretty impressed by that. So all of this leads to a kind of massive parallelism that lets quantum computers do certain computation tasks that are essentially impossible on any conventional computer, no matter how large and how fast. And this is not because the clock speed of quantum computers is very fast. In fact, today they're rather slower than the extremely fast classical computers we have. But rather, it's because the complexity of certain tasks scales differently with problem size, depending on whether you have quantum hardware or classical hardware. For problem size n, like n is the size of a database or something like that, perhaps there are problems where the classical algorithms take time exponential in n, and on some cases in a quantum computer might only scale polynomially in n. So interestingly, we don't yet have a full understanding of what power quantum machines have. The realization that quantum hardware is different than classical hardware has overturned the very foundations of theoretical computer science that were established nearly a century ago, in which basically all hardware, all Turing machines were essentially equivalent. You can write in Fortran a Python compiler, or in Python you can write a Fortran compiler, and you can use different kinds of hardware, and the clock speed might be different and so forth, but basically the length, the power of the machines are all the same. And but it's not true when you have quantum hardware, and we're beginning to understand which problems are quantum easy and quantum hard on such hardware, but we still don't have a complete classification. So here's a kind of crude diagram of complexity classes. There are some problems like multiplication of large numbers that are so easy that I can do them on my cell phone. But the reverse problem, if I give you a very large number that's the product of 2 primes and ask you to factor it into those 2 primes, that's believed to be exponentially hard. And that difficulty is actually this sort of what's called a one-way problem. It's easy to verify, but hard to find a solution. That such problems are the basis of the RSA encryption algorithm that's used on the internet. But Peter Shor invented an algorithm showing that it's easy for a quantum computer to factor large numbers, which breaks that particular kind of encryption, but not all kinds of classical encryption. And actually, in the end, quantum mechanics actually enhances privacy in the end, because there are quantum communication protocols, as we heard about in the previous talk, in which even an adversary with a quantum computer cannot break. One natural thing that's easy for quantum computers to do is solve the equations of quantum mechanics, which is an important task that has actually economic impact in the discovery of catalysts and finding drug molecules that bind to certain targets and so forth. So it turns out that some aspects of solving the quantum equations are very easy on a quantum computer. If I give you the quantum state and ask you to evolve it forward in time, that's actually easy on a quantum computer, assuming you can load the state into the system and the Hamiltonian into the system. But other problems like finding the ground state energy of a complicated molecule with interacting electrons, there exist hard instances of that problem that are hard even for a quantum computer. So we don't yet fully understand how to classify all given problems into how hard they are on classical and quantum hardware. And that's an open research problem, as is quantum heuristics. People make a lot of money today solving optimization problems that are provably hard on classical computers, but with very clever algorithms that find excellent approximate solutions in a short length of time for scheduling FedEx deliveries and matching airline crews to airplanes to routes. With 100,000 constraints, people can make serious money solving these problems today, and we don't yet know how well quantum computers can really do in these cases, but I think they may be able to do well, even if you can't prove that they will generally do well, just as is true for classical computers today. So I want to just review a little bit about information, and starting with classical information. Information is physical, as we like to say. It's stored in and transmitted by physical systems. For example, the position of a switch in a circuit. If the switch is open, that could be a 0. If the switch is closed, that could be a 1. And the fact that photons of light are transmitted when the switch is in state 1 means that you can communicate that bit of information to multiple parties. The same is true for quantum bits or qubits. It's physical. It's stored in the physical states of a quantum system, like an atom or molecule or ion, or with photons, or I'll talk about superconducting circuits. And any physical system that's quantum mechanical has quantized energy levels, such as the atoms in this fluorescent light bulb that I showed you before. And if you focus on the lowest two, that you can call this state 0 and this state 1, and those can be the states of your quantum bit. And quantum information is digital in the sense that the energy levels are discrete, and if you measure the energy of an atom or an atom-like structure, you'll always get just one classical bit of information. The measurement result is always either 0 or 1. So in that sense, quantum bits are similar to classical bits. But there's another sense in which it's completely different, that it's analog, and that's because of the superposition principle. So in between, there exist superpositions of these two discrete states that are mathematically described like this, or by an arrow on the surface of what's called the Bloch sphere. And states at the North Pole, or what I'll call spin up, that corresponds to bit value 0, and states at the South Pole, or spin down, we'll call that 1. There are states that are superpositions of both possibilities. There are quantum amplitudes for both, and those are described by points not at the north or south pole, but somewhere in between. And these two angles, the co-latitude and the longitude on this sphere, determine the quantum amplitudes to be of the superposition. And these states are continuous. And so unlike classical bits, the qubit states are continuous, but so are errors. An error can creep into a quantum state and cause this arrow to drift continuously to a new location. And that will turn out to be dangerous for error correction, as I'll discuss later. So there's a kind of feature of this analogness that the qubit is, it's not really true that it's simultaneously in 0 and 1. It's better to say that it doesn't have a value 0 or 1 until you measure it. But this, as a shorthand, it's not really right. We say it's both 0 and 1, and therefore can do things in parallel, potentially giving an exponential speed up. And so if we think about a classical register of n bits, it can be in one of 2 to the n states. So here's n equals 3. The states go from 0, 0, 0 all the way up to 1, 1, 1. There are 8 states labeled by binary numbers 0, 1, 2, 3, 4, 5, 6, 7. But a quantum and a classical system can be in one of these states. But a quantum system can be in a giant exponentially large superposition of all of these states. And each state has a complex number multiplying it. To keep things simple, I'm just choosing +1 and -1 for the amplitudes. And remarkably, this exponentially complicated thing can be created in certain versions of it can be created in one time step on a quantum computer. And this, in fact, is often what the first step is in a quantum algorithm, which I'll explain later. So this state space is so huge that even a small quantum computer of 53 qubits has about a petabyte of states it can be in. And its operation is very difficult to simulate by solving the Schrodinger equation on a conventional supercomputer. So you don't need a huge number of qubits to have a machine that's, in some sense, more powerful than a big classical computer because it's hard to simulate its operation. So along with the superposition principle, which sounds like a feature, there's a certain kind of bug, if you will. We're uncertain which state the bit is in. If I take a qubit in a superposition state and I measure with what I'll call a Z measurement, or is the arrow pointing up or down, I get a random result. Sometimes it's down, which is a 1, or up, which is a 0. And so the state is actually changed by the act of measurement, and it's impossible to predict what the measurement result is going to be given the input. And it's also impossible for the experimenter to know that the state was changed by their measurement. All they know is the result of the measurement. And this change is called backaction or state collapse. And it's invisible to the observer. So that seems like it could be a bad thing if you're trying to build a computer. It's a deep principle of quantum mechanics, and I like to summarize it by what my friend Sasha Korotkov says about this randomness. It's not that something has a random value and you open the box and see what the value is. It does not have a value until you measure it and bring its value into existence. So in quantum mechanics, you don't see what you get what you see. So it's a feature that you can produce superposition states of all possible numbers that the input register of the computer can hold. So since this includes all the possible numbers that can be stored, the answer to our calculation is already in there. But when you make a measurement, you're going to have one chance in 2 to the n that the measurement result will be this particular one, if that's the right answer. So you're just going to get random noise, and you're very unlikely to get the correct answer. So how can a quantum algorithm possibly produce useful results instead of random noise? Well, quantum particles have wave-like properties, and so do qubits. And I can't really explain in detail how the qubits are wave-like, but it has to do, if you will, with this phase as you move around the equator of the Bloch sphere. You can think of that as a wave-like effect. So we're going to use quantum wave interference, which can be constructive. If you add 2 waves like this, their amplitudes add, or it can be destructive and their amplitudes can cancel. And the square of the amplitude is the intensity, and that's the probability associated with some particular output. And so by using interference, an algorithm can take an initial state, which is a giant superposition of all the possible inputs, and you run the algorithm, and these coefficients, these amplitudes, are sort of the wave-like complex amplitudes. And you want the program to apply destructive interference to the coefficients in front of the wrong answers and constructive interference in front of the right answers, so that when you measure the output, there's a very high probability, a high intensity of the quantum wave, if you will, to get the correct answer. So you can sort of think of a quantum algorithm as a programmable diffraction grating. I showed you a diffraction grating on the first slide, made from a compact disk. But this has to be programmable to solve the problem we want. So you launch these quantum waves, these wave-like properties of the qubits, and then you eliminate certain paths, and you put in certain holes that light through in such a way that you get constructive interference on the correct answer and destructive interference everywhere else. So that's roughly, a hand-waving way about how quantum algorithms work. But it raises a funny question. I mean, how do you, if you don't know the answer to your problem, how do you design an algorithm to give the right interference pattern to focus on the answer? So that's sort of the grand challenge of quantum algorithm development, and we're not very good at it. We're still beginning to learn how to do it. And I think it'll be young people like you all who really take us forward in the future to learn how to develop intuition for how to do this. So I'll turn now to a discussion of quantum hardware. For qubits, you can use trapped ions, cold atoms in optical lattices, electrons in silicon quantum dots. I'm going to talk about superconducting electronic circuits, which my experimental colleagues here at Yale have pioneered. So the first all-electronic sort of chip-based electronic quantum processor was built in 2009 by my colleagues Rob and Michelle at Yale. It's produced lithographically, just like the integrated circuits in your classical computer, except that semiconductors are replaced by superconductors. So this is a very small quantum processor. It only has 2 qubits here and here, but it was the first all-electronic device that could run simple quantum algorithms. And the way that these 2 qubits communicate is by emitting and absorbing virtual microwave photons that travel down this resonator from a couple of centimeters. And could be manipulated to do instructions and carry out small algorithms on this quantum processor. And today, billions of dollars are being invested in industrial systems that are really amazing, but still rather direct scale-ups of this first really rudimentary device that's only built 13 years ago. So here are a few of our graduates, Daniel Sank at Google, and Chad Rigetti at Rigetti Computing, and Honey Pike at IBM. And there are many of these ideas developed in our group are now appearing in all of these superconducting processors that are being built at large companies and small startups and so forth. So what is the superconducting qubit? Well, we developed this transmon qubit. It's a sort of been very widely adopted. It's very simple. It consists of an insulating piece of sapphire on which you evaporate two films of aluminum, about 1 millimeter long, forming a dipole antenna whose two halves are connected by a Josephson junction, which is shown here in electron micrograph. This is sort of the transistor of quantum computing. And so it's a junction between two pieces of aluminum. It's about 2,000 atoms on a side. It's aluminum, and there's a little layer of aluminum oxide tunnel barrier in between, which is an insulator. And normally electrons can't pass through an insulator, but if they're very a thin barrier, electrons are actually waves. And in a superconductor, they travel in pairs and they can tunnel through this barrier. And the excitations of our atom are charges sloshing back and forth in this antenna, which allows it to communicate with microwave photons. So the energy levels of this atom, unlike this artificial atom, are separated by frequency energies that correspond to microwave frequencies, not visible light, like we saw in the first picture I had on the first slide. And so the transition frequency is about 5 gigahertz. It's similar to cell phone frequencies. And it's not quite a harmonic oscillator. The energy levels are not quite uniformly spaced, and that allows us to focus our attention on just the two lowest levels, because its transition frequency is different than all the others. And they emit and absorb microwave light. Why do we have to cool these to near absolute zero? Well, there are two reasons. One is to get the superconductivity. So there's no electrical resistance in these as the charge sloshes back and forth. You have to go below about 1 Kelvin where aluminum becomes superconducting. And the second reason is a bit trickier, that the energy of a microwave photon at 5 gigahertz corresponds to a temperature of about 1/4 of a degree, 1/4 of a Kelvin, 1/4 of a degree above absolute zero. So there's black body radiation coming from the walls of the refrigerator, and it's very important to cool it down to 1/100th of a degree above absolute zero, so that the atom thinks it's in a very cold environment. And this can be done. You wouldn't need to do this if the transition frequency were in the visible, where that would be thousands of Kelvin of energy. But because these are microwaves, we have to keep it very, very cold. So, a kitchen refrigerator is maybe $750, but a refrigerator that will get to this temperature is $750,000. And, ordinary radio wave electronics are pretty cheap, but the kind of electronics that we need to manipulate these things are extremely expensive, but would be much more expensive actually if we didn't have all the cell phone technology that works at similar frequencies. So that helps. So the huge information content of quantum superpositions that I've talked about, which sounds like a big advantage, it comes with a price, which I've also mentioned already. It's great sensitivity to noise and perturbations and dissipation, that the quantum state can drift around continuously on this Bloch sphere and develop errors. And so, you know, if you have a digital computer, you represent the bit value by a voltage, and any voltage that's near zero, you call zero, and any voltage near one, you call one. And only if the voltage excursion is gigantic, like half a volt out or 50%, do you possibly get a bit error. So there's kind of built-in error correction against noise in a digital computer. That's not possible for analog computers. And I showed you that quantum computers behave in an analog way. And in 50, 60 years ago, there were people that spent their lives patching these wires together to program analog computers. And there were even 2,000 years ago, analog computers for calculating the positions of planets. But it turns out that you can't do error correction. There's a no-go theorem on analog computation that you can't correct errors. So what are we going to do if we have errors in our quantum computer? Well, let me restate the quantum error correction problem in a nutshell. I'm going to give you an unknown quantum state, maybe from the middle of a calculation in my quantum computer. If you were to measure it, I showed you that it's going to change randomly due to state collapse or back action, which is going to ruin things. And your job is that if it develops an error, please fix it. So this this seems completely impossible, but miraculously, actually, it can be done, at least in principle. And we're just beginning to learn how to do it experimentally. So the reason that it can be done, despite the fact that quantum computers are kind of analog, is that they're also digital, that errors are continuous, but if you measure them, they're discrete. Whenever you measure, if you can map the error onto a qubit and then measure the qubit, you're only going to get results 0 or 1. And so the trick is to measure what error has occurred without measuring which unknown state it occurred in, and that because that would collapse the quantum information. You want to collapse the error state, but not the logical information state. And it turns out that's possible to do with clever error correcting codes, which I don't have time to really explain. But I'll just show you the first sort of error correction engine, which made the lifetime of the quantum information longer instead of shorter when you applied the error correction. So here's the prototype quantum processor about to be cooled down. Here are 4 high-speed FPGA cards with special software. And this system sends down signals to look for errors, reads the signals when it comes back, makes a decision on whether an error has occurred and which kind, and then sends a correction signal back down, all with a round-trip latency of a few hundred nanoseconds. And actually, 15% of that latency is the speed of light travel time for the signals to go from the computer at the top of the doer to the quantum processor at the bottom of the doer and back. So this is very, very fast electronics. And this was first achieved about 6 years ago. And it just barely made the lifetime, longer. And right now we can make it about 50% longer, But we really need to make it, 10 or 100 or 1,000 times longer. So there's still lots and lots of important work to really get error correction working in a useful way. So now that you're experts, here's a quiz, but don't worry, I'm going to give you the answers. So is quantum information carried by waves or particles? Of course, the answer is yes. Is quantum information analog or digital? Again, the answer is yes. And so I hope I've convinced you that when it comes to quantum mechanics, you have to think differently, that quantum information is carried by waves and particles. It's both analog and digital. And quantum error correction is possible despite the fact that when you look for errors, you change the state of the system. But I want to emphasize that there is a lot of hype and we have to be careful. The hardware is still incredibly crude. It's something like this for quantum. And we have a long, long way to go. But really is, I think, a huge potential for this second quantum revolution based on new understanding, not a new theory of quantum mechanics. That's the same as it was 100 years ago. But a new understanding that some of the weird features of quantum mechanics actually are features and not bugs. So I will stop there and I'm happy to answer questions. Thank you.
Thank you, Professor Girvin, for this really informative and useful talk. It was really great to learn so much about different aspects. So if there is any question, please, you can raise your hand or ask however you prefer, or you can also type in the Q&A. I missed one of the questions earlier, which I would like to ask now. That's from, I think it was in the chat. A question from Russell Roach, that is, what's the state of art on progress on quantum network repeaters?
Is that for Prem or for me?
I think for anyone who would like to answer, I guess.
Well, as Prem mentioned, people haven't really built successful repeaters yet. It's very, very difficult. It's closely related actually to this quantum error correction problem, because the fibers are extremely pure, but still in a few kilometers, you have a significant chance of losing photons. And that doesn't matter for classical communication. You just crank up the power of the signal you're sending. But for quantum information, losing even a single quantum, a single photon, is very bad. So you have to figure out ways to do error correction and do all your operations nearly perfectly. And that's still a big engineering challenge, both for computing and for communication.
Thank you, Professor Girvin. There are some messages to thank you for your talk in the chat, but also there is a question by Paul. Can you explain quantum volume, please?
Yeah, so quantum volume is a kind of metric of how good your quantum computer is. It was developed by IBM. And it's roughly, crudely speaking, it's like proportional to the number of qubits in your computer times the number of gate operations you can do before you errors overwhelm the computer. It's roughly that. It's a little more complicated, but so it's the bigger the quantum volume, the more complicated calculations or algorithms you can run on your quantum computer. And right now, quantum volumes are sort of a few hundred at best, and then it needs to be much, much, much larger. I see there's another question about how much electricity does the quantum computer use? Well, one really interesting thing about quantum computers is that if they consume any energy, the calculation fails. they're completely frictionless, reversible computations, except for resetting the qubits at the beginning where there's a tiny, tiny energy cost. But this neglects the fact that you have either lots of lasers or, in our case, a refrigerator, all kinds of, and then powerful classical computation that is controlling the quantum computer that uses lots of electricity. So, but the quantum part itself uses essentially zero energy.
Interesting. There is also a thank you, Professor Girvin. Another question in the Q&A: what is the right way and more popular to create qubits, which is more stable? I guess that's the question.
Well, yeah, that's a good question. There are many technologies, as I mentioned: trapped ions, cold atoms, Rydberg atoms, superconducting qubits, silicon quantum dots. They all have advantages and disadvantages. None of them are close to yet to what we need in terms of their performance. And so it's too soon to pick a winner. And you know, some young person may invent a completely new way of doing things that will make all of this obsolete. That would be great. But right now, if I had to say what are the leading technologies, I would say superconducting qubits, trapped ions, and cold atoms are all doing fairly well. The silicon quantum dots are beginning to make progress, but still are not nearly as sophisticated right now as these other technologies.
Professor Girvin, how about the photon-based quantum?
Yeah, I should have mentioned also, there are sort of optical photon-based computing methods. There's a lot of money being poured into that as well. I would say there's some potential technical advantages there, but they're not as far along in terms of demonstrating sophisticated gates, and there are certain costs associated with the fact that it's the nonlinearities that Professor Kumar talked about are, you know, they're there, but they're not nearly as strong as they are in some of these other technologies. And so, but a lot of interesting ideas have been put forward for how to do computation with photons. And of course, then if you want to communicate, you already got the photons and you can just ship them off into a fiber. So if we can get the computing part and the gate part working better, it could be a very interesting additional technology.
Thank you very much. And another question by Ron. Are we prepared for future QC hardware discoveries in terms of software algorithms and developments, like quantum IDEs?
What's an IDE? Sorry, display my ignorance.
Ron, would you like to talk directly? I can, let me see if I can find him. If he raised hand, I can find him and he can talk directly. Okay, please go ahead if you'd like to ask.
Yeah, is my microphone working?
Yes.
Yes.
IDE is an integrated development environment.
Okay.
We're currently using IDEs that are kind of stuck in the text world. Pretty much any advancement you see, it's basically we're still writing programs via text for one thing.
Right.
And I just also wanted to comment on, you made a statement that we were sort of in the vacuum tube era of quantum computing. I just really enjoyed that comment, which is what generated my question. history has shown that hardware always shows up with some amazing capabilities before we're really ready to exploit them. Even given GPUs, NVIDIA just released their latest and greatest thing. It's got an insane amount of capacity, and their biggest problem now is how do you keep it busy?
Yes, yes, and how do you program it? So yeah, so I understand the spirit of your question now. So actually, there are a number of companies. There are quantum software startups, there are big companies that are developing compilers and other toolboxes. Right now, and we're going to need all of that as quantum computers get bigger. I mean, right now, everything is kind of hand programmed. You can think of it as kind of machine language optimization that like people used to do in the old days when classical computers had poor performance and needed to squeeze out every drop of performance you could get by working at the level of machine level instructions. But that's pretty hard work, and you'd like some more abstract layer to help you do the software development and the debugging and so forth. And so people are trying to develop those things. Right now, the performance of the hardware is bad enough that your compilers need to be noise aware. They need to know that, qubit number 7 is not as good as the others. Don't use it unless you have to in your algorithm. It's very difficult to shuttle information over long distances in a quantum way. So the connectivity of the hardware has to be very well understood by the compiler. And so these are very, very interesting questions, how you produce a development environment that makes it easier for people to sort of intuitively use quantum hardware. And it's such early days. People are trying to do that, but I think as people get experience with the online computers that exist and realize what's hard to do and what's easy to do, they'll develop new ways of using them and new ways of writing compilers for them. But it's still very, very early days.
Thank you for your feedback. I really appreciate being able to talk to you directly. Thanks again.
Pleasure.
Thank you. Thank you. So there's one last question. Quantum code based, if quantum code based.
Yeah, so maybe it's CSS. So there are quantum codes in which you use multiple physical qubits to encode one logical qubit, which is in a superposition of logical 0 and logical 1. And if it develops an error, you have a kind of redundancy that will let you correct the error. It turns out that no such codes nobody has made hardware good enough to make that work. We have succeeded just barely in getting quantum error correction to improve the lifetime, not by storing the information in physical qubits, in physical objects, but rather storing the information in superposition states of microwave photons. And it just turns out, for technical reasons, the error correction in this case is much, much easier. The qubits stored in photons stored in superconducting resonators have very long lifetimes and a very simple error model. It's basically a damped harmonic oscillator that occasionally loses a photon. And so we've developed the they're called bosonic quantum error correction codes, which have no analog to these CSS and stabilizer codes that you're familiar with from the qubit world, but they work pretty well.
Thank you so much, Professor Girvin. Okay, that was a really amazing talk, and we learned a lot from this really informative talk. Okay. So,
my pleasure.
Thank you so much, Professor. And our next talk is by Professor Edoardo Charbon from Advanced Quantum Architecture Lab at EPFL. The title of the talk is on cryo CMOS qubit control from a wild idea to working silicon. Welcome, Professor Charbon. Can you hear us? Hello.
Yes, I can hear you. Thank you very much. Can you hear me?
Yes, I'm sorry that we are a little bit behind of the schedule, but then we will catch up during the break. Please go ahead, Professor.
Well, first of all, I'd like to thank Professor Girvin and Professor Kumar for introducing what I'm going to be talking about. So I managed to take out a lot of slides. So that's, thank you very much again. So what I'm going to be talking about is something quite wild in many ways. And it all started with a group of people that are highly talented. I started this project in TU Delft, and I'd like to acknowledge those people that really inspired me and worked with me in TU Delft, and also Intel that funded a large section at the beginning of this work back in Delft. So we talked about quantum computing. We talked about being in the pre-1947 age. And I completely subscribe to this. And
Professor Shah, I'm sorry to interrupt you. Are you sharing your screen or your? I may have. Okay, I think that was my fault. I clicked on something. Would you like to start the first screen? I think I was not showing your screen for some reason.
Okay, can you see my screen?
Yes, thank you very much. Sorry about that.
Okay. So I'd like to subscribe to the idea that we are in pre-1947, absolutely. And I think Professor Girvin and Professor Kumar clearly made a case of quantum computing. So, of course, everything started in the 80s, but there's something that Richard Feynman said, that there's plenty of space at the bottom. And I think that even though we may be at pre-1947, Professor Girvin mentioned there's going to be a young person that is going to come up and invent a new qubit. And I strongly believe that's true. I strongly believe that there's still a long way to go in order to get to something that is going to be a appropriate quantum computer. So this is a slide that I borrowed from my colleague Joe Bardeen that compares classical quantum computing. So you've seen that in classical computing you have 0 and 1, and in quantum computing you have a superposition, and the qubit can be represented, the state of a qubit can be represented on the surface of the Bloch sphere, whereas processing in classical is a simple 1 to 0, 0 to 1, whereas in quantum computing you have something called unitary transform that relates to rotations on the qubits. And as said earlier, while the conventional computer, classical computer, is deterministic all along, the quantum computer is deterministic up to when you read it. And when you read it, then you can indeed, what you get is what you read, as was correctly pointed out by you, Stephen. Thank you. So in a typical multi-bit quantum algorithm, you have a series of operations, such as the initialization of qubits, the creation of superposition. Usually one uses a Hadamard transform to achieve that, the encoding of a function into unitary, the processing, and finally the readout. So all this, during this time, coherence must be maintained. This is really important because it means that the qubits have to somehow be either always be coherent or be corrected. So Professor Girvin mentioned quantum correction. The alternative is to not correct, but to simply perform all the operations fast enough that the qubits will be coherent and will have no quantum error. So that means that essentially you need to extend the coherence time. So this is possible way of the future computing, the future quantum computing stack, starting from the quantum algorithm. And then, of course, you have high-level languages and lower-level languages, leading to the quantum execution and potentially quantum error correction. And finally, this interface classical to quantum, where you are in combination with a quantum chip, quantum processor. So you heard them before. Superconducting qubits probably is one of the technologies that is the most mature, along with ions and NV centers potentially. I like very much quantum dots, even though I agree that they are still in their infancy, because potentially they're compatible with CMOS and compatible with solid state technologies that we know today. Why is compatibility so important? Well, it's going to come up later, but I believe that if qubits could be implemented in solid state technologies that are somewhat compatible with CMOS, then it would be possible to build all the electronics necessary to control them and read them out, also in CMOS. And that's a whole promise of my work in the past few years. So essentially, you need to correct the qubits from dephasing and relaxation. And usually, even though you may be operating at very low temperatures, there's nothing you can do. This is going to happen anyway. So in order to maintain high fidelity, you need to find a way to somehow perform correction. So the idea here is to have a quantum processor that is combined through two directions, control and readout, to a classical controller. And the classical controller actually, for most quantum processors, does generation of frequencies of the order of gigahertz, pulses of the order of 100 nanoseconds. And in principle, all these techniques can be combined together to read spin qubits using either electron spin resonance or electric dipole spin resonance or other techniques like these. And the interesting thing is that the classical controller, essentially, as you can see here in this simulation, where the qubit, in this particular case, is a spin qubit, but could be also a transmon, going from the ground state to excited state, only requires a relatively high frequency in the order of a few gigahertz, but highly controlled in phase and in amplitude. So here you can see a square envelope. And then in order to go to this maximum superposition state, or to stay there, or to go to the excited state, as you'll see here. So all what counts is really to be very precise in terms of phase, amplitude, and frequency. And this can be achieved very easily today with CMOS. And the only thing that was difficult at the beginning when I started working in this field was that physicists did not really have a specification. They simply said, well, we use 16 bits or 15 bits in amplitude and as many bits in control of a phase. And if you gave me one more bit, I would use it. And so that's a problem. One of the first things that I did here was to come up with an environment that would allow me to really have an understanding and modeling of qubits and translate those into specifications for the electronics to control them. So the first one, of course, was the signal to noise ratio, signal to distortion ratio, as well as frequency, phase, and so on. And what is really important is to achieve a certain fidelity. So here we could manage, for example, to match modeling the qubit from the solution of the Schrödinger equations to SPICE, essentially, to achieve a SNR of 44 dB that was required for a fidelity of 99.99, or the famous 4 nines. Now the question is, okay, fine, we have specifications, but where is the best place for electronics? So you can see here, and Professor Girvin shows you one possible implementation. Qubits typically at 20 millikelvin, and then you have some intermediate stages at 4 Kelvin, 77 Kelvin, but most of the action is really at 300 Kelvin. So the first thing I ask myself is that the right thing to do? And the answer is absolutely yes. If you have a few qubits, you don't want to do anything more complex though. If you have a very large number of qubits, and if I want to build a quantum computer with thousands of qubits or millions of qubits, then I'm going to have to think differently. So this is how the machines, most of the machines look like today. So we have the dilution fridge, the qubits are at the bottom, and then here you have the stages that I talk about. But most of the action, like I said, it's a room temperature where you have entire racks of instruments. So what we propose is to bring these instruments at the temperature that is reasonable, so reasonably close to the qubits in such a way that potentially everything or almost every connection here could become superconductive with its advantages, and then run the electronics at 3 Kelvin or 1 Kelvin or 4 Kelvin, and with a simple communication with 300 Kelvin. So if we did that, of course, there are several challenges. The first one is to come up with an architecture. So this is an architecture we we came up with. We proposed that it's if you are familiar with transceivers, you'll see that this is very similar to a transceiver with down converters, up converters, ADCs, DACs, and a large section devoted to digital circuitry. And it turns out that actually this is well understood in terms of the precision of the phase, amplitude, and frequency that you can achieve with such a construction. The main challenges are really the noise that you have to deal with. Typically, the noise budget is in the order of nanovolts per square root of hertz. The power budget is also very low. If you want to have 1,000 qubits, you're going to have to, you cannot you cannot dissipate more than 2 milliwatts per qubit, because this is going to bring you to a large upper watt range, and this is the maximum you can absorb in a dilution fridge at that temperature. And then finally, this is the easiest one, so you'll be able to use a few gigahertz in order to operate. Of course, if you're using electronics, you could build electronics that operates at 100 millikelvin, but then you would be limited by a few milliwatts. If you operate at 4 Kelvin, on the contrary, you're limited in the order of watts, and therefore you can have indeed electronics to control thousands of qubits. So what are the challenges of designing cryogenic electronics? Well, first of all, is to choose the technology. So there are many technologies that are available that can operate at cryogenic temperature. CMOS can operate down to 40 millikelvin, but silicon germanium HBTs can also operate at 4 Kelvin. And non-idealities are well known, and power dissipation is really the limit here. So what are the main things that happen to CMOS at cryogenic temperature? First of all, the threshold goes up in both NMOS and PMOS. And in addition, you also have the so-called subthreshold swing that is actually saturating here, thereby limiting the performance at cryogenic temperatures. In addition, you have mismatch that increases, leakage that drastically reduces, that's a good thing, and substrate that becomes essentially floating. So we have done extensive modeling campaigns in all these technologies here, and we came up with models that actually are operating. This is an example of a 22 nanometer FDSOI technology that has been fully modeled, and a paper that will appear soon that describes it. However, self-heating is really a main concern, because any current that you're passing a transistor through will generate heating, and that heating, considering the limited dissipation through the space may actually create issues. So I'd like to go over a couple of circuits that we designed in order to perform qubit readout and qubit control. So first of all, it is a qubit readout. The problem at hand is, of course, to achieve a target fidelity of 99.9%. And using a quantum point contact signal of the order of 400 picoamps with a noise of 53 picoamps RMS, and the input referred noise at the order of, again, picoamps RMS. Again, I mentioned earlier the frequencies in play, but if you are taking a quantum dot, the typical technique to read it is reflectometry, which essentially consists of sending a pulse of radio frequency, and depending on the QPS reflection, you can measure the phase of the reflection, and you can determine whether the qubit was in a state of 0 or 1. Of course, this can be implemented entirely in integrated fashion. This is a chip that we built called Quadro that was comprising a entirely cryogenic PLL, cryogenic LNA operating at 4 Kelvin, and then the usual down converters, low pass filters, a polyphase filters, and then amplifiers for direct and quadrature. And then everything would go to 300 Kelvin, whereas in the future, it might be sufficient to actually operate everything in digital circuit, all the digital circuit, and not even go up at room temperature, but stay at cryogenic temperatures. So the receiver architecture operated at 5 Kelvin with non-zero IF from 0.1 to 1.5 gigahertz, and image rejection architecture for in-band noise suppression that was absolutely necessary, along with a frequency synthesizer that was on chip. This is a low noise amplifier. Again, there's nothing special here. It's a low pass, it's common source amplifier with degenerated source. In this case, using a coil, just an inductor. And then inductive loading along with a cascode, and then the coupling from the first stage to the second done with a transformer. Again, for those of you that are familiar to RF design, there's absolutely nothing special here, except maybe for the fact that there was extreme care in really reducing as much as possible the noise. This one could achieve a noise equivalent temperature of the order of 7 Kelvin. The mixer also is not special. It's just basically a Gilbert cell with an active mixer, a resistor for current bleeding that was added to increase the voltage headroom that is necessary at low temperature. And then again, extreme care in leading the signal to the mixer and controlling the mixer frequency. This was the polyphase filter. Again, nothing spectacular except for very high care of the control of resistances and capacitances, and then a simple inverter-based resistive feedback amplifier chain that actually comes out to create both the I and Q signals. So with this simple architecture, we achieve a image rejection of 20 dB, which is more than sufficient, and an I and Q gain of 30 dB. The frequency synthesizer is basically a simple PLL that is with a programmable divider to control the frequency accordingly, and then a divide by 2 to have both the direct and quadrature frequency generation. So this is a chip micrograph, and you can see here all the parts, including the PLL, the LNA, and the I and Q outputs, and even an SPI for controlling the state of the receiver. Some measurements, in the interest of time, let me just focus on the LNA. Here you can see a noise figure of the order of 0.55 dB, which is actually excellent, but not sufficient. I think for most superconducting qubits, you need an order of magnitude, maybe 0.05. But it can be achieved with a preamplifier that you can put in front of this. This is a VCO, and you can see the VCO performing very well at room temperature and extremely well at cryogenic temperature. This is the measurement that was obtained from the qubit that was presented and was analyzed using reflectometry. And you can see here the ideal data and the measured data that showed the state of the qubit extracted in this way. And finally, the power consumption that was in the order of 108 milliwatt, which is okay because you can actually multiplex in frequency multiple qubits, thereby reducing potentially the power consumption to single digit milliwatt per qubit at 3.5 Kelvin. But clearly there is a long way to go. So here you can see the measurements of the various qubits implemented also in CMOS technology. These are quantum dots that could potentially be translated into qubits in the near future. And you can see that even though they were implemented in CMOS, they can be operated at 50 millikelvin, and therefore it is possible indeed to implement this kind of architecture using a technology that is fully CMOS compatible. So the second part is that I'd like to talk briefly about it, is the radio frequency circuits used for qubit control. So the problem at hand here was to create a time domain frequency enveloped in such a way that the frequency spurs could be removed. And the reason for that is, as I mentioned earlier, to perform frequency division multiple access and therefore to fit multiple qubits onto the same line. Again, we've done the same exercise here, a bit more complex with frequency inaccuracy requirement of the order of 10 kilohertz, inaccuracy in phase in the order of half a degree, and amplitude inaccuracy in the order of microvolts, and finally duration inaccuracy in the order of 36 nanoseconds. So you heard before a latency of the order of 200 nanoseconds. One of the advantages of using cryogenic temperature techniques is that you reduce that latency because you reduce the path required for the signals to go from the qubits to the electronics and back. So this was the initial architecture. Again, nothing spectacular, just a large digital circuit that controls 2 DACs and then up converters, and finally a power amplifier. The final architecture of the chip that is known as a horse ridge was a bit more complex. And as you can see, the digital circuit does a lot of work in balancing and the 2 generated signals and eventually preparing them for the up conversion that occurs here. So this is a micrograph of the chip that it was implemented in 22 nanometer FinFET technology, and it can control in principle 128 qubits. One of the main challenges here was the fact that this chip should not heat up more than 4 Kelvin or 3.5 Kelvin, and therefore the construction of the package and the absorption of the heat was one of the main design challenges that required a lot of energy from us. So this is how the chip fits into the diffusion fridge and its position. And this is the instruction set. So it was mentioned earlier about the machine code. And essentially, this is the machine code of quantum computer. as it can be implemented in Horse Ridge. And you can see here that maybe in one of the first chips, to my knowledge, there was a clear conscious effort in making sure that there is some sort of standardization of the instruction set in order to be able to run the control effectively. So the experimentation was quite complex. We had to go from 2 gigahertz to 18 gigahertz, and we had to demonstrate our SFDR and SNDR, the order of 44 and 48 dB, respectively. This is the pole shaping that we achieved. And here you can see various pole shapes that we could completely program. Of course, the favored shaping of most of the quantum computer scientists, which is the Gaussian pulse, because it shows the best possible spectrum spurs that you can achieve. And this is a qubit processor, actually the 2-qubit processor that was provided by researchers at Delft. The interesting part was the fact that indeed you could really perform a high level of integration and potentially expand it to much larger qubit arrays. The first experiment that was run was the Rabi experiment that consists of checking various positions on the block sphere and controlling them precisely, and for each one of them measuring the fidelity. And so this was done at room temperature and at cryogenic temperatures. Essentially, the two are indistinguishable. The reason why we did that is because we wanted to convince ourselves that we were comparing apples and apples. And so we used the electromagnetic switches to switch at cryogenic temperatures from one to the other. This was the second experiment, a Ramsey experiment, where you have multiple variations, multiple qubit orientation changes. And these manipulations eventually can be standardized in a randomized benchmarking. In this case, we used the 60 Clifford gates, and you can see that the room temperature and the cryocontroller actually perform very, very well. The two lines would be completely superimposed. We just translated them to make them visible. The fidelity in both cases was actually quite similar. We actually wanted to show also different frequencies, so we performed simultaneously Rabi oscillations on 2 qubits at 2 different frequencies. And finally, we performed Deutsch-Jozsa algorithm, a simple algorithm on 2 qubits in a completely controlled, using the controller all along. So I'd like to conclude in a few minutes that remains to talk about the trends. So I think that we talked about controllers and readouts, but we didn't really talk about how qubits can be densified. And I think this is really important. People are talking about 2D architectures and 3D architectures to control qubits. And I think it's really important for the future that we really start thinking about these architectures in combination with control and readout side by side. And so these are some of the proposals. But I think another important development that could apply to a number of qubits is the increase of temperature of operation. Here is an example of a work by Andrew Jurak on a qubit that was operated at up to 1.45 Kelvin. But there has been other qubits. This is another example from the Kuhlmann group that achieves even a relatively short coherence, but even at 5 Kelvin. But I think one should not forget the fact that qubits can be implemented also in other technologies and in other materials such as germanium. So this is a great example from the Veldhorst and the Scapucci group in that direction. So I think in conclusion, I would like to convince you that quantum computing not only is useful, but is within reach of course, we have demonstration by Martinez of quantum superiority, quantum advantage, as we call it in Europe. But nevertheless, I believe that cryo-CMOS technology really is key to scalability, to a very large number of qubits. And while high temperature CMOS compatible qubits can be coming along in the future, I think that's not really the key. The key is really to bring electronics closer to the qubits as much as possible. And of course, 3D integration is there, but I think most of the pressure is really on us designers to try to make this happen. And with this, I'd like to thank you very much for your attention and invite you to IceCubes next year. We're going to be focusing on cryogenic electronics for quantum applications, quantum measurements. You can see here successful meeting in Fermilab a few years back. Thank you.
Thank you so much, Professor Charbon. That was really amazing talk. I think we have one question by Dr. Zimmerman. Please go ahead.
Thank you. Professor Charbon, that was, as Farba just said, a really impressive talk. I am involved at NIST in the United States in setting up reflectometry on semiconducting quantum dots, both in silicon surface dots, but also in the single atom devices with deterministic doping of phosphorus ions in silicon. And I'm just wondering, I briefly looked up your papers while you were talking. Would you be interested at all in collaborating and helping us by giving us access to your chips, which are very impressive?
Sure. Maybe we can take it offline, but I'll be very happy. One of the things that maybe I did not mention, is that the fact that we are kind of agnostic when it comes to qubits. So as long as you need the high frequencies, radio frequency to operate, I think you can pretty much control almost anything you want. And another thing I failed to mention is the fact that the FPGAs, and this was shown by Stephen earlier, FPGAs at room temperature, but FPGAs can also be cooled at cryogenic temperatures. This is one of the first things that I did in Delft. And this is important because that means that a qubit like yours could be reconfigured. I mean, the control for a qubit like yours could be easily reconfigured using FPGAs or using ASICs. So you don't really have to design a new chip every time you change qubit.
Yeah. So I will send you an email and perhaps we can get together with some others here and talk about this.
Thank you. Thank you.
Marbat, is there time for me to ask a science question as well?
Yes, yeah, we can catch up during the break. Yes, go ahead, please.
Okay, so you talked about running all wires from room temperature down, which is the way we typically do it. You talked about having a true monolithic solution where all of the classical control and amplification and measurement electronics are on the same chip as the qubits. But you also talked about this hybrid thing where you have, for instance, your chip at 3.5 kelvins and the qubits at the base temperature of the fridge. And certainly for your reflectometry setup, where one is doing physics experiments with a 1 or 2 or few qubits at most, that makes a great deal of sense. But I wanted to invite you to explain, or at least give us your thoughts on how much does it help us if instead of needing 1,000 wires that go from room temperature to the mixing chamber, we need 1,000 wires that only go from the 4K plate down to the mixing chamber. Does that really help us a lot? I'm very interested in your thoughts on that. Over.
Yes, that's a very nice question. Thank you very much. Nobody asks this question usually. They say, well, what difference does it make? You're just moving the problem somewhere. Well, there are a couple of differences. First of all, you can use interposers that allow you to connect very, very tiny connections, almost at the chip level, even though you might have to have a 30 centimeter to run, but it can be highly miniaturized. The second thing is that you can implement it entirely in a superconductive regime. So in other words, your 1,000 wires, besides the fact that can be highly miniaturizable, they can all be superconductive with the advantages of now transporting phonons, but transporting electrons very well. And this is thanks to the fact that everything it's below 10 Kelvin. So there are plenty of materials that are superconductive and are easy to produce and cheap, that operate in a superconductive regime below 10 Kelvin. That's a short answer. But the complexity is it's highly reduced. The fact that you don't need, practically you don't need, or you need very reduced thermalizations. The fact that you don't really have to attenuate the signals as you would do at room temperature. As you know, you have to have 20 dBm in order to achieve minus 80 dBm at cryogenic temperatures. If you're operating at cryogenic temperatures, maybe there's only 20 dB of difference. So there's a whole slew of advantages that I can come up with. From the theoretical perspective, there's really no advantage. But from the practical perspective, there are a slew of advantages.
Excellent. Thank you very much. Over.
Thank you.
Thank you very much. I think that was the last question. I really appreciate your amazing talk. We really enjoyed that, Professor Charbon. Okay, so I think.
Thank you for inviting me.
Thank you so much. I appreciate that. Okay, so we move to the next talk at 11:30 supposed to be, but we are a bit behind. I'm sorry, Dr. Soderberg, about that, but we catch up during the break. So 11:30, we have Dr. Katyan Brickman Soderberg from Air Force Research Lab. The talk is on quantum networking at AFRL. Yes, Dr. Soderberg, please go ahead.
Great. Can you see my slides?
Yes, I can see.
Okay, great. So thank you very much for the introduction and thank you for the opportunity to speak today. And I'd also like to thank the speakers that went before me today because they did an excellent job introducing the concepts I'm going to talk about today. So today I'm going to talk about our quantum networking work at the Air Force Research Lab. And before I did that, I just wanted to talk a little bit more about what the Air Force Research Lab is. It is the primary scientific research and development center for the Air Force. Our headquarters is in Wright-Patterson in Ohio, but we have 9 directorates throughout the US and 3 international sites. And you know, our main focus is to develop technologies that will help the DoD in the future. And so just to give you a little bit more detail, we have about 1,200 military people within AFRL, 5,000 civilians. So I'm a civilian government researcher, and we have about just under 5,000 contractor positions that help with everything from research to administrative duties. About 3 out of every 5 of those government civilians are scientists and engineers, and 70% hold a master's degree or higher, and about 36% hold a PhD. And then, of course, we have a whole bunch of business professionals that help us run program management, finance, contracting, and everything else. And then as far as our quantum information science work at AFRL goes, that's spread out across multiple directorates. I've listed them on the bottom of this slide, where in parentheses it tells you the geographic location, and then the letters off to the left are really AFRL letters to tell us what directorate it is. But in New Mexico, we have a satellite-based quantum networking group. I'm from the Information Directorate RI, where we do quantum computing and quantum networking. We have a position, navigation, and timing group that's also based in New Mexico. And then we have a few groups at headquarters that work on solid state quantum defects and things like quantum emitters. And then most of you are probably most familiar with AFOSR, which is the Air Force Office of Scientific Research based in DC. And so at AFRL, we group the quantum information science work into 4 main categories that are shown here on the outside of the puzzle: timing, sensing, networking, and computing. And we have active research in all 4 of these areas across the different directorates that I just spoke about. And then we also focus on supply chain and enabling technology and workforce development. But so just to give you an idea of why the Air Force is interested in quantum information and how it may help the Air Force, that's what this slide is meant to convey. So again, I've listed the 4 areas: timing, sensing, networking, and computing on the left-hand side of this slide. And then for timing, we really want to look at things like fewer timing updates and improved navigation, and we want to make small clocks. For the sensing work, we're interested in things like enhanced inertial navigation and advanced low swapped stands for size, weight, and power sensors. And if you combine the timing and sensing together, you can get self-sustained PNT. That's a different way of saying GPS-like accuracy in GPS-denied or degraded environments. For the networking effort, which I'll focus the majority of my talk on today, we are looking at an entanglement distribution testbed and also how to get quantum systems out into the field, so fieldable low size, weight, and power systems. For the computing work, that focuses on, just like everyone else talked about earlier, faster data processing and asset optimization. And then if you combine these lower two categories, you can do things like distributed quantum computing, where you get all the benefits of a quantum computer, but now you can distribute the computational modules, if you will, in geography, at different geographies. And then the foundation to all this along the right is our workforce and enabling technology development. And so I'm going to focus today on our networking work, and predominantly the networking that we're doing in Rome, New York at the Information Directorate. So there's two thrusts to this research. One is foundational and exploratory research, which is shown on the left-hand side of this slide. And then the other is to get these systems outside of a lab and test in a more real-world environment. So toward the foundational research, our focus is on entanglement distribution and multi-node networks. And we focus on both homogeneous, where there's the same type of qubit at each node, and heterogeneous networks, where there's a different type of qubit at each node. So the three technologies we're focused on, and we have active research in each, are trapped ions, superconducting qubits, and quantum photonic integrated circuits. And we also have a quantum algorithm team that I won't talk about today that's predominantly focused on programming and algorithm development on commercially available quantum devices. But all the work they're doing will help inform the network layer, because eventually when we go to program this quantum network, the programming is not going to look too different than what the quantum computing devices look like today. The application is very different, but I think the programming is going to be very similar. And then as we move toward testing things outside the lab, the focus is to reduce the size, weight, and power of all the quantum systems so that we can operate on airborne platforms. And the one we have in mind in the short term is an unmanned aerial system, or a drone. And of course, the results from the foundational research will seed development into this outside testing. And then, like I just said, we're going to try and put a quantum system, either a photonic system or a trapped ion, on a UAS and connect back down to some other quantum system on the ground in the next couple of years. And so in the longer term, what we're pushing towards is a test bed, an entanglement distribution test bed. And this test bed's a little bit different than most of the test beds that are up and running today, in that it has a very DoD-centric focus on it. So what this slide shows is 3 columns, and each column is a different physical site at AFRL in Rome, New York. So on the far left is our open collaborative environment. This is our Innovari Advancement Center. It's a new facility that just opened in the last year or so that's meant to help us strengthen collaborations with both international partners and our domestic partners, because it will allow us to bring foreign nationals into our labs. And so for our in-house labs that sit on a DoD site, it's very difficult for us to bring in anyone who's not a US citizen. And so motivated by that, we started this new facility. It's not just for the quantum work within AFRL in Rome, it's for all the work we do. We're the Information Directorate, so that includes things like cyber, machine learning, and stuff. But for the quantum work, we have 2 lab spaces in there. They're kind of open concept labs, and that the trapped ions, the superconducting qubits, and the quantum photonic integrated circuits are all in one big room to kind of encourage people to talk to each other across qubit technologies. And the long-term goal there is to get a quantum network with at least 3 nodes, where a trapped ion, a quantum integrated photonic circuit, and a superconducting qubit are interfaced to distribute entanglement around that network. Eventually, we also want to have this as a user facility of sorts, not the same scale as the DOE, but a very small user facility where our collaborators could come and either plug in their quantum technologies, maybe a different type of qubit than the ones we have, maybe an NV center or a neutral atom, to test on our network, or to bring a classical technology that needs to be tested on the network. Because as Prem pointed out earlier, having a classical network seamlessly interface with the quantum network is going to be a crucial component to all this. And so we have to understand how those two things can work together. And what we want to study in this environment is the very basic research focused on heterogeneous interfaces and entanglement distribution. How do you distribute entanglement? How do you go beyond 2 nodes? How do you go beyond 3 nodes? And then once you have that entanglement, how do you verify and validate it? And what types of things can you do with it? And so then the most promising technologies will see development into the middle column, which are our in-house laboratories. So they are at a DoD facility. And here the focus turns to applied research that focuses on heterogeneous network integration and really reducing the size, weight, and power of these systems so that we can then take them out to the test sites and perform some more advanced demonstrations. And we have several drone test sites available to us locally. And so that's one reason we're pursuing drones. One is we also think it's just an interesting platform to put a quantum system on. It gives you a lot more control locally than, say, trying to go up on an Air Force plane of some type. So ultimately, this test bed can support ground-to-ground and ground-to-air links. And we would like to test, and we will be able to host other quantum systems like clocks, sensors, and distributed computing elements, because once you distribute entanglement across a network, there's going to be networking protocols you want to perform, of course. But in addition to that, I think there's a lot to learn about how to get clocks and sensors on these networks and what benefits will the distributed entanglement give them. And so this is just a snapshot of our Innovari Advancement Center. It sits about a quarter mile from our main DoD site. And we're looking for partnerships for visiting researchers and student opportunities. In this center, we want to focus on the quantum software layer applications and access, mostly for the networking piece. The heterogeneous qubit interfaces for entanglement distribution, like I just talked about, and also how to verify and validate quantum networking components, both classical or quantum. And so toward these heterogeneous quantum networks, I already said this, so I'll go through this slide a little bit more quickly, but really how the network gets set up and exactly what qubits you use and how they're connected and how the entanglement will get distributed will most likely depend on the end application that you want to do. Depending on what that end application is, you'll probably configure your quantum network very differently. And so the ones that we're focusing on, the qubits, are photons, ions, and superconducting qubits. And what we really want to do is produce the building blocks for this future network so that we have a complete capability to have a trapped ion that may be serving as a memory, to connect to a superconducting qubit that may be serving as a data processor, to an integrated photonic circuit that we want to do some operations in the photons before we send them to the next network node. And so we want to have these Lego building blocks so that we can stack them any way we need to as we start to delve into what applications we want to investigate. And so to give you an idea of what this might look like, I'm going to talk a little bit about how we plan to interface some of these technologies together. And what this slide is meant to show is a trapped ion system. On the lower left-hand side here is an ion trap from Sandia National Labs. And that can trap an ion using an oscillating electric field. And then typically in trapped ion setups, what you do is you have a wide array of lasers that you use to perform the cooling, the detection, and the qubit manipulation operations. And most of the ion species that people use today tend to be in the ultraviolet regime, which makes some of these operations difficult. It makes the optics very expensive. A new qubit technology that we're pursuing is barium-133. So a lot of people have used barium-138 previously for quantum information experiments. And the thing that makes barium-133 different is that it has hyperfine qubits. That's set by the atomic structure, but all it means is that it has very two well-defined ground states. These are the same types of states that they use in atomic clocks, and all the reasons that make them good clock states make them good qubit states. So we would really prefer to have a species with hyperfine qubits. And the other species we're using in our lab is ytterbium, which does have hyperfine qubits, but it's operating in the UV, and it's going to make many of the interfaces that I'm going to talk about today challenging. So a few years ago, the group at UCLA, led by Wes Campbell, trapped barium-133 for the first time and showed that it was a viable qubit option. So we started an effort here on barium-133, and the visible light will make the interfaces more straightforward. It greatly reduces the optical complexity. In fact, all the light should be able to go through a single fiber, and then you get all the qubit capability that you need to due to the hyperfine splitting that I talked about. And really, we're using this to focus on connections to other qubit technologies. And so what the picture on the left is showing, that you could have a single trapped ion with all the light that you need coming out of a single fiber. And then another unique thing about barium is that the light you use to excite the different transitions within the atom are different than the light you use to detect. So how we get information out of a trapped ion is that we shine light on it, and it excites some transition within the ion that tends to be a cycling transition. So a ton of photons are scattered, and you can collect that light on a camera to see if the ion's bright or dark, because each hyperfine level, one appears very bright when you detect and the other appears very dark. So those are like our zeros and ones, the bright and dark. And so with barium, because we can filter out all the incoming light, we're able to just detect the light we're interested in that gives information about whatever protocol we're performing. And so if you look at a typical trapped ion experiment, you see a bunch of lasers on the table with fiber AOMs and fiber EOMs and an array of optics. But if you can combine all these into a single fiber in the end, like we can with this barium system, well, then you can start to think about doing things differently, because what this diagram starts to look like is an integrated photonic circuit. And this is an aluminum nitride integrated photonic circuit from our photon team that's in the lab next door to us. It has 36 tunable interferometers on it, and they're using it for quantum processing applications. But what we want to do is actually replace part of our laser table with these types of circuits. And so we're investigating that right now. And so the status of our effort is that for our in-house lab, so these are in the center of that test bed chart I showed you earlier, we recently trapped barium ions, which is very exciting. These are what you can see in the blue picture. The dots in the center are, I think it's 7 or 8 trapped barium ions. And barium's also unique because of the color it emits is a teal color. So you could actually see this by eye. This picture was actually taken with a normal camera, not a fancy camera like you need for some of the ultraviolet species. But the problem was that our in-house lab had temperature stability issues, and the temperature swings were too great for us to operate in there. So we just got some new lab space renovated, and we're in the process of moving this lab into our new lab space with better temperature stability. We also have our Innovari Advancement Center labs up and running. So about a year ago, it was like the picture on the left, just an empty room. And then late last year, we moved into the Innovari Advancement Center, and just a few months ago, we trapped our first barium ions there. So we're very excited to be up and running in our new center. Okay, so now I'm going to switch gears a little bit and talk about our integrated photonics work. So the integrated photonics team we have here has worked with the AIM, the American Institute of Manufacturing for Photonics in Albany, our neighbors just down the road, to develop a quantum wafer. So that's the picture you see here. It's a 300mm quantum wafer that has thousands of devices on it. I've pointed out a few of them in the right-hand side of the slide. We have things like trenches for one day inserting the matter-based qubits right on the chip, entangled photon sources, and then photodetectors to interface eventually with the ions. And so they're in the process of testing these devices now and also building the next generation. And another thing that this team is working on is an ultra-wide bandgap photonic platform for heterogeneous qubit integration. So really the future hope, for most groups working in quantum information is to have everything chip-based, because it just makes everything so much simpler. And so what our team is working on here is an aluminum nitride substrate, which can go from the UV all the way to the infrared. And so you could more or less host most of the qubit technologies that are available today on this single substrate. And so they've built these, they designed and fabricated them, and they've tested in the ultraviolet, the visible, and the infrared with just light. This doesn't include any matter-based qubits yet. And so for some of these waveguides that are made, what we want to do, I told you, is to be able to replace our optical table components with them. And so we're in the process of doing that. This picture on the left is a false image. It just shows the light coming out of the waveguide. That's what those blue dots are. And we've superimposed it on a linear array of trapped ions to show that, you know, if you make the spacing in the waveguide the same as the ions, then that would be a very easy way to address them. And we're actually in the process of testing that device right now on ions. So hopefully soon we'll have a real picture where we're illuminating the ions with our integrated photonic waveguides. And these particular waveguides were designed for both 493 and 650 nanometer light, which are two different transitions within barium. And then the team's also working on waveguide base splitters for remote entanglement operations. So that's basically an interferometers. How you get these remote entanglement operations to work is that you combine photons from different systems on a beam splitter, and then you wait after the beam splitter for the proper detection event, and it will herald the entanglement within the matter qubits. And so we hope to test some of those in the longer term with our trapped ion system as well. And then the final integration I want to talk about is how we might interface a trapped ion with a superconducting qubit. So if we can get our barium ion to work with all the light going in and out of one fiber, both the detection light and manipulation light, one thing you could do is actually trap an ion above the tip of a fiber, and then you have an ion trap on a dipstick. So there's a few things that you could do with this. One is that you could use it as a platform for things like sensing and clocks. You could put an ion next to it that's hard to read into and write out of, and use quantum logic operations to transfer that information into the in and out of the barium ion, which is much easier to read. So this is reminiscent of what the NIST group did many years ago now, where they made one of the world's best atomic clocks using an aluminum ion, and I believe the quantum logic ion next to it was either a beryllium ion or a magnesium ion. And so that's the same idea here. And then it would be more portable because everything's just on the tip of a fiber, so it'd be ultra compact. So the other thing that we want to try and do with this is put it into our dilution refrigerator that houses our superconducting qubits. So there's a few ways that we want to interface these qubits. One is that we may put the ions up on the 4K stage of the fridge, and then of course the superconducting qubits sit at the millikelvin stage, and build some electro-optic or acousto-optic transducer of sorts to get the two qubits to talk to each other. But another fun thing to try, and a little bit crazy thing to try, is to actually put the ion right next to the superconducting qubit and see what happens. And so we're pushing towards systems like this to explore some of those scientific things. Okay, so now I'm going to turn my attention to the superconducting and just give you an update on where we are with that effort. So this is a new effort for AFRL. The superconducting team has only been here for about 3 years. We recently installed a Blue Force dilution refrigerator in our main DoD facility lab. We also now have one in our Innovari Advancement Center as well. They commissioned the fridge in March 2020, and then they began taking measurements of qubits in October of 2020. And the qubits that we measured were provided to us by both MIT Lincoln Labs and Syracuse University through different collaborative agreements. And so we're partnering with multiple external institutions to fabricate and provide transmont superconducting qubits and other devices, because we don't have any fabrication facilities on site for superconducting qubits. And so just late last year or early this year, we showed our first superconducting qubits. And so they measured a T1 time of 131 microseconds and a T2 echo of 215 microseconds. This is on par with, you know, the best results in the world. And so it's great. You know, I think we're off to an awesome start here. And we also did a randomized benchmarking measurement where we showed a single qubit gate fidelity of greater than 99.9%. And so now we're working on new qubit coupler designs to interface the superconducting qubit modules to things like a trapped ion or an integrated photonic circuit. And to give you a little bit more detail about that, we also recently installed an adiabatic demagnetization refrigerator, an ADR, in the Innovari Advancement Center. And this is not meant to do high performance quantum information operations, but it's meant more as a testing fridge. It doesn't get as cold as a dilution refrigerator, but the turnaround time on it is very quick. And so we'll use this device to test chips at 30 millikelvin to see how they operate before we move into the bigger dilution refrigerator. And so we've begun the initial characterization of our electroacousto-optical converters at cryogenic temperatures. And we're also partnering with our Materials and Sensors Directorate that's in Ohio to look into some novel materials for transducers and superconducting circuitry. And also, as I said before, we're coordinating, the superconducting group is coordinated with the photonics team locally to try and build a chip that has all 3 qubit technologies on it. So kind of the dream is to build an integrated photonic circuit that can house superconducting qubits and trapped ions to have all 3 on the same chip that would go into a fridge, and then have the capability between optical fibers to connect distant fridges. And so that's kind of our grand vision for what we're pushing for at the Innovari Advancement Center. And so just to give you an idea of some of the questions we're trying to answer is, for the ion and superconducting quantum interfaces, how do we couple strongly for efficient information transfer, and what are the best degrees of freedom to use? That's a really hard problem to solve. How do you get a trapped ion that's up at optical wavelengths to talk to a superconducting qubit that communicates in the microwave, and the superconducting qubit can only operate at millikelvin temperatures, whereas the ion can operate, at millikelvin all the way up to room temperature? And then what are the best degrees of freedom in each system to choose? It's not necessarily clear that you want to be in a quote unquote good qubit regime to get this interface to happen. You may have to go out into a messier, noisier qubit area to get the 2 to talk to each other, and then transfer the information back into the good quote good qubits within the 2 systems. And then how to make superconducting circuits compatible with photonic circuitry and trapped ion platforms. One thing we're worried about is how we can mitigate the quasi-particle poisoning that will happen on the superconducting circuits. And how do you interface these qubit modalities across very large temperature gradients and timescales? And then, if you can do all that, how do you efficiently encode and decode multi-part type quantum information between qubit modules and communication buses? So we're not only worried about information transfer between different nodes in the network, but also within the same node and network, you need to be able to perform local quantum information processing operations to include entanglement. And so with that, I'd like to thank you very much for your time. Here's our group. This picture's a little bit old. It was taken in June 2019, but I like this one because it was a summer that we had about 20 interns that came into our summer program. And so our group was quite large for that summer. And we're always looking for students, postdocs, and visiting researchers. So if you'd like more information about that, please feel free to contact me. So thank you very much.
Thank you, Dr. Soderberg, for this really interesting, amazing talk. I really enjoyed, especially that we are very interested in the drone communication between drones and ground, and drone to drone and robotics applications. Is there any question? Let me see. I don't see. Neil, you have a question? You raised your hand from the previous. Is it still up? The previous question.
Sorry, I just forgot to lower my hand. Thank you, Charbon. Over.
Okay, thank you. Thank you, Dr. Soderberg. So if you want to apply for one of these collaborations that, for example, you said communication, how do you, can you give us a little more information about that?
Yeah, I'd be happy to. So there are different ways. If you're a student, if you want a visiting researcher, so we have a student program for the summer. I say student, but it can include faculty and postdocs as well. So if you're interested in that, send me an email and I can send you the link. It's through our sister organization. It's a not-for-profit Griffith Institute that handles that application process for us. If you're interested in a more collaborative effort for research, then there's a few agreements, things like educational partnerships or CRADAs that we could put in place. And then that allows us to share information and people back and forth. And then it's also possible for us to have contractual efforts with people, depending, that depends on funding, but you could apply to our BAA, say, if you have an idea, you could send a white paper to our open BAA.
Thank you.
And then that will make it to our team eventually, and we can talk to you more.
Thank you so much, Dr. Soderberg. There is a question by Paul. Can you say more about what the quasi-particle positioning problem is?
So that would be a good question for Dr. Matt LaHaye, who leads that effort. I see Britton's on the line. I don't know if he's here right now. He's a speaker in a later session. I would have to put you in touch with Matt to answer that because I'm not as familiar. I'm the trapped ion person, so I'm not as familiar with the quasi-particle poisoning. I know it's a source of decoherence in the system, and kind of any noise or source of heat or light can cause issues in these superconducting circuits because they need to be at millikelvin temperatures to operate. So anything that disturbs that local environment can really be detrimental to the qubits. But if you send me an email, I believe Prabhat has my email address. I'm happy to put you in touch with Matt.
Thank you, Dr. Soderberg. I really appreciate your talk. It's very interesting, especially me and Dr. Quadrelli and our team are very interested in the type of work that you're doing. So thank you so much again for this great talk. I think we can communicate with you by email later for more questions. Thank you so much.
Yep, sounds great. Thank you so much.
Thank you very much. Okay, so I think our next talk is at 12:30. If I'm not sure if I'm sharing the correct screen. So we'll have. Okay. We'll be back in about 10 minutes for the next talk. Thank you, everyone.
Barbad, this is Neil. Would it be okay if I play around a little bit with sharing my slides while we're in the break?
Of course, yes, sure. I stop my share. Please go ahead. Feel free to share.
In particular, I'm curious to find out if I will be able to see the chat window during my talk.
You don't see
And
the
I won't. Okay, so can you see a red laser pointer over the N in Neil?
Yes, yes, I can see.
Okay, good. So I will ask you during my talk to monitor the chat window.
Sure.
And if there are questions along the lines of, can you suggest a book to read or a workshop, or can you explain some general concept, then I'd ask you to just not bring those up during the talk. But if there are questions that are actually to clarify something I said or to further discuss something I've actually said, I'd be happy for you to help me out by bringing those up during the talk.
Of course.
Is that okay?
Of course, that definitely, I understand. Sure, we'll do that. Thank you.
For both, can I also try?
Hi, Professor Georgiou. Yes, of course. Yes.
Yes.
Please.
So let me see. So share screen, right? Oh, that's no problem, Neil. No problem. Continue. Let me see here. How do I do this? Share desktop. Let's see here. Oh, so it's not so trivial. 1 second.
There's no share screen at the bottom?
There is 1 second, but I need to do some things because I 1 second, I have not used it on this Zoom. Okay. Zoom will not be able to record the content of your screen.
Well, I think Neil is still sharing. Maybe you need to stop sharing first, I guess.
Let me see here.
This is
let me see here. Share.
Oh, yeah.
Okay, let me see. It works. Okay. So I can do either this or I can do this.
Oh, yes. It is.
Okay. What is this? Open. Would you like to record? Grant access this application. I don't know what this thing is. Screen recording. I don't know. Deny or open system preferences.
I don't think it's from my side.
No, this is not from you. Okay, so whatever that thing. Yeah. Sometimes these computers are have a mind of their own. So okay, so you can see this, and then if I want to do
full screen,
tools, view, full screen. Okay, so this is, and this looks fine, right?
Perfect. Yeah, that's great.
See everything on the side. Okay.
Thank you.
Yeah, good that we did it.
Sure. Thank you.
I feel a little bit better.
Great. So we'll be
Okay,
back.
I'll see you in a few minutes. Go
5 minutes.
to drink some water. I'll be back.
Thank you so much.
Oh. Hello.
Hi, Professor Georgiou. Let's see. If,
So I can start sharing the screen.
yes, would you like to?
Maybe I can do this thing here, share. Let's see. Tools or not. Just 1 second. Let me go the other way around. Actually, it's better. This way. Share. This is like this. Okay. And now I can probably I can go through here. Right. Tools. No, view. And full screen. Yes.
Okay, that's great. Okay, Professor Georgiou. So it's my great pleasure to welcome Professor Tryphon Georgiou from University of California, Irvine. Professor Georgiou's talk is on density transport and the Linbald equation. Thank you, Professor.
Thank you.
Go ahead.
Thank you very much for board, and I thank very much you and the organization of this great workshop. It's a privilege being here. And I have to say that the presentations before me and probably the ones after me, the results are beyond impressive. The comment that we are still working on the times of at the very early stages beyond the transistor, and to draw the analogy, diodes, whatever I forget now the name, resonates, but seeing the quality in the technology and the results, it's really impressive, and it's very hard to imagine how the future is going to look. So my talk is not going to be on technology. It's going to be more theoretical, and it's going to be more mathematical, so to some degree different. It started from some tantalizing questions about similarities and differences between the classical and the quantum world. I've been interested for quite some time on non-commutative geometry in connection to quantum channels. But today I'm going to talk about some beautiful connection between a subject which is called optimal mass transport and the dissipation mechanism in quantum evolution. So the title is density transport. So in the process, I'm going to tell you a little bit about a classical subject and its relevance in information theory. So the background is that about 20 years ago, Jordan Kindler and Otto published a very influential paper where they proved that in a classical context, the gradient flow of the entropy functional with respect to a certain specific metric is actually the heat equation. So the talk will be about the quantum analog of exactly this statement. So let me parse it a little bit. So here you have the classical Shannon entropy, which quantifies information in a distribution. And then we have the heat equation that we all know and love. You have the Laplacian on the right-hand side and the partial with respect to t. Now, this is a functional on the space of densities, distributions, and you can take the gradient of that, but for that you need a metric. So if you use a certain specific metric, the Wasserstein metric, a metric that compares two densities, and I will explain it a little bit, you actually get the heat equation. So this, in one statement, it links three very important concepts. And the very interesting thing, and again, as I said, the tantalizing question is how far this connection goes. So I'm going only to give you the gist of it. In the process, I'm going to be able to tell you a little bit about what optimal transport is. And the remaining of the talk is a non-commutative version. So this, some of the motivation and the connections between the von Neumann entropy and the Lindblad equation, which is, the Lindblad equation is exactly the analog of the heat equation for open quantum systems, systems that are coupled to a heat bath and you have loss of information. You know, the system, the equation of the system is a partial trace when it's coupled to something bigger. So here, this is a 4-slide a quick rundown of what is optimal transport. Optimal transport goes back to Gaspar Monge, a great mathematician, founder of École Polytechnique, one of them, was working on Napoleon's army, and he came up with this idea at the time of how do you move mass from one point to another. So he came with the idea that you have to move a mass and pay for how far you're going to move it. So if I want to compare two distributions, I don't subtract, integrate differences to get a norm, but I want to actually say how far I'm going to move a pebble from position X to T of X. So she was looking for a transportation map. This notation here means that the push forward of a certain measure is another measure. So it took almost 150 years before the problem had a very nice resolution in the work of Leonid Kantorovich in the 40s. In fact, he received the Nobel Prize for this work because the transportation of resources is extremely important in econometrics. He resolved it in the following way. I'm going to just mention this also in the context of quantum. Instead of looking to move from a point X to some other point T of X, T is the transportation map, you postulate coupling the 2 points through a joint distribution. So you can think of X and Y as random variables, and this is the variance of X minus Y. And pi is called the coupling between the two marginals. So the integral of pi, if you think of them as distribution in one coordinate, gives you one of the measures, and this is a density. It's easier to think of densities, and it's a density in the other. So basically what Kantorovich did is said, instead of moving the blue to the red, let me just put them on orthogonal coordinates and look at the product space. And in the product space, I'm looking for a measure that matches the two. So I hope this is clear. It's a very simple way of writing it. And the problem becomes linear. So he invented linear programming to solve this problem because there is a cost, there is a cost, and the cost sits here, and the unknown is the pi, and the margins are data. So now we come to yet another development in this subject, which is in the last 20 years is rapidly taking, transforming the way we're doing sometimes things in probability theory, in stochastic control, in thermodynamics, and it has the same problem of moving one mass to another, assumes a dynamical formulation where you have a continuity equation here. So this is the divergence of a momentum. So you choose a velocity field that's going to move one distribution to another. And in the process, you would like to do it in such a way so that you minimize an action integral. This integral here is velocity squared times the density. And this problem has the same solution as before. So the solution of this infimization is precisely the infimization of this, this problem, and it's precisely the infimization for this problem. All of those are called the Wasserstein distance between the beginning and end distribution. I'm going to give you a slight insight into what's this connection. The cost x minus y squared, x and y are 2 points in the Euclidean space, is the same as if you try to infimize the velocity of a curve, C1 curve that moves from one to the other. And the optimizing curves are straight lines between the two. This is just Euclidean geometry. When you lay on top of that this probabilistic structure, there is no significant complication. You can look at probabilistic structures that move from one Dirac delta to another. So this is a joint distribution on curves and path spaces. And this is just the Euclidean distance between 2 points. And it's given with this complicated expression. And you can put more layers into this. And basically you connect the Kantorovich formulation, which cares about going from beginning to end, to a dynamic formulation that doesn't only care from going from beginning to end, from one distribution to another, but minimizes a kinetic energy, or the expected value of a kinetic energy, or if you like, the same expression can be thought of as an action integral in very much classical physics. So this is sort of a very quick rundown on some ideas from optimal mass transport. You can be viewed as a stochastic control problem where you have a dynamics and specify marginals, or you have a PDE formulation of the same. Now, one is interested for many reasons to push this kind of a framework or understanding of how you relate non-commutative objects and do matrix valued optimal mass transport. And you can, motivations from that is from, for example, medical imaging and interpolating matricial distributions, and also quantum. So I'm going to go quickly through the slides because I need to keep time or track of time. So this was sort of the background, and at the same time there were reasons to start looking at an analog in the quantum world. So we can think of transport in the quantum world and transporting a density to another density. These are Hermitian trace one matrices or operators. It corresponds basically to the two ends of a quantum channel. The quantum channel is materialized by a Krauss operator, trace preserving totally positive map E that moves one density to another. And one would like to understand a little bit about the geometry and maybe calibrating channels which specify relations between the two endpoints and bring in the cost, some sort of a cost. So the analog of a Monge-like formulation of optimal transport for the quantum is pretty much open. There are some thoughts, but there's no convincing resolution of how natural one can develop this framework. There's a little bit more on the Kantorovich-like formulation, And there is a lot more on the dynamic formulation, which I'm going to talk about, and it couples to the Lindblad equation. So if you like to think of a Kantorovich-like formulation of optimal transport, what you would be looking at, the analog would be the following. You have two density matrices at the two ends, let's say, for example, of the quantum channel or some other structure, and you're looking for a density matrix in a product space when, if you take a partial trace, it gives you the two marginals. And then at the same time, you try to minimize a certain cost. Notions of what a cost is, I'm going to come back to this at the very end of the presentation. And this is still not fully understood and resolved. However, the third formulation of optimal transport, so this is simply states again the same. There was some preliminary work a few years back. So the third formulation is actually quite interesting and has given some fruits which draw some, again, tantalizing analogs and similarities and dissimilarities between the classical and the quantum world. So the project here is to replicate this dynamic formulation where you try to minimize some sort of a kinetic energy, having some continuity equation in the background that preserves, for example, the mass of rho, or here the trace, and matches marginals. Some clue to this can be given, and was given by the Lindblad equation. The starting point is the Lindblad equation. Here I have the coefficients of the Lindbladian symmetric for simplicity. The Lindblad equation looks like this. The first term over here is the Heisenberg term, the Schrödinger part. And this thing here is the diffusion, which basically quantifies the coupling to the heat bath of the rho. Rho, again, is a Hermitian positive definite trace one density matrix. Now, comparing this expression with a continuity equation is quite suggestive. And before I show you how exactly the similarity is, I would like to explain a little bit about, again, this is almost like elementary, but it is worth bringing it on the same page. So when we do calculus, ordinary calculus, we like doing derivatives, we're taking derivatives. But the functions may play a double role. So for example, here the f can be thought of as an operator. So you take the g of x and you just multiply with f. And you have an operator here, which you would take the derivative. Now, how would you take the derivative of f? The derivative of f is simply the commutator of these two operators. So when we take derivatives at the level of operators, you just have to take commutators. And you can see this thing here. There is a test function g. And if you first multiply and take the derivative, or take the derivative and then multiply, you get this action. So therefore, it's quite natural to think of taking, this is just notation here, that you have a matrix and you take the derivative of a matrix with respect to another matrix, and you just define this to be the commutator. By having this, it allows you to view the collection of a number of commutators. Oops, sorry, I keep jumping here. A collection of commutators as a gradient. So the L are non-commutative coordinates. The moment you think about that, we have some very nice calculus, which again, it's not totally new, but it formalizes and allows us to think in a different way about continuity equations and so on. So this is a gradient. The gradient of a product satisfies the usual rules. Then you can compute the divergence by duality, having some inner product, standard inner product. When you have matrices, you take all collections of matrices, then you take inner product by summing traces in the suitable sense, and then you could do duality, you have a divergence. So that's the divergence operator. So if I have a matrix here, and I take the divergence with a collection of non-commutative coordinates, it gives me this. So with that under our belt, we can simply go back and write down the Lindblad equation in this way, so that the right-hand side just simply the Laplacian. It's the gradient times the negative of the divergence. And this part is simply the Schrodinger equation. So this is really the heat equation with a drift term. So now we would like to carry out the program. We carry out the program of doing optimal transport. So we have now a way of thinking about the continuity equation for matrices. So this is a matrix, and this is the divergence with respect to a collection of non-commutative coordinates. So there is no underlying space. We don't have the classical world, but we still have these non-commutative coordinates. So we can think of putting here a momentum operator. Now, how do we multiply a density matrix times some sort of a velocity field, which is also matrices, to get a legitimate object, which is Hermitian or skew Hermitian, depending on the setting, whatever we need. So there are certain choices that in the quantum world, there's a whole zoo of ways you can multiply things and get the right object. For example, if I have rho, which is a symmetric matrix, and V is another symmetric matrix, I can choose in this last picture here to multiply, put the V in the middle and multiply with half of the rho on both sides, and I still have a symmetric matrix. Or if V is skew symmetric, as velocity fields are here in this context, these are technical details. Again, I retain skew symmetry. Now, there are two other ways which are extremely interesting, is this one, and there is this one, the Kubo-Mori multiplication, which appeared, it's also in the work of Feynman, going back 50 years. So this is basically a non-commutative multiplication between two objects, matricial. You multiply, because you don't want to put them on one side, you multiply a little bit on the left, a little bit on the right, and you integrate over all possible splits. And this is extremely nice and beautiful and gives a very nice geometry. So having this, we can try now to replicate with two of those. The second one is more interesting than the second, the first, but I'm going to devise both at the same time because the first one is easier to explain. You can define a distance between two density matrices. Following exactly this formula, you say, I would like to minimize kinetic energy. And kinetic energy is, you can define it to be the trace of the density matrix times some velocity fields, and the velocity fields are obeying a continuity equation that matches the two marginals. And you can carry out this product, this plan. We can go, we can do duality theory, and I'll briefly explain this. The second plan is you have a Wasserstein distance with the second option. And the second option is to use the kinetic, the momentum to be this. So the way you multiply the velocity is you put a rho on all sides and integrate with an extra degree of freedom. So this here, the inside is just simply a non-commutative multiplication. And then you can write down the continuity equation this way. So I think time is running short, so the technical part are going to go very quickly. So briefly, you crank the mathematics, the handle, you put Lagrangian, you try to quantify the structure of optimal velocity fields. And you can prove that if you find a velocity field that matches the marginals, life is good and it's optimal. There is a beautiful Riemannian structure, which I think I overestimated, and I have a lot of slides, so I skip through this, but you look at perturbations of the Hermitian operators. These are matrices which have trace 0. And then you can relate perturbations with Lagrange multipliers and with velocity fields, and you can have a beautiful Riemannian structure in the tangent space of density matrices. And you can define Wasserstein distances between the two marginals, which are basically also geodesic distances. So you can think of a curve in the space of density matrices, which has very nice properties. You have some convexity in this problem. And then the moment you have a metric, you can try to think of how you do gradient flows. So the choice for the metric by your choice of multiplication 1, if you have the von Neumann entropy, this is the trace of the product of rho log rho, you can crank the handle here, you look at the steepest ascent, and the steepest ascent gives you that the velocity field has to be of this type. And then you have a gradient flow, which is nonlinear, and it's different from Lindblad. However, it's extremely interesting in its own right. And perhaps some of you, and the younger people listening, may be able to find a different interpretation and insights in this. So the second one, which is sort of the logarithmic multiplication, again, you can carry the handle. It's much more complicated. So the duality is an object that I don't even want to show you. And then you look at the gradient flow. Oops, here it is. So you take simply the derivative of the von Neumann entropy, and you look at it and you see what's the gradient ascent. So the gradient ascent direction is then minus the gradient of log rho. But now if you plug this into the continuity equation, and the continuity equation is rho non-commutative multiplication with the velocity field. And the velocity field is the gradient of log rho. So the non-commutative multiplication has the velocity field sitting in the middle and the rho here materializing on both sides. So this formula here looks very complicated, and then you need to take the divergence of this. However, there is a miracle identity. It's absolutely miracle. So it's the non-commutative analog of taking the derivative of the logarithm and then multiplying by rho. So if you take the derivative, the rho comes at the bottom and cancels this rho and just leaves the gradient. So the same thing is true in the non-commutative world. And the moment you plug this in there, you get basically the Lindbladian. So there is a lot of magic in here, which is tantalizing. What it is telling us is simply that the Wasserstein distance, the particular non-commutative notion of distance between densities, is a natural notion of distance which drives the dissipation mechanism. So this is the precise analog of Jordan, Kindler, and Otto's result. To recap, you have a choice of multiplying. How do you multiply? And there are more things. There's a whole zoo of ways you can do this. This particular one is extremely interesting. The other one has some other advantages, which I cannot discuss now due to shortness of time. And just briefly, I have a few minutes. I wanted to say the Kantorovich formulation of optimal transport is not well understood. The Kantorovich formulation would try to link two density matrices through a density matrix in a product space. This is would be the analog of devising a joint probability at the two ends of a quantum channels, which we know is not possible. But yet, many elements might be able to give us some natural way of doing this, as long as we understand how one can penalize such coupling. And the coupling maybe should go through the duality. The duality would require that you connect points in an underlying space and have a distance between them. And points here, there's no underlying space. So the closest to that are rank 1 trace density matrices. So, so there is some life in this, but it's not well understood. So concluding remarks, we have the Lindblad equation as a gradient flow. There are some other practical applications of this in the non-quantum world, tensor field interpolations and so forth. I just want to have a page with references. This result that I talked to you about appeared almost simultaneously in 3 papers that were uploaded on they're here on the archive within 1 week from one another by Eric Carlin, Mitzenweig and Milke in our group. There are some papers that influenced, most important Carlin's paper in Mass in 2014. We also had a version of something very similar. And there is more work that is taking place, but it is a different take on an old subject. So it's just simply theory and mathematics. And I just wanted to bring this to your attention because I really believe that there are more things to be understood. The subject is, of course, 100 years old plus, but you know, we can dream of it at different levels: the technology level, and the mathematics level. Because, by the way, I just want to end with one little thing. Erwin Schrödinger in 1932 published 2 papers on the directionality of time, and that launched a subject which is called Schrödinger bridges. And this subject is well and alive, trying to give another more classical interpretation of quantum mechanics, and connects very much to the work on optimal transport. So if any one of you would like to look at it, the buzzword is Schrödinger bridges. So with that, I would like to end my talk. Thank you very much for your attention.
Thank you, Professor Georgiou. That was really amazing presentation, especially that we also looked into the theoretical aspects, because previous talks more applications. That was really interesting. Thank you so much. So let's see if there is any question.
Any question?
Okay.
If I went too fast, I apologize. It was kind of different.
It was yeah. It would be great to have the papers later, to have those references to study a little bit more. I personally really enjoy the theory aspects. It's a bit hard, but I really like that.
But fast.
Sometimes it's hard to follow, but really interesting. Thank you so much. I don't think there is any questions so far. Maybe we can later on. If there's
yeah, please reach out to me. Later I can send you papers.
I would like myself to get those papers.
Thank you very much.
Learn more about them. Thank you so much, Professor Georgiou. Thank you. All right, so the next talk is by Dr. Clarice Aiello from University of California, Los Angeles, on the topic of from nanotech to living sensors. Professor Aiello just informed me that just now that she may not be able to attend herself, so she sent me just now this video, which I would like to share with you on her presentation. So I hope you can see the video. Can you see my screen?
It's loading.
I'd like to call myself a...
Am I sharing the sound? I guess I need to share the sound. Make sure share sound.
Quantum engineer. This means that I develop apparatus. I like to call myself a quantum engineer. This means that I develop apparatuses to study and control objects that are so small and so well protected from their environment that they are better described by the laws of quantum mechanics, as opposed to the laws of classical mechanics that ruled everything big around us. So people get a little bit surprised when I tell them that I study things that might be happening in birds and butterflies. So before I explain where I'm going, I really need to tell you where I come from. So we're going to start talking about quantum mechanics, and we'll soon be motivating things of biological relevance, such as organismal migration, how our cells respond to oxidative stress and radiation. And I hope I will have motivated a bit how we can learn with nature to build better technologies. And this is because I'm a quantum engineer who's interested in how quantum physics informs biology at the nanoscale. So let me start by saying that I think humankind is obsessed with measuring things better because we think it means that we can understand nature better. We can think about measuring better frequencies with this atomic clock that sits at NIST and lets us define very precisely what a second is. We can think about measuring better magnetic fields so that the magnetic resonance image of our baby is better resolved. And we can think about measuring better acceleration so that our gaming experience is enhanced. But what happens if the quantity that you want to measure is very, very small? Or worse, what happens if the object causing the quantity to be measured is very, very small? I'm going to argue that in this case, you need a tiny little sensor that is capable to measure tiny little things. If the sensor is tiny, let's make it very tiny. Let's make it quantum. There's a whole body of mathematical arguments that prove that if you use a quantum object as a sensor, your measurement is improved. In other words, the sensor quantumness enhances the measurement, and this underlies the field known as quantum sensing. I'm going to talk to you about a technological quantum sensor that I worked with in the past. In particular, I put a single spinning diamond to use as a quantum magnetic field sensor. So spin is a merely quantum mechanical property that measures how well a particle interacts with magnetic fields. And people usually depict a spin as an arrow up and down are just two different energy levels of this quantum property called spin. Electrons have spin, for instance. The spin that I worked with arises from a crystalline defect in diamond, which is a color center. Color centers are defects that absorb light and then they fluoresce. They are responsible for the colors of those very nice diamonds that you see at the bottom of the slide. So the way that we track in the lab those defects that occur naturally is by putting at room temperature a crappy slab of diamond will do on top of a moving stage, and we move this diamond sample at the same time that we shine a laser at the sample. A laser makes it more efficient and convenient, but it doesn't need to be a laser. So as we're scanning the sample, the moment we hit one of those centers with the laser, the defect is going to absorb the laser light, get excited, and then fluoresce, emit light. And we can track this fluorescence. And this is what it looks like in increasing zooms. In the bottom right of the screen, what you see there is a fluorescence blob that effectively signals the fluorescence of one single spin, which is quite remarkable. But there's something even more remarkable about the fluorescence of this spin, and that's the fact that just by looking at how strongly this blob is fluorescing, you can actually tell if the spin is up or down. This defect has a quantum state dependence fluorescence intensity. I'm going to come back to this fact in a moment. So it can be put to use as very sensitive magnetometer in the following way. There I depict the two different energy levels of this spin. It turns out that they have an energy difference in the microwave range, about 3 gigahertz. And one of those states, the states denoted 0 there, is insensitive to external magnetic fields, whereas the state +1 is sensitive to magnetic fields. That is, in the presence of a magnetic field, state 1 would be shifted a little bit, perturbed by a tiny quantity delta. Via the Zimmerman interaction, this delta is proportional to the strength of a magnetic field. And that's what I'm going to say is important and is a point that is not usually made. Measuring a magnetic field is effectively mapped onto the problem of being able to measure a tiny mismatch or detuning delta from a known energy difference. In this case, the energy difference between the 0 and 1 states in the absence of any magnetic fields. And measuring detunings or mismatch from resonances is something that engineers and physicists have known how to do for many decades. So the big picture here is then to have a tiny little sensor that is capable to measure tiny little magnetic fields caused by a sample, because we can measure the energy shift caused by the presence of an external magnetic field by the sample. So I want you to note that I just described a technological quantum sensor that works at room temperature and in the noisy environment of the crystalline material, and also of, say, the sample under study. So until recently in my life, those were the type of sensors that I was used to dealing with, right? But at some point I realized that many times nature made sensors that outperform humankind-made sensors in crazy, crazy ways. And I'm going to describe one magnetic field sensor that works remarkably similarly to the technological quantum sensor in Diamond. And that's what I really want to be talking about to you today. But in order to do this, we need to start with the biology at the nanoscale, namely the chemistry. So it's been known for decades now in a field called radical chemistry that magnetic fields can alter the final products of a class of chemical reactions that are spin dependent. This means that some chemical reactions, they take different pathways depending on the state of a spin. If the spin is up, the reaction continues through one pathway. If the spin is down, the reaction continues through another pathway. Importantly, the macroscopic final products of this chemical reaction can be different. That is, a spin flipping process that occurs at fast and at the top of a chemical reaction can have macroscopic differences at much longer time scales. And it turns out that magnetic fields can actually alter the probability of us finding the spin up or spin down. That is, external magnetic fields can alter the probability of where the chemical reaction will go. So this has been demonstrated at room temperature, in solution, in the solid state, in the gas phase, and for magnetic fields down to the Earth magnetic field strength. In the beginning of the 80s, and that's where the biology enters, people wanted to understand how birds migrate. It's known, undoubtedly known, that birds, when they migrate, they use, at least as a partial cue, the magnetic field of the Earth, which is weaker than the magnetic field that you sense when you hold your cell phone close to your face. So how do they do this? The hypothesis was that were the same spin-dependent chemical reaction being sustained in living organisms, organisms could sense magnetic fields to the extent that they could sense different physiological concentrations of products coming from these spin-dependent chemical reactions. And in birds, for instance, it was hypothesized, it's still not proven, that maybe chemically the photosensitivity of the vision of birds could be modulated by such spin-dependent chemical reactions, so that birds, when they shift their heads, they could actually see magnetic field lines and know where to migrate. At that point, the only animal protein that was known to sustain spin-sensitive chemical reactions was a flavoprotein that is also a photoreceptor called cryptochrome. Cryptochrome is present in our retina, in the retina of migrating birds, in the antennas of migrating butterflies, but it's also present in all our cells because it has circadian rhythm regulation functions. And it turns out that cryptochrome is very well conserved throughout the tree of life. Okay, all those organisms there, they express cryptochrome, and organisms boxed in red are organisms for which there is at least partial evidence that magnetic field sensing is related to cryptochrome. And yes, humans are right here. So evidence for cryptochrome-based magnetosensing is really, really widespread, but unfortunately at very disconnected length scales. At the very tiny length scales, as you see in the left of your screen, are studies done in cryptochrome in solution that shows that cryptochrome in solution behaves very much like that spin in diamond that I talked about. So in the top left plot, what experimenters did was track the fluorescence, the light emitted by cryptochrome as a function of the time that it was excited with the laser. So cryptochrome can also absorb light and then fluoresce. And that's exactly what the experiments were tracking. The first thing that you see is that the fluorescence goes down. You're killing the chromophore, you're killing the sample. But as the sample was dying, the researchers pulsed a magnetic field on and off. And interestingly, you can see modulations of the fluorescence intensity of cryptochrome as a function following effectively the magnetic field. And this has been repeated many times. Effectively, if you remember, with the spinning diamond, just by looking at how strongly the blob was fluorescing in our computer screen, we could say if the spin was up or down. Here, just by looking at how strongly the spin is fluorescing, you can actually know if the chemical reaction took one pathway or the other pathway, in very good analogy with the spin in diamond. On the other side of the length scales, at the very big length scales, people have done experiments in plates of cells, with birds, with flies, that show that they behave in a way that is consistent with this spin hypothesis, okay? In a way that is consistent with being dependent with cryptochrome. For instance, flies can no longer feel magnetic fields once you knock out the cryptochrome gene. If you put back into the flies human cryptochrome, they're back to being able to sense fields and so forth. There's a lot of evidence, but it's really hard to say, well, the bird is migrating because it has some quantumness in it for a certain time. So that's really the space where we want to be. We want to bridge those length scales. What we're doing in my group is developing apparatuses to do chemical-like, if you will, quantum sensing-like experiments in single cells, in a couple of cells, with the resolution of a single protein. In other words, it's microscopes with coils. But this is not a talk only about birds. There's evidence that the same sort of spin-dependent chemical reactions might be behind many different biological phenomena, especially concerning metabolic regulation, cellular respiration, cell growth, the regulation of reactive oxygen species, the yield of DNA repair. So we think that be nature using those quantum knobs or not, we think that we can manipulate quantum knobs towards driving physiology with many potential applications in healthcare or therapeutics. In the same way, if nature is using quantum for something to sense things in the environment, nature knows a lot how to deal with noise, right? So we think that we can learn with nature strategies to deal with noise, which is what actually plagues quantum computers. It's the loss of quantumness due to noise. And we think that quantum physics or quantum sensing, technological quantum sensing and technological quantum computing could benefit from learning with nature strategies to overcome noise or to be optimized to certain environments. And that's exactly the mission of my group. We want to unambiguously either establish or refute that quantum mechanics is being used by nature, and actually learn with nature and drive those quantum mechanical knobs for something. We're not the only people doing this. There are many groups doing high-tech quantum inspired experiments in biology. It's a field called quantum biology. It's a field that is at the interface of many different things, and I'm not endorsing nature, but I'm endorsing discovery of nature, and I really think that interdisciplinarity is going to drive big questions in science forward in this century. I would like to thank my group members who braved the task of starting a group in the middle of a pandemic in a theme that is sometimes edgy, but that's all I wanted to share with you today, and may the quantum be with you.
Hi, everyone. Okay, so I think you can see Dr. Aiello's email, cla@ucla.edu. So if you have any question, please, I'm sorry, please contact her by email. She's not here herself, unfortunately. So we have about 10 minutes break. And the next talk is at 1:30 by Professor Britton, Plourde, and we'll be back in 10 minutes. Thank you. Hi, Professor Plourde. Oh, hello. Hi.
Hello.
Hi. Would you like to try to share or?
Sure.
Okay, so let me stop my share.
Okay. Let's see. Yes.
Make sure everything is okay. Everything's working. Okay, perfect.
Does that look good?
Yeah, perfect. Yes.
Okay, and let me get a laser pointer here.
Just wait one more minute, please, for
Sure.
Just in case if anybody is still trying to join again.
No problem.
Thank you. I think we have some international attendees who is very late for them. I think they will watch the video that we are recording later.
Sure, that makes sense.
Yeah. Okay, it's my great pleasure to welcome Professor Britton Plourde from Syracuse University. The title of his talk is Protecting Superconducting Qubits from Environmental Poisoning. Okay, Professor Plourde, please.
Okay, super, thanks. So yes, good afternoon, everyone. I'm Britton Plourde, and I appreciate the invitation to speak at this workshop today. I'm going to tell you today about a looming problem for trying to build large-scale processors, quantum processors using superconducting qubits. But I'm also going to show you a recent result from my lab at Syracuse that shows a path forward to trying to mitigate this particular environmental poisoning problem that is looming there as an issue for future quantum error correction. So this is work based in my group here at Syracuse by several grad students and postdocs, and also part of a close collaboration with Robert McDermott's group at the University of Wisconsin-Madison. Okay, so we heard a little bit earlier in Steve Girvin's talk about superconducting qubits. And so, of course, superconducting qubits have seen great progress over the last 2 decades, a little more than 2 decades. Looking back at 1999, when most people would argue the very first superconducting qubit was implemented at NEC in Japan, the coherence time, so the lifetimes of how long a quantum state would persist in these circuits has improved by over 5 orders of magnitude. And so this tremendous progress in the performance of these circuits has enabled really impressive quantum engineering of pretty large scale systems. So highlighting 2 over here, some relatively recent devices from the Google team and from IBM with somewhere in the range of 50 to 100 qubits. And so this has ushered in what's termed by John Preskill, of course, the noisy intermediate scale quantum or NIST era, with lots of exciting developments going on. And there have also been initial steps in these sorts of systems towards implementing quantum error correction. And we heard a little bit about that also in Steve Girvin's talk earlier. Now, to really implement quantum error correction at scale, to really build a fault tolerant system, we need even better gate fidelities than are possible with these current best state-of-the-art qubit coherence times. And we need even more qubits to be able to have all the necessary qubits, the physical qubits, for implementing logical error-corrected qubits. And so that's lots of work, and there's lots of people working hard at those problems. But even with that, if we could implement that quantum error correction, it's very important to note that the quantum error correction schemes that we have can only correct for local uncorrelated errors. So if an error happens at 1 qubit and 1 point in an array, that can be corrected. But if errors happen across the array simultaneously, that's a big problem, and that breaks quantum error correction. And so I'm emphasizing that last point because recently, just in the last year or so, 2 different groups have demonstrated correlated errors occurring in superconducting qubit arrays. And so I'm highlighting these 2 recent results here. One from our collaborators in the McDermott group at Wisconsin, and another one from the Google team, both published just last year. And so what was observed in these experiments is that there are these random energy depositions into the chip from very high energy particle impacts, very, very high energy relative to the qubit energy scales. And we'll come back to that in a little bit. And these come from things like gamma rays emitted from background radioactive contamination in the lab, or even from things like cosmic ray muons raining down on us from above. And when these sorts of high energy particles hit a chip, they generate what's called quasi-particle poisoning. And we'll define what we mean by quasi-particle poisoning a little bit later in the slides. But this quasi-particle poisoning results in simultaneous errors of qubits across the array. And so this is exactly the thing that's problematic for quantum error correction. And it seems to happen. And it happens about roughly once every 10 seconds. So if you're running a quick quantum algorithm and you're not trying to do full-scale error correction, this isn't such a big deal if it finishes in less than 10 seconds. But if you're trying to run a really big calculation and trying to correct for quantum errors, and something that's going to need to run for longer than 10 seconds, and this is potentially a showstopper type of problem. Okay, and I'll come back to discuss some of I'll focus on this Madison correlated error experiment in a little bit in the talk. But before we can do this, let's take a step back and we need to say something about the physics and engineering of superconducting qubits. And so we heard a little bit about this earlier this morning from Steve Girvin, but let me give another take on this, more or less the same thing. But so we could try to make a qubit out of superconducting circuits if we just make a simple LC oscillator. So take a superconducting inductor and some superconducting plates and a low loss dielectric to make a capacitor and make a circuit like this. If we can cool it down to really low temperatures where the thermal energy is less than the energy quantum in this circuit, where this frequency is going to be given by just the natural frequency of this oscillator, then we should be able to resolve these energy levels. But the problem is this will be a perfectly harmonic oscillator. So all these levels will be equally spaced, and we'll never be able to prepare just an ideal Fock state, say of one of these levels. So we wouldn't really be able to make a useful qubit out of this. So to do that, we need some way of adding in anharmonicity. So we need to distort the potential just a little bit from a parabola, so it's no longer a harmonic oscillator. So to add in anharmonicity, the natural way to do that with superconducting circuits is what's called a Josephson tunnel junction. So this can be formed if we take two superconducting electrodes and bring them close together and have them separated by just a thin tunnel barrier, sort of nanometer scale in thickness. And in that case, you can get a tunnel coupling between the two electrodes so that the circuit acts like an inductor, but most importantly, it acts like a nonlinear inductor. So it acts like it has an inductance whose value depends on how much current is going through it. And so that kind of nonlinearity distorts our potential. So instead of having this parabolic potential from this dashed line, it gets distorted. It turns out it's a cosine potential. And that pushes the levels so that now, if we look at the ground state, the transition up to the first excited state is a unique frequency that's different from all the other transitions. So it's very slightly anharmonic, but it's enough to now make the circuit work as a qubit. And so if we can cool it down to a low enough temperature, we can have this ground state be our qubit 0 state. And this first excited state, which typically is roughly 5 or so gigahertz above the ground state, will be our qubit 1 state. And this simple qubit that consists of now just a Josephson junction shunted by a big capacitor is what's called a transmon qubit. It was first developed by the Yale team about 15 or so years ago. And it's one of the kind of the standard workhorse qubit that's used by places like Google and IBM and others, and us for that matter. Okay, so that's how we can make our qubit. But now we need to think about what are the sorts of effects that limit the performance of that qubit. What about decoherence and errors in these circuits? Well, this sort of applies to any qubit, whether we're talking about a superconducting qubit or not, but we can think of errors of our qubit on the Bloch sphere and break them into two different types. We can think of bit flip errors that tend to flip, say, a 1 qubit state down to a 0 state as something that we would call a relaxation type of process, where that involves energy exchange. So this is, in the language of NMR, this would be what's called a T1 type process. Whereas we can also have phase flip errors that would, say, flip a superposition maybe at the plus X point on the Bloch sphere, like a 0 plus 1 state, to the minus X point on the Bloch sphere, or 0 minus 1 superposition. So that's a phase flip error. And in NMR language, that would be a T2 or T2 star type of process. And it's a dephasing type of effect. And now, specific to superconducting qubits, what are the limiting sources that affect these two different types of errors? Well, the relaxation errors, which we're going to mostly focus on today, are caused predominantly by two things. One is dielectric loss. So the materials and interfaces that make up the circuit, losses at the microwave frequencies where the circuits operate can affect this T1 time. But another important piece are non-equilibrium quasi-particles. And dephasing tends to be set by fluctuations in various circuit parameters, and also to some extent can also depend on these non-equilibrium quasi-particles. So this is going to be a key player in this effect I'm going to talk about today for these particle impacts. So let's spend just a slide here talking about what quasi-particles are and what I mean by quasi-particle poisoning. So in a superconductor, in the ground state of the superconductor, the charge is carried by Cooper pairs, which are say pairs of electrons here that sit at zero energy. And here we're plotting the density of states on this axis for single particle excitations as a function of energy on this axis here. And so there's a gap in a superconductor at energy delta, which is of order about 1/10 of a MeV up to about 1 MeV, lowercase m, millielectron volts. And so there can be no single particle excitations below that gap. But now if we have some extra energy input into our superconductor, energy that's above twice this energy gap, that energy could come in the form of, say, a photon, or it could be a phonon, so a lattice vibration. If that energy is above this threshold, then it can break the Cooper pair and make two excitations above this ground state. And these two excitations necessarily have to be above delta. And these excitations are what are called quasi-particles. And so the quasi-particles are now dissipative. They carry entropy when they move around the superconductor. So they're generally a bad thing. And if you have excess quasi-particles in a superconducting qubit, they cause excess loss and they limit T1. They can reduce T1, the lifetime of the qubit excitation. So once we have these quasi-particles, they can scatter and they can lose energy, but they can never get below delta. But if we have two quasi-particles at or above delta come together, they can actually recombine and form a Cooper pair again. And when they do that, they emit a phonon, so a lattice vibration at this energy 2 delta. So they drop down, and just for energy conservation, the system has to spit out this 2 delta phonon. And so, we can ask, where can these pair breaking effects come from? And so these phonon bursts, which is going to be one of our main focus things we'll be talking about today, can come from these high energy particle impacts. So these muon and gamma ray impacts can generate lots of phonons with plenty of energy to break pairs. We can also get photons in our system that can come from things like millimeter wave photons, so terahertz waves coming from black body photons at hotter parts of the fridge. So hotter is relative here. We're talking about things that are maybe at a few tenths of Kelvin or a Kelvin are very hot compared to the qubit. And the black body photons from those carry enough energy to break Cooper pairs. It turns out there's another related mechanism that our collaborators in Madison uncovered very recently, and that is resonant absorption of these black body photons, but now exciting spurious antenna modes of a qubit that can resonate up in the hundreds of gigahertz range. And we recently worked with Robert McDermott's group and published this joint paper here, or at least put this paper on the archive, highlighting this effect. But I'm going to mostly focus today on this phonon absorption mechanism. Okay, so now that we've got that basics out of the way, though, let's come back to this recent experiment from last year in Madison, where they're looking at these correlated errors. And so in this case, they're using an array of qubits. They make the qubits in a particular parameter regime where the qubits become charge sensitive. So these are the qubit energy bands. So the transition from the ground to the first excited state, so from the qubit 0 to the qubit 1 state, now depend on the charge that's coupled to the qubit island in a periodic way. That's periodic in 2 electron charges coupled to this qubit island. And so this allows us to actually use the qubit as an electrometer to sense the local charge environment around the qubit. So it turns out by doing a relatively straightforward pulse sequence on our qubit, while sweeping a bias charge that we can control with an on-chip bias line, and this isn't this is my collaborators in Madison doing this, but we do a very similar thing with our devices here. We can get a periodic type of modulation here, but there's an offset to this that depends on the environmental charge that the qubit is trying to sense. And so by doing this measurement and fitting that offset, it's possible to get a measurement of this, this charge background. And so the Wisconsin team did this, and they did this on this chip that has 4 different qubits on it at different locations relative to each other. And what they see, if they do this offset charge measurement as a function of time over a long time, here's 10 hours, they see a series of these discrete jumps where the offset charge jumps by fractions of an electron charge. And this has been seen before by several different groups around the world. But what's new here in the Madison experiment is they were doing this on 4 different qubits simultaneously. And very interestingly, they can see correlations in these jumps of the charge for qubits that are close to each other. So in this case, the red and purple qubits are these 2 that are separated by a few hundred microns. And you can see lots of the steps happen at the same time. So both qubits are sensing the same charge event. And also the other 2 qubits here, the blue and AQUA one up here, they also sense similar offset charges, jumps at the same time. And going beyond that, what they're able to do in this experiment in Madison is also look at correlations with the T1, so that the relaxation time of the qubits getting degraded. So they could use the 1 qubit as a charge sensor while measuring the lifetime T1, the relaxation time on 2 other qubits. And they could see every time there's a charge jump on one of the qubits, the other 2 qubits see a dip in T1, suddenly gets worse. And it stays bad for something like about 100 microseconds before it recovers. And this is exactly these correlated errors that I was referring to. And a very similar thing was observed in the Google experiment that was also published last year. There are these periodic events, again, once every tens of seconds or so, where the T1 just drops. And that's something that would cause a correlated error between multiple qubits and be fatal to quantum error correction. So what's the physical picture of this? Well, I already described some of it. The idea is there are these very high energy impacts. So coming from things like gamma rays from background radioactive contamination or cosmic ray muons, when one of these particles hits the chip, it deposits a huge amount of energy, something like 100 kilo electron volts, even up to a mega electron volt. This is about 10 orders of magnitude larger than the energy scale for the qubit transition. And it's 8 or 9 orders of magnitude larger than the scale for superconductivity itself. So these are extremely high energy events. And when one of these particles hits a chip, at first it deposits this large amount of energy, and that ends up breaking electron hole, generating lots and lots of electron hole pairs in the silicon and the substrate that the qubits are fabricated on top of. And that turns out to result in these offset charge jumps that are sensed in this recent experiment in Madison. But then these electron hole pairs recombine, and when they recombine, they radiate lots and lots of high energy phonons that are much bigger than the energy gap of the superconductor. And these phonons can propagate throughout the chip. And then whenever they impinge on the superconducting surface, these are side views of a chip here. So the superconducting layer would be this blue feature up at the top. Whenever the high energy phonons hit that surface, they break Cooper pairs in the film and generate quasi-particles. And these quasi-particles are then what cause the poisoning and the reduced T1 relaxation times of the qubits. Okay, so this is the physical picture for this. And so, what could we do about this? So, if we want to mitigate this, okay, one way you could do this is try to shield against these high energy particles. So you could imagine, okay, if we want to shield against cosmic rays, we're going to have to go down deep under the earth, maybe into a mine shaft a mile or 2 below the surface, and use Earth to shield us from cosmic rays. That's not so practical, but maybe it's not completely impossible. But then we'd still have to deal with radioactive contamination in the lab or in the cryostat from emitting the gamma rays that can also cause poisoning. So that's also hard to deal with. So instead, we could try to work on the chip itself, try to make the device impervious to these sorts of radioactive particles. So one approach might be trying to suppress the phonon transport by maybe micromachining, developing voids, or intentionally fabricating voids in the silicon that can scatter phonons. But the approach we're going to focus on involves trying to force the phonons to down convert, to shift to lower energies where they're not damaging, where they can no longer break pairs in the superconductor. And so we're going to do this by using normal metal structures that we're going to put on the back side of the chip. And in the case of these normal metals, we can rely on electron phonon scattering. So if a phonon comes in to the copper, it can have some probability to scatter off of conduction electrons in the copper, scatter inelastically and lose energy, so that it can then when it comes back out into the silicon, not have enough energy when it bounces up and hits the superconducting surface up here on the device layer to break pairs. And now to do this, the initial estimates are that would need a pretty large volume of the copper, something like 10 microns thick. And I'll note that this approach was proposed also just about last year by John Martinez in this article for doing this backside metallization for exactly implementing this phonon down conversion. So this is what we're going to try. And we figured out last year a way to make these very thick copper structures. This is a picture looking at the backside of one of our chips. So this is 10 microns thick copper that we electroplated onto the back of a silicon wafer, and we cut it into these 200 micron on a side islands. And our experiment that I'll be talking about for the remainder of my slides here, we're looking at two different chips that we fabricated. One of them is sort of the control chip, doesn't have anything on the back of it, just bare silicon. And on the top of the chip, it's got our ground plane and it's got our qubits. And then our other chip now has these copper islands on the back. But now, in addition to looking at this phonon generation from say particle impacts like gamma rays, we also incorporate extra Josephson junctions around the perimeter of our chip that we can use as phonon injectors. So we can do a controlled phonon injection if we pulse the voltage bias to these junctions up above their superconducting gap. We can break pairs and generate quasi-particles in these junctions, but those quasi-particles, rapidly recombine. And when they recombine, they emit phonons into the substrate. And those phonons can also bounce over and find their way to our qubit, where they can cause the same sort of poisoning that a gamma ray or a muon would cause in the qubit. But now we have a way to do it controllably. We can't controllably dose muons or gamma rays, but we can controllably pulse these junctions. Okay, and so this is what our chip looks like on the top side of it. So again, the copper is on the back side. Here we're looking at the top. So we've got an array of qubits. We're going to focus on these 3 qubits here. And close up, the qubits look like this. The green colorization highlights the qubit capacitor island. The yellow down here is the Josephson junction. But then out at the perimeter of the chip, we have these different injector junctions. And so on the chip that has copper on the back side of it, it's got its injector junction over here, and it highlighted in blue. And the chip that has no copper on the back has its injector junction out here, highlighted in red. And the injector junction looks like this. It's got 2 pads. We can bias it up and inject phonons from that mechanism. Okay, and so our first type of experiment we can look at is this sort of pump probe experiment where we pulse the bias to this injector junction that's on the chip, and we can measure the change in the relaxation rate of the qubit. So we can measure the qubit's T1, this inelastic relaxation lifetime, and we can first measure it with no injection, so to get a baseline level, and we can subtract the T1, the inverse T1 that we measure with a particular injection pulse, and subtract off this baseline relaxation level. And that's what we're plotting on these 2 graphs down here, is this change in the qubit relaxation level. And this measurement on the left side of the plot, we're making a pulse to the qubit. It turns out we're pulsing it at 1 millivolt for 10 microseconds. And so that 1 millivolt is large enough to be well beyond the superconducting gap of the Josephson junction to be able to break pairs, make quasi-particles that recombine and emit phonons. And then we vary the delay time until the point where we measure T1 of the qubit. And what we see here is this relaxation rate goes up. And on this way of plotting it, up is bad. So up means a larger relaxation rate or a shorter T1. So the qubit its coherence is getting worse and worse. And it gets worse and worse over a time scale of about 30 microseconds before it reaches a maximum. And this time scale, this 30 microseconds, is just about what we would expect for the characteristic time for phonons to propagate. Let me go back to the previous slide for a second. From the injector junction, say here, to a qubit over here. So that's about the right time scale, considering the speed of sound and the properties of the phonon propagation. And so that burst of phonons we injected here reaches a maximum at this point. And then over this time scale of about 60 microseconds, those phonons eventually find their way out of the chip, and they leak out into the holder that the substrate is mounted into, and the chip cools back off and returns to its baseline level. So the scheme that I'm using throughout for colorization here, red corresponds to the chip that does not have these copper reservoirs on it, and blue corresponds to the chip that does have the copper reservoirs. So we could see the chip without copper sees this big degradation or big enhancement in the relaxation rate when we inject phonons, whereas the chip that has copper barely registers a change. It's down at very low level. And so there's a factor of it's over 35 times difference here in this enhancement of the relaxation rate. Now we can do a related experiment if we fix this delay time at this peak value of 30 microseconds. And now if we vary the amplitude of this injection pulse, that's going to change the number of phonons that we're injecting per pulse into the chip. And so if we look at the red data, which again is the chip with no copper, so no phonon down converting structures, we see that when this bias gets above this point here, about 0.4 millivolts, which is the energy gap for the aluminum junction that we're using to inject, suddenly this relaxation rate rises, and then it keeps increasing as we go further. Now, if we look at the same measurement for the chip with copper, we see it rises more gradually, but then it reaches a peak at about 0.56 millivolts, it turns out, and then comes back down, and it's almost 2 orders of magnitude lower out here than the chip chip without the copper, chip with the copper. And now this peak, we actually can understand as not being a phonon-mediated poisoning, but this is actually due to the fact that these Josephson junctions, when we bias them up to inject phonons, they also generate what's called Josephson radiation. So they radiate electromagnetic radiation, just like an antenna, but narrow band radiation that's at the Josephson frequency, which depends on the voltage that we're biasing and a constant called the magnetic flux quantum. And so this peak here at 0.56 millivolts corresponds to a frequency of 270 gigahertz, so pretty high frequency. And this turns out to match very well with our modeling of this spurious antenna resonance that I mentioned earlier, where a qubit can resonantly absorb this electromagnetic radiation. So this is now photon-based poisoning, photon-mediated poisoning, as opposed to the phonon-mediated poisoning we're looking at here. Okay, so besides looking at changes on the relaxation time, we can also look at this quasi-particle poisoning directly in the time domain. So it turns out there's, with these charge-sensitive qubits, which the Madison group used earlier for their correlated error experiment, and that we use here for our measurements now, it turns out there's a pretty straightforward pulse sequence we can use to map the parity of the qubit, whether or not there's even number of quasi-particles or an odd number of quasi-particles on the qubit island. We can map that onto the qubit one-state population. And we can just do that repeatedly and measure the characteristic timescale for the quasi-particles to switch. And we can see that for the chip, the red chip without the copper, it's actually a pretty low rate. This is about the state of the art in the world right now, a little better than 1 per second. And our chip with the copper is even an order of magnitude better. So our copper, we can already see here, we could see it on the previous slide and we can see it here. It's doing a really important job of reducing this poisoning rate. But we can actually go in and look directly in the time domain at these quasi-particle parity switches. If we bring back the Josephson junction now, these injector junctions, and now we do a pulsed injection. So we pulse this injection junction to inject phonons into the chip, and we do this periodically. So we do it at a frequency of 20 hertz. And then in between these injections, we repeatedly measure parity on the qubits. And we can now get time traces of this quasi-particle parity switching back and forth. And we can do that as a function of the width of these injection pulses. So how many phonons we're injecting. And so on this plot up here, we're looking at the probability for this parity to switch as a function of effectively the number of phonons that we're injecting. And we can see for the chip without the copper reservoirs, this rises a lot more quickly than it does for the chip with the copper reservoirs. And so it takes about a 20 times larger pulse, so 20 times more phonons to get the same switching probability levels. So this tells us that our copper reservoirs are very effective. They're down converting at least 95% of these injected phonons that we're putting into our chip. And so we can now use this to not bias the junction and not inject phonons, but we can now just try to look at background events. It's just a slow process because these are fairly rare. So we have to run the experiment for a day or even a few days. And this shows a short snippet of just about a minute worth of data. We can measure the 3 qubits on one of the chips simultaneously and look at these kind of switching events. And we can look for correlations where, say, in this case, the dashed lines highlight 2 qubits switching their parity at the same time, or the dotted line over here shows 3 qubits switching their parity at the same time. So those are correlated errors. And what we can do is we can compare then these correlated error rates between the chip with the copper in blue and the chip without the copper in red. And what we can see, this middle section here highlights twofold correlated errors. And so the chip without the copper, we see pretty high rates of these twofold correlated errors and even threefold correlated errors. But with the copper, these correlated errors are down, both twofold and threefold are down by 2 orders of magnitude below what we measure without the copper. So adding on these normal metal reservoirs does a really effective job of greatly reducing these phonons and the poisoning, quasi-particle poisoning that they can cause. And it turns out we can use these measured rates here of twofold correlated errors to show that with this mitigation strategy, we've already been able to beat down this rate of, the probability here of correlated 2-qubit errors to below the level that would be necessary for doing surface code quantum error correction. So since time is basically out, let me wrap up here. So I've told you today about this problem that's out there for near-term, large-scale quantum processors based on superconducting qubits coming from high-energy particle impacts, so from things like cosmic rays and gamma rays. But I've shown you a strategy that already in our initial implementation works really pretty well for down converting these high-energy phonons and making it so that these sorts of large-scale qubit arrays can operate in the presence of these high-energy particle impacts, but at a level of correlated errors that's down to the point where it's still possible to do quantum error correction. And so, we're still looking into, are there ways we could do even better? Could we get even better down conversion with a different metal besides copper? Could we also add in this micro machining of the silicon to scatter phonons? And can we also change around the structure of the superconductor on the device side of the chip to try to also deal with the quasi-particles themselves in the qubit regions? So I will stop there and take questions if there are any. Thank you.
Thank you, Professor Plourde. That's really great. I think I have one question here. Any experiment to use high temperature superconductors to replace current aluminum copper superconductors?
That's a good question. So it depends what you mean by high temperature superconductors. But if you're referring to the copper oxide, like YBCO, for example, those sorts of materials with very high transition temperatures. So YBCO is, I believe, 90 Kelvin. That is not really practical for making qubits. There have been some ideas that were pursued long ago to try to do this, but the main problem there is these very high temperature superconductors from the copper oxides have a more exotic pairing mechanism for the Cooper pairs, and the structure of the superconducting gap is no longer basically it's a rather than an S wave pairing symmetry, it's a D wave pairing symmetry that has nodes in the superconducting gap. So these quasi-particles that we talked about before actually extend down to 0 energy along certain directions in momentum space. And so that's sort of poison, or that's kind of death for making a qubit out of those. Now there are other superconductors that are not that high TC, but that are higher TC than aluminum. Things like even niobium, which has a TC of about 9 Kelvin. Aluminum that we're using here is 1 Kelvin. Niobium nitride has a TC of about 16 Kelvin. So those would be attractive to make qubits out of. The problem is there's no really great technology to make sufficiently small tunnel junctions with very low dielectric loss with those superconductors. But even if that were possible, the qubits themselves would still need to operate at very low temperatures if they're going to have their transition frequencies at 5 gigahertz, if nothing else, just to thermalize the qubits into the ground state. So it's a good question, but at the moment, yeah, aluminum is still king for making qubit junctions, and current qubits, superconducting qubits moving forward will be operated at the bottom of dilution refrigerators.
Neil, you have a question?
I do, but since I've asked several questions already today, I'm going to suggest maybe anybody else that's asked a question should go ahead of me.
There are some questions in the chat. One that I missed, what type of practical quantum computer do you think we will be receiving in 2023? That I missed. It was from the earlier, if you would like to answer that.
Well, yeah, I'm not sure. So I work in an academic research lab. So we typically work on experiments like the one I showed you today with a few qubits. I don't have the resources, and there aren't very many academic research labs that have the resources to build a large scale quantum processor. So I think that's a question for someone, say at IBM or Google or some other large industrial labs. But I mean, if you look at the roadmaps, they're sort of at close to 100 qubits now, and I think they're projecting a few hundred in the next couple of years. And yeah, they have very ambitious goals, but they have a lot of people working very hard at these problems.
Thank you. And the next question, if all this work at hardware level, do we still do error correction for single qubit at software application level?
Well, right. So it's a question of when do you need to start doing error correction? And so, I mentioned that over the past several years, people have made the initial steps towards quantum error correction, but there are no fully error corrected quantum computers right now. I mean, that's still probably at least several years away before the gate fidelities have to get even better than they are now. And we need even larger arrays of qubits than we have now. So at the moment, there are still near-term uses sort of in this NIST era that we're in now, where you don't need error correction. So if you can run your computation in the timescale less than when your errors start to accumulate and your quantum information becomes completely scrambled, then you could still get some mileage out of doing that without having quantum error correction. And so I think one of the keys is identifying what are those near-term problems that are interesting, where you don't need full-fledged quantum error correction.
Thank you. And the next, so the cosmic particles can penetrate the radiation shield of the fridge is the question mark.
Yes. So cosmic rays, so muons are raining down on us all the time from the upper atmosphere. Yeah, my lab is actually in the second basement of our building here at Syracuse University. So not only do the muons not just get into our cryostat, but they also get through 2 floors underground. So you really have to go much deeper underground if you want to get away from the muons. It turns out if you look at the Madison paper from Robert McDermott's group from last year on the correlated errors, they do a very careful analysis working with some particle physicists who specialize in dark matter detection, analyzing these. And it turns out the muons are actually a smaller problem. The gamma rays turn out to be a bigger problem. So gamma rays from background radioactive contamination.
Thank you. And Neil, would you like to ask a question?
Sure, thank you. This is really nice work. I have 2 related questions. The first one is real simple. By phonon down conversion, you mean you're thermalizing these hot phonons, essentially? Is that correct?
That's right. So we're trying to, we have these phonons at very high energies, many orders of magnitude above the superconducting gap. We want them to interact with conduction electrons in the copper, scatter inelastically, heat up the copper, so those electrons get hot, and then the phonons come back out at a much lower energy.
Right, so essentially they come out at the thermal energy, is that correct?
Whether or not you call it thermal I'm not sure if it's quite correct to call it a thermal distribution, but we do want to cool the phonons off. That they're giving off their energy to heating up this copper, which then can itself cool off slowly by radiating out into whatever the chip is mounted on.
Okay, so maybe I'll pursue this a little more. Do you have an estimate for the energy of the phonons as they're coming back out of the copper?
We don't yet. So this is actually sort of the next phase of our project is actually to start to model those phonon dynamics. We can show empirically now that I think our pump probe measurements where we can inject phonons from the tunnel junctions on the side of the chip and have those phonons propagate over and poison the qubits. If we do that without the copper and then with the copper, we can show that we absorb, almost all, 95% of the phonons. But what their exact energy distribution is, we can't say right now. We know that it's the vast majority of the phonons when we have the copper on are getting down converted below the superconducting gap. But beyond that, we can't say.
Right, okay. And then my second question is, without this copper film, have you done any estimate, given how far the energy can propagate sideways in your sort of 100 microsecond time scale? what would you expect just the temperature rise of your solid piece of silicon to be if you're getting a 1 mega eV photon coming in?
Right. Yeah, so that's a good question. And I don't have a number for you. I mean, it's a little hard to come up with an actual temperature because it's all, the dynamics is very fast, right? This particle comes in, generates this huge number of electron hole pairs. And there's also some interesting subtleties to that process that are spelled out really nicely in the Wisconsin paper from last year, where because of the different electron and hole dynamics, that's what leads to these charge offsets that are observed in that Madison experiment. That we also see these same charge jumps. Yeah, so what exactly the temperature of the silicon is, I can't say offhand. I'll also point you though to a nice analysis in this theory paper that John Martinez published last year, which kind of motivated our work, where he proposed this idea of using thick copper islands to down convert the phonons, where he goes through and just thinks through the different stages of it. I think he calls this first phase the fireball stage, where the particle first hits the chip and you generate this large burst of electron hole pairs. But yeah, we do know that the time scale for the phonons to get out of the chip and the chip to effectively cool back down to sort of its baseline level is about 100 microseconds. And that's consistent with the time scale you'd expect for these phonons to just couple out of the places where the chip is anchored around its perimeter to the sample holder that's then itself, bolted onto the cold plate of the fridge.
Okay.
Thank you. The next question, has your group done experiments in deep underground sites like the bottom of a mine to measure cosmic ground radiation effects?
We have not, but I do know that there are some efforts underway from some other groups. There have been some experiments in Europe, in Italy at the Gran Sasso lab, which is, I think it's an old mine. It's deep under a mountain in Italy. There's also some experiments going on, I know, at Fermilab, where they have a deep underground site that's a mile or two below the earth. In both places, they have dilution refrigerators that are operating underground. And so they're able to study how things change with superconducting, whether it's qubits or just superconducting resonators, when you can take away this at least the cosmic ray component. You don't necessarily take away the radioactive contamination. That's a separate topic.
The next question from Abdul Ali. Why not using high TC superconductor for quantum computing?
Well, I guess this was a similar question to before, but maybe, so again, high TC superconductors, like say copper oxide superconductors, are problematic for qubits because they don't have a full gap in all directions of momentum space. So the gap goes to 0 in certain directions, and that means you have quasi-particles all the way down to 0 energy. So you can't really build a practical qubit out of them.
Another question by Ron. I understand that work at Washington State PNNL have done some work in this area. Have you connected with them?
I have talked with folks at PNNL in the past, but not about this particular problem. So I guess maybe I should learn more about what they're doing too.
Okay, I think that's all the questions. Any other question? If not, okay, thank you so much.
Thank you.
Plourde, really amazing talk and very interesting work. It looks,
thank you.
For somebody who is not a physicist, really difficult work you are doing. Amazing work. Thank you for this great presentation.
All right, thanks for the invitation.
Okay, so the next talk will be at 2:30. We have about 20 minutes break. Let me share. Again, before I share, I think I can pause the recording. Okay, it's my great pleasure to welcome Dr. Alexey Gorshkov from University of Maryland. The talk is on quantum sensor networks.
Thank you very much, Farbod, for the invitation, and thanks for everyone for attending. And I should say that I'm from NIST and the University of Maryland, so I have these two affiliations. So I will talk today about quantum sensor networks. So quantum sensors are sensors that use that harness quantum mechanics for sensing. And because quantum sensors can be very small, they can be used to achieve high spatial resolution. But at the same time, because all measurements are fundamentally limited by the laws of quantum mechanics, quantum sensors can also be used to achieve high precision in sensing. So one example that you've already heard about in a talk by Clarice earlier is the nitrogen vacancy or NV center defect in diamond, which you can think of as an electronic spin whose energy level splitting is sensitive to magnetic fields at temperature. And as a result, these NV centers can be used for magnetometry and thermometry. And in particular, they've been used for magnetic imaging of live bacteria, for example, and for nanoscale thermometry of live human cells. Another example is a Rydberg atom, which is a highly excited atom where the negatively charged outer electron is far away from the positively charged core. And as a result, you have this large electric dipole moment, which makes Rydberg atoms very sensitive to electric fields and make them into excellent electrometers. So how does a quantum sensor work? So this is the simplest situation where your quantum sensor is a two-level quantum system with levels 0 and 1, whereas 0 is kind of one of the basis vectors in your two-dimensional Hilbert space, and 1 is the other basis vector. And then you assume that your Hamiltonian is just the 1/2 theta z, where z is the Z Pauli matrix. And then you see that with this Hamiltonian, it is diagonal in the states 0 and 1. And furthermore, states 0 and 1 are just split by energy difference theta. So one of them is at 1/2 theta and the other one is at -1/2 theta. So theta is the energy difference between 0 and 1, and you're interested in measuring this energy difference. So the way you do this is you prepare the state psi, which is 0 + 1. And then you let the state evolve under the Hamiltonian. As a result, the states 0 and 1 pick up a relative phase, theta t. And then you can measure this relative phase just by measuring the Pauli matrix X. And I'm going to skip the derivation, but what you find is that as a result, you can measure theta with a measurement uncertainty delta theta, which is 1/t. And this 1/t makes sense because if you, for example, double your time, then you need a half as big of a change in theta to get the same effect. So that's why it's 1/t. So this is just a single qubit and a single parameter. Now let's suppose we have n sensors. And let's suppose all n of these sensors, or n qubits, are coupled to the same parameter theta. One possibility then is to use these sensors, these qubits, independently. So you just have n copies of the experiment from the previous slide, and you prepare every qubit in the state 0 + 1, and then evolve under this Hamiltonian. And since you just have n copies of the same experiment, your uncertainty decreases by the statistical factor 1/√n. And this is called the standard quantum limit. On the other hand, you could instead entangle your qubits and prepare the state 0, 0, 0 + 1, 1, 1, which is called the GHZ state. You see that these two states are actually eigenstates of this Hamiltonian and are separated by the energy m theta. So when you evolve under this Hamiltonian up to an overall phase, you get this state where the two states pick up a relative phase n theta t relative to each other. And so it's like a two-level system, except instead of having theta t, you have an n theta t. So it means that the uncertainty you get is now, instead of 1/t, it's 1/nt. And turns out to get this uncertainty, it's sufficient to measure the Pauli X operator on all the qubits. The reason why you get this improvement from 1/√n to 1/n when you make use of entanglement is because contributions to quantum noise from each sensor in some sense conspire to partially cancel each other out. And this is called the Heisenberg limit. And this is the best possible measurement that's allowed in quantum mechanics. Okay, so now let's talk about a quantum sensor network. So now we assume that each of our qubits I is coupled to a different parameter theta I with the same theta Z coupling. And now let's suppose that instead of being interested in every single theta, we're interested in measuring a desired linear combination of these fields theta I. And let's suppose that this linear combination is alpha 1 theta 1 plus alpha 2 theta 2, etc. And we call it Q. So here's a cartoon where we suppose we have 4 sensors. And at each sensor, there is a field theta I, which is unknown. And there is a weight alpha I, which is known because we pick that weight. And for simplicity, I will assume that these weights are real, although it's easy to generalize to complex weights as well. And then the idea would be to use these different weights to target the spatial profile of the sort of desired signal you're interested in, sort of the property of the field theta that you're interested in, such as, for example, the Fourier mode or a spherical harmonic. So, for example, you might be interested in a signal that has higher weight on the right side of the cell than on the left side, or in a signal that has higher weight in the periphery of the cell compared to the center. So back, in 2018, so we solved this optimization problem, and we found the optimal protocol for measuring this linear combination Q. And it turns out that the optimal protocol also starts with the same GHZ state as we use for the case where all, where all thetas are equal, and we're just interested in measuring that one theta. Except now, as we evolve this GHZ state under this Hamiltonian, we sometimes apply single qubit pulses to dial in these weights alpha. So in some sense, we can decouple or refocus those qubits for which alpha is small, such that we're less sensitive to the corresponding theta. So I'm not going to go through details, but this is roughly how it works, and we get the optimal measurement. So now let's try generalizing this. Suppose instead of measuring just the linear combination, you want to measure any desired analytic function Q of these thetas, theta 1, etc., theta n. So we also solved this problem, and we found the optimal protocol, which actually is very simple. So the protocol has 2 steps. So first, you measure individual theta I without using entanglement for negligible fraction of time to get estimates that we call theta I tilde. Then we linearize our desired function Q around the estimates theta I tilde. So that is, we first write that Q evaluated at a theta I tilde plus the linear Taylor series expansion. And then we drop higher order terms. If we drop the higher order terms, this new expression is linear in theta, and we can just use our linear combination protocol that I discussed before to measure this linear combination. And then we add this linear combination measurement to to the part of this that doesn't depend on the theta I, and we get an estimate for Q. And now the trick is to prove that the terms that we neglected here, the higher order terms in theta I minus theta I tilde, they don't dominate the uncertainty, and they're negligible. And indeed, we show that if we choose this negligible fraction of time sufficiently wisely, this is indeed negligible, and we get the optimal solution. So let's now generalize this a little bit more. Let's generalize this to what I call a parametrized field. So far, every qubit was coupled to its own kind of unknown field theta I, and we wanted to measure a function of these theta I's. So now let's generalize as follows. Suppose we have a vector k, vector of k unknown parameters theta 1 through theta k, But now let's suppose that these thetas don't couple to the qubits themselves, but there are some other functions fi of theta that couple to these qubits. So the fields are parametrized by the parameters theta. And then we want to measure some function again of these thetas. We assume that the function q is given, and we also assume that these functions fi are given. So the unknowns are only the thetas. Furthermore, we assume that we have enough sensors to measure the thetas in principle. So forget about entanglement. Suppose we just use an unentangled protocol to measure each fi individually. So then we assume that we have enough information to kind of invert this problem and solve for the thetas, and then plug it in and compute q. So in principle, we have enough information. So the question is, how do we do this in the fastest possible way using entanglement? So what this assumption of enough sensors means, it essentially means that d, the number of sensors, is greater than or equal than the number of parameters theta I, because then there are sort of enough equations to solve for theta in terms of the f's. And the problem we're facing here is if there are many sensors, we can't really directly use our earlier results, since there are infinitely many ways to express q in terms of f's. There's only one way to express q in terms of thetas, but infinitely many ways to express q in terms of f's. And our previous protocols, they worked in terms of f's. So we need to solve this problem. So let me motivate this problem a little bit better. Suppose we have this rectangle, and inside this rectangle, we have unit electric charges, which I will label by J, that sit at unknown coordinates Rj. So here's one that sits at coordinate R1, and another one that sits at coordinates R2. So R1 has an X and Y coordinate, and R2 has an X and Y coordinate. So then our theta, these parameters are R1 and R2, or more precisely kind of R1, X1 and Y1, and X2 and Y2. So there are 4 of these parameters, X and Y positions of the 2 charges. And now let's suppose that Fi's, the things that we can sense, are Z components, so out of the plane, for example, of the electric field at a given sensor, which I will label by I. So for example, there'll be one sensor right here, whose Z component of the electric field is a F1, then F2 right here, and they all depend, of course, on the positions of these charges. And let's suppose there are 3 more sensors that sit right here. And let's suppose I'm interested in measuring Q, which is the Z component of the electric field at some position labeled by star. But I cannot put a sensor there because that's inside the rectangle, and let's suppose I cannot put sensors inside the rectangle. So I want to use the information at the sensors that I do have access to kind of figure out what these locations of these charges are and understand and learn what the value of the field is at a position without the sensor. So the problem that I have is the number of sensors that I have is 5 here, and the number of parameters that I don't know is 4. So it's the X and Y coordinates of the 2 sensors. And in this case, if I have these many sensors, there are infinitely many ways to express this quantity Q in terms of the Fi. So I don't know how to use my previous protocols. So this is the problem. So now let me simplify it even further and present you sort of with a toy example where you can see how this problem arises and how it's solved. Suppose I have just 2 unknown parameters, theta 1 and theta 2. You can think of them as the coordinates of those charges, for example, in this previous example, but now let's suppose there are just 2 unknowns, theta 1 and theta 2. And let's suppose that the field amplitudes at the 3 sensors are F1 is equal to theta 1, F2 is equal to theta 2, and F3 is theta 1 plus theta 2. And suppose I want to measure the function Q of theta 1 and theta 2, that's just theta 1. So I just want to know only theta 1, and I have these 3 sensors that are coupled to theta 1, theta 2, and theta 1 plus theta 2. So let's consider 2 strategies. So strategy 1, I don't use entanglement. I measure F1, F2, and F3 separately, and I want to extract from this the value of theta1. So the way to extract the value of theta1 is I can compute this linear combination of F1, F3, and F2 for any A that's not equal to -1. So it turns out for any A that's not equal to -1, this expression, if you plug in here F1, F2, and F3, this expression is equal exactly to theta1. So any A here works if it's not -1. And then you do a little bit of optimization and you find that without entanglement, the optimal A is 1/2. And the uncertainty in the measurement of Q is 0.8 over T. Now let's consider the second strategy. So we have the same linear combination, but now let me call this B. And now we use entanglement to measure this linear combination. And I know how to measure linear combinations. I told you about this in earlier slides. And I do now the analysis and I check what is optimal. Turns out now the optimal coefficient with entanglement is not 1/2, it's actually 1. And the resulting uncertainty is 0.5 T. So you see that by using entanglement, we were able to reduce our uncertainty from 0.8 T to 0.5 T. So more generally, so this is just an example, but more generally, we found the optimal strategy for any linear functions Fi and Q of thetas. We proved that this is the best strategy allowed by quantum mechanics. And we generalized it to any analytic functions Fi and Q just by using the same trick of first measuring the thetas approximately and then linearizing around these approximations. So let me again mention a few examples. So again, the problem that we solve is that we have a vector of k unknown parameters, theta1 through theta k. They determine this fields Fi that couple to the sensors, and we want to measure the function Q of theta. So this is the example that we had of these charges at positions R1 and R2. The unknown parameters are the theta, and we have sensors at some positions outside of the box whose fields are determined by these charges. And example that I presented earlier is that I wanted to know the value of the field at some other position without a sensor. Now, another example could be that this function Q could, instead of being the value of the field at some sensor, at some position, excuse me, it could be, for example, an integral of the field over some region, or it can be some other much more complicated property of the field created by these charges. So another example, in addition to these kind of electric charges and electric fields, could be the example of nuclear spins that are sitting at unknown positions and possibly have unknown magnetic dipole moments, and they're producing magnetic fields. And then we can use magnetic field sensors to sense this magnetic field, determine the positions of these charges, and in an optimal way compute the magnetic field at some unknown point, or perhaps some integral of the magnetic field over some region. So all of these things can be solved, using this solution. So so far, the problem that we solved, actually, all of the solutions that we had, they use the maximally entangled states. So let's get back to this simple problem where we have parameters theta I that are coupled to qubits through this theta I Zi coupling, and we're interested in measuring a linear combination. So forget about all these parameterized fields, forget about analytic functions, just back to the simplest problem. So the protocols that we have, or most of them, as long as all of these coefficients alpha are non-zero, they actually start with a fully entangled, sort of not maximally entangled, but a state where all n qubits are entangled. And so the question is, do we always have to use these states where all n qubits are entangled? Can we consider states where entanglement is where fewer qubits are entangled and still get the optimum? And this would be useful because highly entangled states are hard to create and they decohere fast. Yeah, so can we achieve the same optimal measurement by entangling fewer qubits? And the answer turns out to be yes. I mean, not always, but for some values of alpha, the answer turns out to be yes. And the key to finding this protocol, so we describe it in this paper, is to divide your time in fractions Pn, where sum of the fractions is 1. And then instead of using the same state throughout all of your time, you use different states. Instead of this GHG state, you use different states during each fraction of time Pn. And if you do that, it turns out that these states in general don't have to all be n qubit entangled. And to be more specific, we find the following, that if your coefficients alpha satisfy the following inequality, so here it's the sum of the absolute values of the alpha I is less than or equal to some integer k times the largest value of the alphas, then you can achieve optimal measurement with at most k-partite entanglement. So let's digest this. So let's consider the situation where alpha 1 is equal to 1, but all the other alphas are 0. So it means that we're only interested in measuring theta 1, and we're completely uninterested in all the other alphas, thetas, excuse me. So in that case, the sum of the absolute values is 1, because alpha 1 is 1 and the rest are zeros. The largest alpha is also 1. So this inequality is satisfied for k equals 1. So it means we can achieve the optimal measurement with at most one partite entanglement. So it means no entanglement. And this, of course, makes sense, because if we're only interested in measuring theta 1, then we could just use a qubit 1 to measure that theta. Now let's consider the opposite extreme, where all the alphas are equal. So we want to equal to 1, and we want to measure the sum of these thetas. So in that case, the sum of the absolute values of alpha I is n, and the largest alpha is 1. So we need k equal to n to satisfy this inequality. So this means that if we're interested in measuring this uniform linear combination, we actually need the full n-partite entanglement to achieve this. And so what this formula says is that more generally, the more uneven your distribution of alphas is, the smaller is the k in k-partite entanglement that you can use to achieve the optimal. But if it's uniform, it has to be n-partite entanglement. And finally, before I close, just the last thing. So far, we discussed that measuring a single function, but let's suppose you want to simultaneously measure multiple functions. So again, let's suppose the theta i's are coupled to zi's like this, and we want to measure not one linear combination, but simultaneously m different linear combinations, q1 through qm. And the goal in this case is to minimize the sum of the variances of the m estimators of these quantities qm. Let's consider the following three example strategies. So the first strategy is just the local entanglement-free protocol, where I measure each theta I independently, and then I just compute the qi. Another strategy is I divide my time into m blocks and use the first block to measure q1 using the optimal linear combination protocol, use the second block to measure q2, and use the mth block to measure qm. And then I optimize over how I split my time in blocks. And finally, a third strategy where I also do a sequential measurement of linear combinations, but now instead of measuring these linear combinations, I measure some other optimally chosen linear combinations and compute the linear combinations I'm interested in from the ones that I measured. And what we find is that actually, in many cases, this third strategy works best. It works better than these other strategies, especially when the number of sensors is large. And just briefly to mention the applications of these sensor networks. So you can imagine applying them at small scales or at large scales. So at small scales, it could be the scale of a single molecule or a cell or a human, where you can imagine applications in chemistry, biology, and medicine, where you could measure magnetic fields, electric fields, and temperature. Or you can imagine applications on the scale of the entire globe, where you would need a sort of a large sensor network to connect these sensors together and entangle them. And then you can imagine potentially applications in geodesy and geophysics, where you could measure magnetic fields, electric fields, gravitational fields, or temperature. So to summarize, we found often optimal entanglement-based protocols for measuring one or more properties of spatially varying fields. As an outlook, it'll be interesting to consider optimal sensor placement. So for now, we just assume the sensors are fixed. To marry our ideas with error correction, and to some degree, this has already been done. To consider the case where the generators, which in this case were Z1, Z2, et cetera, they were all commuting. But what if we consider non-commuting generators, such as, for example, in vector magnetometry, where you have one field is coupling to, say, a Z1, and the other field is coupling to X1. So they couple to two different Pauli matrices on the same qubit. It'll be also interesting to measure properties of time-dependent, such as stochastic fields, to allow for the movement of sensors during measurement, to invent protocols where the measurements will be verified or possibly encrypted, such as the server that owns the sensors cannot figure out what we're measuring and what the answer is. And I should mention finally that the same ideas apply not just to qubits, but also to photons or phonons that are used as sensors, where the parameters theta can couple to, say, A dagger A or A plus A dagger. So with this, let me thank my numerous collaborators and the funding agencies. Let me thank my current and past group members, and thank you for your attention.
Thank you very much for this great presentation. So one question is from Aditya. Please go ahead, Dr. Sharma.
Hi, thanks for the talk. I was wondering, several slides back, you mentioned the advantage of the entangled measurement over the unentangled one.
Yeah. So
how does that, how does it scale if you have like more detectors?
So let's see. So it doesn't, let's see. I think it's basically, let's see. Yeah, so if the number of sensors and the number of detectors is about the same, then it's the same thing basically. And especially if you're, you know, if the things you're interested in are kind of sort of uniform. I mean, if we just go back to the linear combination protocol, I mean, it's the same thing. It's if you're interested in measuring a single quantity, we know that we go from 1/√n to 1/n. So similarly, if you're interested in measuring a linear combination, and this linear combination is sufficiently, you know, uniform, then it's the same thing. You get an improvement from roughly, you know, 1/√n to 1/n. Now, if you're asking about this parameterized problem, where I have n sensors, but I have sorry, I have I have d sensors and k parameters. I believe the improvement is still kind of the same. It depends on the number of sensors. So if the thing you're interested in is sufficiently uniform, I mean, in some sense, then you basically get an improvement from 1/√d to 1/d. But of course, it depends on what problem you're, like what question you're asking. If the question you're asking happens to depend only on the thing that couples to one of the sensors, then, you know, the other sensors are useless and you get no improvement. Yeah, thanks. Great question.
Thank you. Any other question? I have one question if there's no other question. I actually got very excited about this presentation because I think I can find a link between what we would like to do in terms of communication between multiple drones. So basically each drone has a detector and then they're communicating by, it can be basically, it's kind of a quantum key distribution using mobile platforms. Basically, it can be a ground platform or a UAV type. I feel that this can be very relevant, and I think I need to learn more about your work. But if you haven't,
right. So in your case, it's more about communication, right, than about sensing. So you're thinking of using maybe these sensing ideas,
yes,
to do better communication
between multiple agents or robotic agents.
Right, right. Yeah. So that's I mean, if you're trying to do classical communication, then maybe these ideas are useful because these parameters are classical. But if you're trying to do quantum communication, then it's a little bit different because you know, the parameters I have here are kind of classical. So like you're sensing quantum states. It's a little bit of different. But yeah, I can imagine that there are interplays here. I mean, feel free to send me an email, and
definitely,
it'd be great to find some connections. Yeah,
I would like to learn more about it. I think there is a kind of a link here, which is, for example, let's say quantum teleportation, but can be used for sensing on a moving platform that is like a multi-agent kind of robotic platforms and so on. So I think me and Dr. Quadrelli will read more and then we'll contact you about that.
Sure, I'd be happy to chat more, brainstorm. Yeah, I mean, that's great.
Yeah, I think
that's awesome.
Interesting potential here. Thank you so much.
Thank you. Thank you.
Gorshkov. This is really interesting. I really appreciate your presentation.
Thank you.
Okay. Next, we have Dr. Joshua Bienfang from National Institute of Standard and Technology. The title of the talk is Single Photon Detection Systems for Advanced Photon Counting. Thank you very much, Dr. Bienfang. I really appreciate your time and your presentation. Please share your presentation.
Okay. Are you seeing my presentation?
Not yet.
How about now?
Yes.
Okay, and you see my cursor, my mouse?
Yes.
All right, great. So yeah, thanks for inviting me. I'm going to be giving by far the most engineering talk of this quantum engineering workshop. And this is a compendium of work, and I'm just going to make one point to the audience, and I hope by the end of this talk you'll be convinced of it. But I have very helpful collaborators in Alessandro Rostelli and my group supervisor, Alan Migdal, and as well as members of Carl Bergen's group at MIT. And this is some work that's been funded by DARPA and NIST and others. So I'm going to be talking about single photon detectors. And the first question is, what is a single photon detector? Well, it's capable of producing a measurable output signal from an input single photon. And so we often think of a single photon detector as the sensor. So for example, you might think of a photomultiplier tube where a photon can hit a photocathode, and by the photoelectric effect, a primary electron is ejected and sent through a dynode chain where by electron emission and acceleration along a voltage chain, you get gain. And you get a macroscopic current pulse at the end output. That's your measurable output signal. Or you might think of a single photon avalanche diode. These are the most common two types of single photon detectors. A single photon avalanche diode, and here's a cross section where it's basically a PN junction with a deep absorption region in this case. And the junction is biased above its avalanche breakdown so that it only takes a single injected carrier to initiate a runaway avalanche based on impact ionization. And then you can get a macroscopic current from that. Or you might think of a superconducting nanowire detector, or an SNSPD, which are the highest performing types of detectors of this type of detector anyway, where a single photon hits a nanowire that's a few hundred nanometers in width and a few nanometers in thickness. And it creates a hotspot that grows to a normal region in the wire. And if the wire is current biased, then you get a voltage spike because it was formerly superconducting, and all of a sudden there's a little piece of resistance in there. But the point of my talk is that these sensors exist within systems. So for example, a SPAD system might look like this if you open up a SPAD module, or an SNSPD system might look like this if you open the cryostat. And the systems really allow the sensor to operate. It's going to energize the sensor. It's going to control its function. It needs to be read out. The sensor needs to be read out. And then many of these systems need to be reset. And the capabilities of the overall detection system are often determined by the control system in which it's operated. And so that's what I'm going to try to convince you of. And this is often an engineering issue. So for example, in SPADs, well, single photon avalanche diodes are very popular. They're low cost, they're low power, they're compact, and they have reasonable performance over a broad spectral range. I didn't include silicon carbide devices that might work in the UV, but they cover the visible and near IR in silicon and indium gallium arsenide with reasonable, but not 100% detection efficiency. Silicon devices, thin ones, which operate at the shorter wavelengths with high efficiency, can provide pretty good timing resolution, full width half maximum of 20 picoseconds. And these higher efficiency devices can offer a few hundred picoseconds of temporal resolution. And they can have low dark counts. And if you cool them, they can even have lower dark counts. In-gas devices are noisier. Indium gallium arsenide, indium phosphide SPADs are noisier, and they have lower material purity, and their performance is therefore lower. Both types of SPADs are susceptible to afterpulsing, where the macroscopic current pulse can result in a few carriers being trapped within the junction. And when the device is rearmed or recharged above breakdown voltage, if one of those trapped carriers is released, they can initiate a secondary avalanche without the input of a photon. So it's a noise event that's correlated to a prior detection event. And so typically a SPAD is turned off by its control system for a little while after an avalanche to allow charge to dissipate and traps to release. And so when you reactivate the device, there's a very low probability of afterpulsing. And for indium gallium arsenide, the amount of time you had to wait was typically very long. So for example, in this lower plot on the right, you'll see that to get reasonable afterpulsing, you had to wait a few microseconds. And to get to the minimum noise floor, you had to perhaps wait up to 10 microseconds. So these devices were counting in the kilohertz range or tens of kilohertz range in the early days of quantum key distribution. And that was unfavorable. So what can we do to reduce afterpulsing? Well, it's known that the afterpulse probability scales with the amount of avalanche current. And so things that we can do to reduce afterpulsing is reduce the amount of current that flows in an avalanche. And one way to do that is by bias gating the device. So you just raise the bias voltage above the breakdown voltage where runaway avalanches can occur for very short periods of time. Of course, the device is only sensitive to single photons while it's above breakdown. So these are the duty cycle suffers, and the system's only useful for communication systems like quantum communications, or perhaps where there's a lot of photons and you might not miss a few of them. So anyway, so this is the engineering part. What happens when you gate a SPAD? So here's an experimental trace of a gate pulse applied to a SPAD, AC coupled to a SPAD's cathode. And if you look at the anode, the readout of the anode, you'll see this black transient that comes out the anode of the SPAD. And if there happens to be an avalanche during the gate while the SPAD is biased above its breakdown voltage, well, then you might see a rise on the anode due to the conduction, the runaway avalanche current. But of course, it terminates when the bias is brought back down below breakdown. So if you want to detect these avalanches with, say, a comparator, the avalanche either has to be higher than that gate transient, or you have to suppress that gate transient. And the question arose a few years ago, since these devices were critical for quantum communications, is can we really reach a fundamental limit in avalanche size? How sensitive can we be to avalanches? And essentially, how much gain do we require from our SPAD to produce a measurable output signal and still be useful? And so the quest went on to minimize that quantity. And the approach that we took was to to essentially use optimal filtering of this systematic noise that we were seeing. So if you bias the SPAD with, say, a sinusoidal signal, and you set up a Mach-Zehnder interferometer where the SPAD is in one arm and you have a reference arm, and you cancel at the output of the Mach-Zehnder, you can suppress that sinusoidal signal coming through the SPAD. When you set this up, you can get great cancellation, many tens of dB of suppression of that signal. But when you set that up, what you find is that you also see the harmonics of that bias signal, okay? And that's because the diode is a varactor, because when you vary the bias on the junction, the depletion width modulates a little bit just due to the change in the bias. So it acts like a nonlinear capacitor, which generates harmonics. But that's not a bad thing, actually, because we also want to have short gates in a SPAD. So if we apply multiple harmonics to the input of the SPAD, we can shape a gate using, say, Fourier synthesis. And then we can use all those same harmonics in the reference arms to suppress the gate transient. And we can have a short gate with great suppression of the gate transient. And so, for example, in this lower plot, I'm just showing what happens if you just use one harmonic, you just have a sine wave in black. And if you add just a second harmonic, you can shorten the width of a gate by almost half just by the addition of a single harmonic with the appropriate amplitude and phase. So as part of a DARPA program, we pushed this to what we were able to do, which was a combination of 4 harmonics in the gate and the cancellation arm. And with 4 harmonics and a rep rate of 1.25 gigahertz, we were able to make gates on the order of 145 picoseconds in width. You can see them here. With 3 harmonics, the minimum was about 200 picoseconds, and with just 2 harmonics, it was 280 picoseconds. And this system required active stabilization because it's essentially a multi-harmonic Mach-Zehnder interferometer. So we built this system, and it worked very well. And so how close to the fundamental limit did we get? Well, on the cathode of the SPAD, we're applying these 22-volt gates, very high amplitude gate pulses at 1.25 gigahertz. And on the anode of the SPAD, on the output of the interferometer, we're measuring these kinds of signals after a low noise amplifier. So this is with all the harmonics suppressed. And so, this has roughly this noise has a Gaussian width. And so if you just take 5 sigma of that, we estimate roughly 25,000 electrons for the minimum threshold we could set here. And then if you calculate Johnson noise for a room temperature 50 ohm load, using the same avalanche duration, you can estimate roughly 5,000 electrons. So we start to get to approach the fundamental limit for room temperature operation of these devices by using nice interferometric readout systems. So how did all this pan out? Well, this system would greatly suppress the afterpulse probability. So I copied that plot from the earlier slide up here on the right, and I'm showing that the afterpulse probability, instead of microseconds of recovery time, now we're down to a few nanoseconds of recovery time for high efficiency operation. And this led to a significant increase in the usable count rate of these devices. These spikes in the data here are just an optical reflection from an FC connector. So we actually applied the same thing to nice silicon devices, not because they had a particularly low noise, but because these devices operate at a much higher voltage, and they typically had a count rate that was limited by their recovery time of a few megahertz count rate, less than 10 megacounts per second. And that was primarily because these voltages were fairly high, and the amount of time it took to switch these voltages was reasonably long using the electronics at hand. But if we simply put them in one of these Mach-Zehnder interferometer systems again, the same SPAD taken right out of a module can recover in a relatively short amount of time, a few nanoseconds. In this case, we're just applying a single sinusoid to the SPAD and using 3 harmonics to suppress the gate transient at the output. And we can reduce the amount of charge in an avalanche by about a factor of 500. And this allowed this the count rate, the device to count roughly 10 times faster. So if they were normally counting up at a few million counts per second, up to 10 million counts per second, we were able to push this device up to 100 million counts per second without going below the original efficiency of the module. And this drop off here, we just know occurs due to the AC coupling of our comparator. And that means that these small avalanche signals that are really just crossing our comparator threshold, as the duty cycle of the signal going into the comparator changes, these events drop below threshold. So anyway, so that was another useful application of the same technique. For SNSPDs, these devices don't have any problem. Well, they don't have a lot of problems. They're nanowire detectors, and the detection cycle looks roughly like this. So if this is a nanowire with a current bias, those white lines, and a photon hits it, it creates a local hotspot, and that hotspot grows until it creates a normal region in the device, and there's a voltage spike across this normal region due to the current bias. And then there's an inductive and thermal relaxation of that hotspot. The inductive part is just the kinetic inductance due to the current flowing in the superconductor. And then there's the cooling of the nanowire itself, which isn't actually a lot of energy, but if the current is too high, the hotspot can latch up. But anyway, the point is that these devices produce an output signal that looks roughly like this. It's a fast rising edge with extremely low jitter, and then a nice exponential relaxation due to the inductance of the nanowire, of the bias current. And they can have very, very low dark counts, nearly zero. The dark counts, these may be dark counts from, say, cosmic rays, as we were mentioned earlier, or potentially anomalous thermal events, things like that. The circuit for an SNSPD looks like this, where there's a current bias, and then the superconductor is normally conducting, and if a photon hits it, the switch opens and you get a little resistive path, and you get a little voltage spike on the output. And you can make arrays of these devices. A kilopixel imaging arrays have been made using a clever geometry of a row column readout, where you can you read out both lines biasing the SNSPD. These little circles are SNSPDs, and you can get a positive pulse and a negative pulse and on the rows, on the columns and the rows, and locate which pixel fired. And this has been a successful technique for the kilopixel scale array. But the question arose, the limitations of this approach is that you can get one count per row and column per relaxation time. So if one of these pixels fire, that row and that column is down until that relaxation time is over. Moreover, if you want to scale to, say, a megapixel or a much larger focal plane array, you're going to need a readout system that's ready whenever the photons arrive, which can be a lot. That could be a tremendous demand on the room temperature system. And what you'd like to do for an imaging system where temporal resolution may not be an issue, what you'd like to do is have the room temperature system control the readout of the focal plane array. And you'd like the sensor to just accumulate photon detection events until you're ready to read them out. This is exactly how a CCD works, for example. The difference is that an SNSPD would have zero noise. This can be done with superconducting nanowires, in fact. About almost a decade ago, this 3-terminal device, it's very much like a transistor, was invented at MIT, called an N-tron, a nanocryotron, which is really it's all metal, but it's just a constriction on a superconducting channel. So there's a gate input and a drain and a source. And the drain source is biased with current. And then when a current on the gate crosses a threshold, this narrow constriction right here gets hot and it goes normal, and it generates enough heat to cause the channel to go normal, and then the device stops conducting, or at least becomes resistive. And so a very small input current can cause a large change in current in the drain source channel. So it's a thermoelectronic device. And it's useful because it can be triggered by the output of a SNSPD. So for example, if we have a bias current going through an Entron drain source, and then we have an SNSPD, and the SNSPD's output drives some current into the gate, well, whenever the gate is activated and the Entron goes normal, some of the bias current can be diverted into a storage loop, right? And so each time the SNSPD fires, we get another increment of current getting injected into the storage loop. And using SPICE simulation, these devices can be modeled using SPICE. This is an illustration of that process. So here's 7 detection events and 7 levels of loop current in this storage loop. So what's really neat is that these devices can be chained. So you can make an encoder at the sensor on the superconducting wafer using chains of these storage loops. So for example, here's an SNSPD driving this first Entron that would inject some current into this storage loop. And if I have that first storage loop include another Entron, well, then when the current in the first loop crosses the threshold of the second Entron, it will inject current into the secondary loop and deplete the current in the primary loop. And so you can create a counter this way. And so here's a simulation of, say, 3 detection events, and you can see when the first detection event occurs, the first loop is charged. And then when the second detection event occurs, the first loop charges up to a higher level, and then it triggers the threshold of this loop Entron, dumping the current in the first loop and injecting 1 unit of current into the second loop. And then when the third photon arrives, a unit of current is re-injected into the first loop. And so at this point, the first loop has 1 unit of current and the second loop has 1 unit of current. And if you read it out by, say, disrupting the conductivity of both of these loops simultaneously, you'll get little current voltage spikes on a readout line. And that would be the binary digit 1, 1, which is 3, okay? What's also neat is that these types of encoders or counters don't have to work in binary. If we adjust the bias current of these Entrons, these loop Entrons, then we can cause the threshold at which they go normal to change. And so we can require, say, 3 detection events to make the loop Entron trigger and operate in a base 3 counter. So it'll take three units of current in the first loop to inject a single unit of current into the second loop, and so on. And so here are 7 photon detection events simulated, getting injected into a base 3 counter. And when you apply the readout pulse, you get the trinary number 21, which is 7. So this is great because this is great scaling for counting to very large numbers. And this has been demonstrated experimentally at MIT. This is 1 storage loop right here with a very large loop inductor. This is what holds the current in this loop. The Entrons are these little junctions right here, 1, 2, 3. And current is stored in this loop. And then when a threshold is, it's being driven by an SNSPD. And then it injects current into the second loop. And then there's a third Entron just for readout that just goes to a resistor. So you can see the experimental result here where the SNSPD fires, and each time the SNSPD fires, this first loop Entron is triggered, of course, the first input Entron. And then every 2 units of the input Entron, the second loop Entron fires. So it'll take 2 events, 1, 2, on the input Entron for this Entron to fire. And then the next 2, 1, 2, and then the second Entron fires again, and so on. And it'll hold the current for arbitrary periods of time. So the amount of time between detection events doesn't matter at all. And similarly, because it's operating in base 2, this third Entron fires for every 2 detection event, or 2 firings of the second Entron, and so on. So this is a 2-digit, I'm sorry, I guess it's technically a 3-digit base 2 counter. Obviously, this is all, prototype stuff, and the device area is an issue. These inductors are relatively large, but this is a powerful technique for scaling to integrating detection events at the sensor with essentially zero read noise. So we can make a focal plane array with the sensitivity of an SNSPD and zero read noise. And SNSPDs have been demonstrated operating everywhere from 400 or 300 nanometers out to about beyond 10 microns now. So they have the potential to scale far into the IR. We've experimentally demonstrated counting not in base 2, but all the way up to base 6. So with just a few digits in base 6, you can count hundreds of detection events at the pixel, at each pixel, and then read them out when a room temperature readout system gets around to it. Okay, so I hope I've convinced you of I hope I've achieved my goal of convincing you that both the single photon sensor and the system in which it's embedded matter. And moreover, that your capabilities of detecting single photons can really be enhanced without changing the sensor at all, really just the support electronics operating the sensor. Thank you very much.
Yeah, thank you very much. That was really great. And definitely quantum engineering was a great presentation. And I was wondering if there is any question. I have myself a question. So I'm curious about detection, single photon detection, free space kind of application, how that can be achieved. I would like to know.
Sure, yeah. So if I roll back to this picture of a SPAD, for example, are you talking about in SPADs or in SNSPDs?
Any kind of detection, but like, for example, during the day, let's say outside.
Oh, sure. Yeah. So here's a free space coupled SPAD with an area of about 180 microns across, sorry, a diameter of 180 microns. And during the daytime, there's a lot of background solar flux. So you basically have 3 knobs to operate with single photon communications during the daytime. You can spatially filter so that your SPAD's active area is only seeing light from a selected spatial source, right? So that'll be limited ultimately by diffraction, but really by scintillation in the air. You can do spectral filtering. So your communications band or your signal band can be a very narrow spectral region with very high quality optical filters, but not unit transmissivity. There'll always be some loss of the filter. And also there'll be a skirt to the filter that has to be considered as well. They don't have perfect edges. And then the last thing you can do is temporal gating. So for a communication system, the propagation speed through air doesn't change much at all. The density, I mean, you know, the index of refraction of air is 1.00 and then some numbers. And so it's really only in the 3rd digit there that the propagation time is fluctuating due to, say, density changes in the air. And so you can, if you have a receiver and transmitter temporally synchronized, then you can do very powerful rejection of any background photons. And so, for example, we've been able to do free space QKD during the day with temporal gates as short as, I think we were operating with 100 picosecond temporal gate. And so anything that arrived outside of our 100 picosecond gate, we rejected as a solar or background photon.
How about, is it the same if you're doing entanglement? Similar?
Yeah, I mean, the same thing holds, although I guess it depends on what degree of freedom is entangled. But polarization is not disrupted significantly through the air. So polarization entanglement has been demonstrated through free space. And all the same tools can be applied.
Oh, great. Thank you so much. I have one more question. I think 2 more questions. Detecting single photon can be achieved by using a photo set or silicon nanocrystals embedded inside MOS structure. Why not use this technology?
I am not familiar with this technology. If it's a new type of single photon detector, I haven't learned about it yet.
Okay. And another question is, how can you be certain that you have captured exactly 1 photon and none missed or importantly, 2 or more masks in one event?
Yeah, so this is a great question. So all the detectors that I talked about here today can't tell the difference between 1 and 2 or 3 or 4 photons. They'll respond in roughly the same way. There might be a difference if you hit one of these photons, one of these detectors with say 100 photons, because for example, in a SPAD, you remove, by hitting it with so many photons at once, you remove a lot of the variation in the growth of the avalanche in the device. And so you can get a steeper edge at the output of the SPAD, but it really takes a lot to get that to happen. So these are all what we call click detectors. There are different detectors that can resolve photon numbers, or you can multiplex click detectors, for example, by using a spatial array of click detectors and distributing your light across them. Although 2 photons can still go to 1 detector, so you have to try to minimize that probability, and it doesn't scale well. But we can show that we can detect 1 photon by doing an anti-bunching experiments with say 2 of these types of click detectors, and illuminating something like a Hanbury-Brown twist interferometer with 2 of these detectors. And we can show that there was 1 quanta of electromagnetic energy going into the beam splitter of the Hanbury-Brown twist interferometer.
Thank you. And a question from Ron, which circuits simulation SPICE?
Yeah, it's just LT SPICE, the free one.
Oh, okay,
yeah.
Interesting.
Yeah, there are some models, I think they've been published by the MIT group.
Okay, thank you so much, Dr. Bienfang. I think there's no question at the moment so far. I really appreciate that.
Okay, great.
Interesting presentation, very informative. Appreciate you.
Okay. Let me stop sharing here.
Okay.
Can I stop sharing? Oh, here we go.
On to our next presentation by Dr. Neil Zimmerman from NIST, the challenges of distributing entanglement over a quantum network.
Hi, everybody.
Yes, please
Can you
share.
hear me okay?
Yes, I can hear.
Okay, I'm going to share my slides in a minute. I
Thank
just wanted to mention a couple of things before I start. This has been a really great workshop. Thank you, Farbad.
Thank you.
First of all, I'm running a simulation on my computer. So Farbad, if at some point I start to really slow down, please let me know and I'll stop the simulation
Sure.
going. Secondly, I'm going to be talking about quantum networking, and Prem, Kumar, and Kathy Ann Soderberg's presentations earlier were very nice for me because they set the stage in a lot of ways. So you'll see on a couple of slides, I'm basically going to skip over those slides because they already covered them quite well. And I'm sure nobody's going to mind having a shorter talk. This is a fairly long day.
Yes.
All right, so let me see. Oh, I'm sorry. And the last thing is, I would be happy to take questions during my talk. And I will not be able to see the chat window nor the Q&A. So Farbad has graciously agreed to monitor those for me. If you ask a question that's a very general question, like, can I suggest some book or a workshop to read? He'll ask me those. We'll look at those after I finish my talk. But if you ask a question that's directly related to something in my talk or asking me to clarify something I said that wasn't unclear, I would be very happy to stop and answer those questions in real time. Thank you.
Thank you.
All right, let's see if I can do this again. I did it a little while ago.
Yes, we can see it.
Okay. Can you see my red laser pointer over the M
Yes,
in my name?
we can
You
see.
said yes, good.
Yes,
Hi,
thank you.
thank you for staying around. I'm not the last speaker, but I'm towards the end. This has been very interesting. And I'm going to also talk a little bit about engineering. And in particular, I'm going to focus on some of the engineering challenges of a quantum network. And as I said a minute ago, you heard a little bit about one of the particular challenges from Prem Kumar. That was Raman scattering and coexistence of the classical and quantum signals in a fiber. And from Kathy Ann, you heard about some very nice work on a variety of the challenges, more on the scientific side. So what I'm going to be giving is kind of a survey of the field and a variety of challenges. I am not going to be talking specifically about work at NIST. This is more a characterization of the whole world's advances and challenges. So amongst the pretty pictures I have here, I think Kathy Ann mentioned this, I think it was her. I'll be talking a little bit about some of the challenges of photonic integrated circuits. I'll be talking a little bit about some of the challenges in fibers. I'll be talking about some of the challenges in just something as mundane as a switch. And then if there's time at the end, I'd like to have kind of an open conversation where we talk about what the most compelling possible application is for quantum networking, because this is something that I haven't decided in my own mind. And I think it's a really open and really important question for many people in the field. So a little bit of just a free conversation might be fun if there's time available. Okay, so as I said, I would like to be clear in my talk. And so if there are questions that come into the chat that are obviously about Neil wasn't clear about something, I will stop and answer those, because I'd rather only get through half of my talk and be clear than to get through all of my slides and have nobody understand anything. And also, while I promise to try to answer your questions, I don't promise to succeed all the time, as in this cartoon from the Dilbert author. All right, so what's next? Aha, yes. This is just a bit of an amusing, perhaps amusing, I find it amusing aside. Someday, I hope to see a quantum network that uses neutrinos or gravitons or some other exotic particle. But as many people have already mentioned today, nobody expects that to happen. Everybody thinks it's just going to be photons. So that's what I'll be discussing as well. And as I mentioned at the end, I'd love to have a lively discussion on what people think is the really most compelling application for quantum networks. These are some of the ones that have been discussed. Alexey Gorshkov showed his very nice theory work on the improvement that one can get with entangled sensors. And again, of what I think of as the three areas of quantum 2.0, the obvious application is least well developed in quantum networking. And I will say that at the end. So while I'm giving my talk, if you want to put a little thought into what your particular take is on this, again, I'm not sure we're going to have time, but I'd love to hear some discussion. All right, so jumping right into some of the challenges, several people today have talked about the issue of single photon sources, and amongst the metrics that are important, this is sort of the inverse question to the one that Paul Borrell just put into the chat window on Josh's talk. This is not about having measuring missing photons in the detector. This is about the issue of putting out more than one photon in the source. And I'm not going to read through all of this. I will make one of the points is that as we work harder and harder to get pure and indistinguishable photons, it makes it harder to also get a high rate. So it's hard to optimize simultaneously all of these different metrics. And coupling onto and off of the chip, in particular off the chip, is a really big challenge, and people are not close to getting 99% or greater. And there are also some promising avenues with using multiplexing. Obviously, I'm not going through all the details. This is a survey, and I guess, Farbad, at some point you're going to ask for our slides. I'd be happy for people to see my slides. Okay, so next thing is switches. Probably at least some of the people in the audience have seen this kind of switch. They're ubiquitous in fiber communications. This is just a rack-mounted box. It's about this big, and a whole bunch of fibers come into one side of it. Those are the transmit lines, and there's a whole bunch of fibers that come into the other side of it, and those are the receive lines, of the inputs and the outputs. This is a very common commercial off-the-shelf item. It is not particularly expensive. It works pretty fast, I think microsecond switching times, or tens of microseconds maybe. But the issue in terms of using it for a single photon is that the light pulses that come in are converted to electrical pulses and then reconverted back out to a light pulse. And if you remember, I think it was Prem Kumar earlier who mentioned the no cloning theorem. It's impossible to do that. We can't convert, or at least it would be very hard to convert a single photon to an electrical pulse and back out in a way that maintained the quantum information of that pulse. There are some people who are thinking about doing that at the physics level on a chip, but it's not something that this kind of switch can do. Absolutely not. This is a purely classical piece of equipment. There are some switches that actually can preserve the quantum encoding, that is the single photon nature, that can lead to entanglement and teleportation, all the things that have been mentioned today. And that's because these mirrors don't convert to electricity and back. They actually have a couple of these micro-electromechanical actuated, to use a phrase that I know some of the people that organize this like, to take light coming in from a fiber and to direct it to a particular output fiber. Obviously, this will not degrade the single photon in the same way that this switch will, but the issue is that these are slow. And so for a lot of things where there's just a dedicated route from Alice to Bob, the speed of the switch will not matter that much. But if there are some times when we want faster switching, then that's going to be really important. And so that's another challenge. And as people have repeatedly said today, maybe some of the young people in the audience will end up making a lot of money by coming up with a better quantum compatible switch. All right. So the next thing again is this PIC, photonic integrated circuit. This is just one sketch of one type. And so I'm differentiating between what many of us who are on the older side know of as optics experiments, which are these big optical tables with big components, and you put your hands on it, you move stuff around, and again, just a single monolithic chip that has all of the waveguides and switches and all the other stuff on it. Again, I'm not going to read through all of the stuff that I have written here, but I will mention that amongst other things, sometimes temperature regulation on the chip is very important. It is clear that little changes in the lithographic sizes of things can be very important. And as Josh mentioned in his talk, Josh Bienfang, telecom versus visible versus infrared, those are really important differences. And some of the materials are not well designed for instance, detection at telecom. So again, just some of the different challenges in moving from physics optics experiments on a table to the kind of integrated thing that we would need if someday we're going to have a quantum internet. All right, so let's talk a little bit about fiber attenuation. As I think Prem Kumar, somebody mentioned earlier, we can't just amplify a single photon the way we can amplify light pulses that go around the world now. For instance, some of you may be aware, all of the submarine fibers that go between the American continent and the European continent or the Asian continent, those all have what are known as fiber amplifiers. These are sections of fiber that have erbium atoms doped in them. Every, I don't know, 100 kilometers or something along the floor of the oceans. And that's a way to send a signal from New York City to London town and still have a big signal when we get to the other end. Again, because of the quantum no-cloning theorem, we can't amplify a single photon and maintain its quantum information. So amongst the ways that people have come up with for getting around that, I'm not going to explain the complicated topic of quantum repeaters, but I will say it's a combination of the physics experiment called the Bell state measurement, and Josh, I think, mentioned that repeatedly in his talk, done in a hierarchical way. So there's a Bell state measurement at every node, and then every 2 nodes, and then every 4 nodes, and every 8 nodes. And it uses this concept of entanglement swapping that we've heard of today. There's a little bit of experimental and theoretical work in something called cluster states. I'm not going to go into this at all, other than to say, in my opinion, cluster states can't solve the problem. They can just enhance the effect of quantum repeaters. And the simplest brute force possible way to do this, and again, maybe some young person in the audience will come up with some great new fiber material, is to just make the fiber with 1,000 times less attenuation. Now, that's easy for me to say, and obviously if it was easy to do, people would have done it 50 years ago and earned a lot of money at it. But it is something that would be very helpful to the possible future quantum internet, in addition to which, of course, everybody using the internet now would also pay more money to do that. Okay, so now I'm going to come back and talk a little bit more about one of the particular challenges in quantum repeaters.
Can I ask?
And I'm only going to talk.
Sorry to interrupt.
Yes, go ahead, please.
There is a question, sorry, I missed that from your previous slide. How many mirrors could you have in that right-hand photo? I missed that in the previous slide. Sorry.
I'm sorry, I'm having a little trouble hearing you. The question was about this and how many mirrors could one have?
How many mirrors could you have in that right-hand photo? Yes. How many mirrors?
Okay, you know what? I don't know the answer to that. I am not an expert on this type of switch. If anybody else in the audience knows, please just answer it in the chat or speak up. Sorry, I just don't know. Okay, so going on with the quantum repeater, thank you, Farbad. Again, anybody that wants to ask a question, please feel free to do so. And Farbad, just tell me when to stop. The hardest part is in this Bell state measurement. And in particular, in the fact that we need both photons to arrive at the detector at the same time. So if we have 2 photons coming from 2 sources that arrive at the same time, that's great. If we don't, within the lifetime of the pulse, then that's not good. The Bell state measurement will not work in that case, in which case the whole quantum repeater scheme will not work. So in this context, same time means within the lifetime of the photon. And that leads to the hardest part, in my personal opinion, of quantum repeaters, which is getting what's known as quantum memory, meaning the first photon comes in and we hold it while preserving its quantum information content until we know the second photon is coming also. And let's see, is it the next talk? No, the second talk from now by Aditya Sharma, and I hope I said his name right, will be talking about one way to implement this. All right, so now I'm going to talk a little bit about coexistence. Prem Kumar discussed this earlier in detail, and he did some very nice work. So I'm going to skip past this slide, except to put the same problem in a different context. In the classical internet, each light pulse is at least 1 trillion photons. So this might give you a better visceral sense of why, if we want the classical signal, which is in all these layers of the network stack, along with the single photon that's in the quantum or physical layer, having those in the same physical fiber clearly is going to be a challenge. And again, Prem did a really nice job of discussing that. So I'm just going to skip over all of this. And again, he talked about Raman scattering. Okay, so here's my summary of the first part of the talk. If people want, there will be some time to go into this discussion of applications, but there's a lot of engineering problems that have been solved for the present internet. And I hope I've given you a sense that there are a lot more problems to be solved for the future quantum internet. And that's a great thing, right? Most people that are in science and engineering go into it in part because they like hard problems and they like the challenge of solving them. So again, I'm not going to read through what's on the screen. I'm sure you can read it for yourself. This is just a list of some of the things that I discussed. And my acknowledgements are, unfortunately, there have been probably 50 or 100 people that have helped me understand the various aspects of quantum networking. And some of them are actually attending or speaking at this workshop today. So you know who you are. Thank you all. All right, so going on to, oh, maybe I should stop right now. That's why I put the slide in here. Before I go on to this other discussion, if anybody has questions, please let me know. No other questions? Okay. I guess I'm going to go back and try to have a little discussion.
Thank you very much, Dr. Zimmerman. This is really interesting presentation. And do we have more slides?
I'm going to go back and do the last part of my talk, which is this part. So can you once again see my red laser pointer on a slide with people sleeping?
Yes, we can see them. Thank you.
Excellent. So I'm glad we have a bit of time to discuss this. So let's go from the sleeping audience to the awake audience. And I mentioned this a little bit earlier. I'm going to discuss it again. There are I think of three areas in quantum 2.0. There's quantum computing, and we've seen a fair number of photographs today of superconducting qubit devices in big dilution refrigerators. We've had a bit of discussion today about quantum sensing. To me, the applications, the argument for why quantum sensing is by far the easiest, because there are companies right now who at least have venture capital funding, if not are actually earning a profit on quantum sensors. And I can't remember who it was. It might have been Dr. Quadrelli early, who talked about the TRL, and he made the point that there are TRLs of 7 or 8, technology readiness levels of 7 or 8 for some quantum sensors. But for quantum networks, it's clear to me that there is no good consensus for what the killer application is. And I would love to hear some discussion of this. I'm going to start by just giving you my personal opinion, which is right now we have quantum computers with a couple of 100 qubits. And I think it was Britton who mentioned a while ago that IBM and other companies are talking about going up to 1 million, or I've seen as much as 100 million qubits. And we're probably not going to make a single dilution refrigerator that's, I don't know, the size of a football field, or I don't know, maybe a whole house or something. It seems very likely to me that to get to something like 1 million or 100 million qubits, we are going to have some type of quantum server farm, probably in a place near the North Pole or South Pole where the cooling cost is a lot lower, just as server farms and cloud computing facilities are often in cold places. And so one imagines each of these racks would have a whole bunch of rack-mounted little quantum computers that might have 100 or 1,000 qubits in them, and then they'll all have to be entangled together to make the whole quantum algorithm work. And it's that entangling that has to go on a single chip between the different things in the rack and from one side of this facility to the other, that, in my opinion, is the most compelling application for quantum networking. The idea is that all the things that we need to entangle over the whole Earth or into satellites, as Kathy Ann mentioned, still have to be done on this short scale. And it seems very likely that this one, at least, will be necessary in order to get the full promise of the quantum advantage. And so I would really love to hear other people's thoughts on this. So I am going to stop sharing now, and I am going to look forward to seeing if anybody else wants to share his, her, or other possessive opinion on this.
First, thank you so much, Dr. Zimmerman. I have two questions here. If the fibers can get better for lower wavelengths, what are the solutions to use existing fibers?
I'm sorry, are you reading this out of the Q&A?
Yes, yes.
Okay, let me try to read this at the same time. And Ron, I'm sorry I didn't have the answer to your question about the mirror switch. If the fibers can't get better for lower wavelengths, what are the solutions to use existing fibers? I don't know if there is, I don't know of a solution to use existing fibers. That's my honest answer. And then what are the advantages, examples of advantages of networking quantum sensors? Well, Alexey discussed the theory of that. And early in his talk, he made the point about the standard quantum limit versus the Heisenberg limit. That in the standard quantum limit, when we average sensors together in a very common way, we get 1 over the square root of n better signal. Whereas if we network, if we entangle the sensors, then we can get to a 1 over n averaging, which is clearly substantially better. And that's my best short answer for the advantage of doing entanglement of quantum sensors. There's also clearly the advantage of just having quantum sensors, and Clarice had this recorded talk where she talked a bit about that, which I thought was very nice. And then obviously a sensor isn't useful unless we can communicate with it. So I don't know if your question was about entangling or networking quantum sensors, so I tried to answer both. And then Anonymous asked, does that mean we need networks of dilution refrigerators? That does seem unlikely to me, but I don't know. It just depends on what people want to do and how much they're willing to pay for it. Okay, and then Changli asked, what is quantum repeater? Keep the quantum state. Again, I can't go into the details of this, but I will bring my presentation back up and try to answer this in a bit more detail. So the question is, how do I get a single photon, or how do I entangle a single ion or atom or superconducting qubit or semiconducting qubit in Africa with a single qubit in South America? As you've heard repeatedly today, we can't send that single photon over 10,000 kilometers of distance in a fiber and have it survive. So one way to do that, which Prem Kumar mentioned earlier, is if I have a qubit here and I have a qubit here and these are long distances away, we can use this entanglement swapping idea. And so the quantum repeater is just a hierarchical way to use that entanglement swapping. So for instance, I have 2 qubits, I have 2 entangled photons here, and I have 2 entangled photons here. These 2 go off and go through a Bell state measurement, and that entangles this one with this one. And then I've done the same thing on the other side. And then with the next Bell state measurement, I entangle the one over here that you can't even see with the one over here. So I've entangled 2 away, 4 away, 8 away, 16 away. I'm not amplifying the same single photon. I'm just achieving the goal of entangling qubits that are very far away by doing this entanglement swapping. And I hope I answered your question. And then Sean Moore asked, could you entangle a quantum memory and physically move it to another location? Absolutely. And there is, for instance, at least one group that's using what's known as optical tweezers with ion qubits to do that, where they actually move the ions around. If you're talking about moving it from Africa to South America, that seems like a very tall order, which is why people talk about doing with photons instead. But Sean, if I don't know over what distance you're asking this question, so I've tried to give you my best answer. If you want to unmute or ask another question, I'll be happy to answer, although I know I've gone past my allotted time. And I'm sorry that nobody put in his or her favorite application for quantum networking. I was hoping to have a discussion, but that's okay. There's lots of questions and I'm happy to answer those too. Oh, Sean wrote, that's good, thank you. Okay, great. I read a science fiction book once where this entity would send entangled particles between different galaxies, but that's not something that's within the technology of humans for a long time to come, I think. Aha, Sean was thinking across continents or on satellites. I have not seen any proposals for physically moving ions or clouds of atoms or superconducting circuits or semiconducting circuits between continents or on satellites. If you've seen that, then I'd love to know about it, but I'm pretty sure that over those distances, people are just talking about moving photons. In part because I don't think anybody knows how to preserve the quantum state of a qubit while it's being driven across a continent, both in time and in distance. And it's going to be shape, and temperature, and humidity, and all those other things, those real world things. I should probably stop talking now. I'm past time.
Thank you so much, Dr. Zimmerman. It's really interesting, useful and helpful, informative presentation. I really appreciate that. Okay, so the next presentation by Dr. Thomas Gerritz from NIST. The title of the talk is Optical Quantum Metrology from Component Characterization to Quantum Network Metrology. Welcome.
Hi, good evening. Can you hear me?
Yes, I can hear you.
Can you see my presentation?
Yes.
Looks good. Okay. Yeah, thank you, Fabot, for the nice introduction and having me here to talk about the optical quantum network metrology. It's been a great workshop so far, and I don't know if I thought I might not have enough time to go through all the slides. We'll see at the end, but there were some really great introductions and background information provided. So I may be able to skip over some of those. I can cover all the stuff that I have in there. So this work, we're working with a whole bunch of colleagues in Boulder and in Gaithersburg at NIST to develop metrology that is related to quantum networks. And so I want to give you an overview on what we have done, and that's mostly related to component testing and component metrology, so single photon detectors, single photon sources, and then tell you how we envision to do the quantum network metrology. So give you, give you an outline of the talk. I give you a quick overview of future quantum networks and challenges that are important. And Neil just gave a fantastic talk about the challenges itself. So it's just going to be a short recap. I'm going to tell you about single photon detector and source characterization. And so this is the next part is kind of, if I still have time, I would like to talk to you about node synchronization, and it really connects to what Neil was just covering with doing Bell state measurements and having photons arrive quasi-simultaneously, actually within picoseconds over kilometers of distance, and how we can solve that. And then I'll conclude with an outlook. So I like to put this slide up. This is classical internet traffic as a function of years. 2016, that's when this graph ends. I don't have an updated version of it, but we all know it. The global internet traffic is growing exponentially. Will this be the same for quantum networks? Will we ever have a quantum internet? We don't know. I think what we do know is that we are kind of down here. This is the graph that shows the total hosts within the internet out to 2019. And in the late 60s, early 70s, there were a few nodes, a few hosts. And that's where we are, a few nodes in test beds, demonstrations, entanglement of, 3 nodes maybe. So we have a long way to go. However, what we do know, from this exponential growth, let's say communication channels get narrower and narrower because you want to pack more and more information there. And so you need to do measurements. You need to, for instance, when you communicate classically, the laser has to have a certain wavelength. You need to send that signal at a certain wavelength, and you need to measure that wavelength. You need to confirm that the wavelength is where it should be. So that you would call optical performance monitoring. So you're basically constantly monitoring the performance of your network. And that really helped to speed up the development and the growth of the internet as we know it. It requires resources and it may be costly, but it helped the development and the growth. So we are envisioning something similar for quantum networks, actually. And I hope, I can go into more details during this talk. So this is just a very schematic overview of 2 nodes that are connected within the quantum network. And, there's one node, there's another node. All these nodes will have inputs and outputs. And what we do know is that there's going to be photons exchanged between these nodes, probably at the telecom wavelength, because as we heard, this is the lowest loss possibility of sending photons long distances. And so we use optical fiber here in the quantum link. The 2 nodes will also be augmented by a classical link to exchange classical information. And that's where let's say the metrology data that I will talk about later will be exchanged and will be able to get access. Components, in the nodes, they range really from, like, let's say classical or passive components, just switches as we've just seen, optical fibers, frequency converters. So this would maybe then be a quantum component, quantum memories, quantum repeaters, or the qubits themselves. Now, the whole idea is to have this network work in a heterogeneous fashion. That means that I have a component, or let's say a qubit from vendor A operating at wavelength A, communicate with a qubit from vendor B operating at wavelength B. So there needs to be there need to be measurements done. There needs to be some sort of performance metric for these components to be able to talk to one another. And it may require a frequency converter because wavelength A is different from wavelength B, and I cannot talk unless you have the converter. Now, all these components will challenge the photons that are being sent through them. And related to Neil's talking about challenges, these challenges are loss and noise and decoherence. So we need to characterize these components, make sure that they work accordingly, so we can maybe deploy them on a big scale. So to summarize, basically summarize Neil's talk, not all of it, he talked a lot about a lot more things, but to summarize for some of the challenges for future quantum networks. This quantum channel will not necessarily be a dark fiber. So the fiber will have classical signals going through. So we have the coexistence problem that we heard about today. For the quantum signal to be successfully transmitted, we need to have noise that is 10 orders of magnitude lower than classical signals. So the noise in classical signal systems is like microwatts, so we need to be on the order of femtowatts or lower. And I said, coexistent classical signals with very faint quantum signals. We also heard that quantum information copying is not possible because of the no cloning theory. And the network needs to be transparent. There's no optical electrical to optical conversion. So we cannot have these nice cheap switches as we heard in the last talk. There's also a thing called polarization mode dispersion. So for a lot of the applications where interference is necessary, the polarization of the two photons or photons need to be maintained or at least well known so we can compensate for it. And normal single mode fiber, we have polarization mode dispersion. So the output state of the polarization is unknown at the end of the fiber. We need to know that so we can adjust it. We do need quantum repeaters, as we just heard. And in order to do these Bell state measurements and to maybe have quantum repeaters, we need to well be synchronized. These nodes need to be well synchronized. And it depends really on the application. It can be picoseconds to nanoseconds. And this, you know, when you talk to classical networking folks, this is difficult, you know, synchronizing a node down to a nanosecond. But there are already, as I hopefully can show later, commercial equipment is available to principally do that. So for metrology, what do we want to do? Or what is the aim here? We need to develop an infrastructure and standards to characterize the nodes, transmission and protocols. We should develop versatile tools and measurement procedures. And we need to disseminate what we have just learned through tools and our expertise. So again, you know, we hope that the metrology will assist the technology development and allow for the heterogeneous integration of newly developed components in the future. Right, so this is the grand picture, the grand vision, let's say. And so now I'm going to tell you what we've actually done. So I want to start out with a baseline characterization tool for optical single photon metrology, and that is the single photon detector calibration, where we characterize single photon detectors. And that also goes back to Josh's talk, because I going to talk about some of the metrics that he actually mentioned. And then also I'm going to talk about single photon source characterization, so we can characterize the spectrum of a single photon source very efficiently. I won't have too much detail to go into this, but we have also the capability of measuring photon number. So we, in a single shot, we can measure and determine the number of photons, and we can measure or characterize exciting photon number statistics from that source and characterize the goodness of the source thereby. Right, so I'm going to start with the detector calibration, but I want to tell you why it is actually a baseline characterization tool. If we have a calibrated single photon detector, we know the single photon detector really well. What we can do, we can then attach a single photon source to it and characterize it with the single photon detector. What you then have is two well-characterized systems that work in unison, and you could call them measurement standards. Also, if you had a pair of those, you can always cross-check. You should always get the same result. And if not, then probably one of the two systems is not working well. So with this, once we have this pair of, let's say, measurement standards, we can insert devices. We can insert the devices or the network itself. And that's, again, these components that I was mentioning earlier. Right, so the way we do the detector calibration is based on a traceability chain at NIST. So we actually start out all the way with electrical standards. And then trace that down to measure optical power in an optical power meter. So effectively just a photodiode. We characterize a photodiode really well in the traceability chain. We add the nonlinearity of that power meter to it and its spectroresponsivity. And so with these three, we can now characterize and calibrate variable attenuators in principle. So, you know, if we are measuring power in the microwatt regime, we can now use a cascade of variable attenuators that gets us down to, 90 dB or something, which gets us then to the single photon detector, single photon level. And so we calibrate these attenuators using the power meter calibration and the power meter nonlinearity. And so here's a setup. We at NIST we actually have 2 setups. Actually, I think we already have 3 setups to measure efficiency of single photon detectors. And I'm showing you the one that we have here in Gettysburg. There's a picture. I might go into this in a minute, but the principle is as follows. We take a laser that sends out a stream of photons with about 10 microwatts, so that's really high power. Then we fiber couple it into an input attenuator, fiber attenuator, and that is at the input. And then we have a fiber beam splitter. Most of the light is being transmitted or reflected to the power meter, to a monitor power meter that effectively just keeps track of the laser power after this input attenuator. The low reflect or the low transmittive part goes to another variable attenuator and to a reference power meter. This is this one. So now we have maybe a monitor to power ratio, of 10 to the 5 or something. We measure 10 microwatt with this monitor power meter. We measure 100 picowatt with this reference detector. So that can set this ratio between the monitor power meter and the reference power meter. Now, as we now increase this input attenuation, we rely on the fact that the splitting ratio is constant. As we increase this attenuator in the beginning, we reduce the power, and we can reduce this all the way down to 1 femtowatt, which puts the power meter, the monitor power meter, to about 100 picowatts. So that way, with the absolute calibration and the nonlinearity correction, we can actually predict how many photons are here at that device under test of the single photon detector. And so with this, we can measure its efficiency. And again, here, this is an example of the calibration setup. The only thing that I want to point out is that we use a super continuum laser. So we can, in principle, characterize single photon detectors right now from like 700 nanometers to about 1700 nanometers. Okay. Yeah, so this is an example of a special test. And so this is now actually being developed as a service in Boulder, not in Gettysburg, but in Boulder. So you can actually send your single photon detector soon to Boulder, and they will be able to characterize this and your detector and quote you your efficiency with well-traced uncertainties. So what can we characterize of these detectors? So here, this is an example of a silicon APD, so an avalanche detector, as what Josh was talking about extensively. This is a free space detector, so we can measure the free space response of this detector. So this is the spatial uniformity, as we will. We can also characterize the after pulsing that Josh talked about in great detail. And so, as he mentioned, nanowires don't have as many problems as like SPETs. We can see this, the after pulsing here. So this is an after pulsing histogram. After, what is the probability? You're asking a question, what is the probability of detecting another photon or a pulse after you detected a photon? And this is this histogram here, and you can see this after pulsing peak here, and then it eventually levels out. And that's what you would assume to happen for a Poisson distribution for a continuous wave laser. This is for a SPET detector. This is for one of these nanowire detectors, these SNSPDs, and you do not see any after pulsing peak. And so if you plot that for various detectors, we have done this, we've seen some surprises. You know, in the nanowire case, there's no after pulsing, but for 2 different SPETs, the after pulsing actually goes up, the probability goes up with a function of count rate. And in the other case, the probability actually goes down as a function of count rate. So, and you need to know this probability of after pulsing, because if you include these counts in your detector character or calibration, you're overestimating your efficiency. You get an extra count for a photon that you're counting. So you need to characterize that and correct for this when you characterize detectors. And then the other issue that can happen is blocking loss. So as a function of count rate, the detector efficiency apparently drops. And that has to do with the dead time of the detector. So as also Josh mentioned, you know, a SPAT can be dead for 50 nanoseconds. So it means I detect a photon, and for 50 nanoseconds, I will not be able to detect any other photon. If a photon arrives within that 50 nanosecond window, I don't see a click. And you can imagine if my photon rate at the detector goes up, this the amount of photons that end up within that dead time will actually go up. Plus you have more clicks also. So what that means, the ratio between the measured click events to the actually impinging photon rate will drop. So it's an apparent drop in the efficiency. So that is important. So when you quote a detection efficiency, one should also say and quote at which count rate. Okay. Good. So this is our baseline detector characterization. I just want to now briefly mention the source characterization. So in this case, this is an example. We have many different methods and uses to characterize sources. I just like this one because it can really quote probe quantum phenomena in the frequency domain. So what we use here is we make use of dispersion of optical fibers. So that means, you know, we're generating a photon pair. This is a photon pair source. We send it into fibers. We send them individually into fibers, so the H photon and the V photon, and then we send them through dispersive elements. And that means that in this case, a blue photon arrives before the red photon in time. If I now have detectors that have extremely low timing jitter or timing uncertainty, I can now relate the arrival time of the photon, which is here on the left, to the frequency of the photon. And I can do a coincidence measurement because these photons are paired, and I can reconstruct this joint distribution, joint spectral distribution. Now, before we showed this measurement, working with these nanowire detectors, free running, these measurements took about 24 hours, and the quality wasn't nearly as good as this one. Now the measurements, you know, using this technique, take about 30 seconds, and this is a vast improvement for source characterization. And so with this, we were able to characterize the frequency response of a quantum interference at the homomonal interference dip. And this is like a basic ingredient for the Bell state measurements that Neil was talking about earlier. So we can use that technique, you know, to characterize the source, but also, you know, once we're in a network setting, we can actually use that to characterize the Bell state measurement in the frequency domain. Right. So what do we want for systems? This slide is basically to show that, you know, it's fine and good to do all of these experiments in the lab, but, you know, we want to kind of get these tools out there, get protocols out there, get best measurement practices out there, and we want to test these things in the field. So what we need is portable systems that actually have this good traceability of uncertainty. And so for that, we have a nanowire detector system that we can ship, which has well-characterized detectors. And then we just actually build a source that is now well-characterized in terms of its efficiency on how well you can couple light into or photons into the fiber. Now with these two, and this is like a 19-inch rack box. With these two now, you would have your measurement standards, a detector system and a source system. The traced uncertainty for the detector system is about 1%. For the single photon source, this is still work in progress, is now about 2%. Right. So looking a little bit into the future. This is also something we've already done, but we will deploy soon in a network. So when you take that concept of the source, we now want to distribute entanglement. We want to use sources that actually generate entanglement and not just correlated photons. And so again, we have this exact same source, just with a little trick. We get polarization entanglement out of the source. So we have down here 19-inch rack box with the source. We have two analyzers that are also 19-inch rack, and then a detector system. So now we actually have a source to distribute polarization entanglement. And looking into the big picture for the future is we really envision to have these instruments. Presumably now even 19 inches is still pretty big. If you think about it, having it at each individual node, these measurement tools. So of course you want to have them in integrated photonics at some point as well. So what the idea is here to have these, we would call them measurement suites or metrology nodes, like strategically located throughout a quantum network. And so what would these metrology nodes would do, they would send out known states of light. So you could call them almost a beacon of known states. And then you would have well-characterized detectors at another node, and you would then therefore characterize the link. And that can be, this is a telemetry data that can be fed into a management of the quantum network to route entanglement efficiently. And so, yeah, this brings me to the management of the quantum network, because in order to manage a quantum network, how do I route entanglement from node node 1 to node 3? I may have many different routes to take, and I can take different routes, and the shortest route might not be the best. There may be noise along the path. There may be too much loss along the path. Someone cut a fiber, or the polarization isn't maintained really well on a short time scale. So metrology will actually, these telemetry data will actually supply this management, this software-defined network, the management of the quantum network, provided with data such it can make an informed decision on which path to take for the entanglement to route, let's say, node 1 to node 3. Okay. Oh yeah, and then of course, this is now in the near future. So we are setting up a quantum network testbed at NIST, and the lab is being built right now. And for this, of course, we want to deploy all the tools, the metrology tools, and get the basic operation of the network going. Oops. Then we have additional space for user experiments, space for memories, and environmental testing, and so on. And we can connect to the outside, for instance, and many other labs around the NIST campus. Right, so how much time do I have left?
It's almost 4:30, but I think—
Okay, no time. That's good. that's okay. Yeah, I think I will skip over the synchronization part. Maybe I just gonna pose the problem real quick, and then we'll move on to the conclusions. So as Neil mentioned, for quantum repeaters, you need to perform an operation that's called entanglement swapping. And there's actually a beautiful experiment done a few years ago that shows entanglement swapping between two independent single photon sources. Now, these two single photon sources, they were all on one optical table in one lab. And what you have to do, you generate two pairs, 4 photons, and you do a 4-fold coincidence measurement between these 4 photons, while 2 of the photons are shared on a fiber, on a beam splitter here on a measurement plane that does the Bell state measurement. And based on the measurement outcome, you're swapping entanglement from these 2 photons to these 2 photons, effectively entangling the two sources that have never, the two photons that didn't talk to one another, namely this one and that one. And in order to do that, at least in this case, for spontaneous parametric down conversion, you need to do that with a precision, a timing precision. These two photons need to arrive at that beam splitter here with picosecond precision. In this case, you know, the delay is about, delta t is about 2 millimeters, but 2 millimeters correspond to, 10 picoseconds in fiber. And you can imagine, you know, if I go long distances in the network where the fibers are kilometers long, that is an extreme problem where, you know, the fiber might change by 10 picosecond easily over kilometers of distance. And so that's the problem. And I don't want to take too much time. If there are questions, I'm happy to answer the questions about the synchronization. What are the requirements? We need to define quantum and classical resources required for metrology. That's what we will find out, what's really necessary. Where do we really need quantum? So where do we really need entanglement to probe and provide telemetry data for quantum networks? We need to develop protocols for performance testing of the network to allow for efficient entanglement distribution, and need to develop standalone measurement systems for to monitor the network using various tools, components, and protocols. And so with this, I would like to thank you for your attention, and we're always looking for postdocs, so please let us know if you're interested. It's an exciting area to be in, and NIST really is a great place to be. Thank you.
Thank you very much, Dr. Garrett. It's really interesting presentation. I really appreciate that. It was very informative. I go quickly to the questions. I think the first one is in terms of synchronization, how to compensate for temperature changes and pressure changes that will do picosecond and nanosecond length changes.
Yeah, so thanks for this question. So yes, what we can do, we can send a short photon pulse through the same fiber and measure its arrival time. And then let's say physically adjust the delay, right? I mean, have a delay line somewhere at the end, but that's not really, you know, scalable if you think about this for every single node. The other option is to have like local clocks, local oscillators running at each in these individual nodes. And they all tick at the same rate. Now what you can do, and these run these photon sources or memories or whatever, you know, they're synchronized with the local node. And if you want to delay the emission of a photon by a few picoseconds, what you can do is adjust the phase of this local oscillator a little bit, such that now the photon will arrive at 4 quasi simultaneously with the photon from 1. I hope that answers the question. So I think this is the more elegant solution really, is to have local oscillators like clocks that you can adjust the phase accordingly. But then of course the whole network has to be synchronized with, you know, one grandmaster clock.
So if you have a local clocks, so there is a classical communication here, is that right?
Yeah, that's correct. That's correct. And we actually did experiments with a high accuracy precision time protocol. Sorry, actually it's called White Rabbit. And so what that is, you know, you have a leader that's driven by, let's say, grandmaster clock. In this case was a rubidium reference, 10 megahertz in, 1 pulse per second in, and you have a classical communication channel to connect to a follower from this leader. And so what the follower does, it follows the 10 megahertz with a jitter, shot-to-shot jitter of less than 10 picoseconds. We've actually measured jitters of around 2 picoseconds between the 2 10 megahertz outputs, and that's over a kilometer of fiber. Yes, and you could send the quantum signal through the same fiber, because we also did the noise study on it, you know, because there's a classical signal now through this HAPTP protocol. What is the noise induced into a quantum channel? And that's the result. It's like, you know, hundreds of thousands of counts of photons per for the quantum channel. And that's still okay.
Thank you.
Yeah.
Next question from Ron. What is the definition of a dark fiber or quantum dark fiber?
Yes, I would call it dark fiber. And maybe that's not the precise definition, is a fiber that doesn't have any other classical strong signals in there. So it's kind of a dedicated fiber to your application. I think there's the term dark fiber in the classical networking as well, which means that really, I think it's only dedicated to your application. So for quantum, that means we don't have any classical traffic in there. We only have our quantum traffic in there.
Thank you. And then the next question, can we characterize a single photon detector with the coherent light of a laser?
Yes, yes, you can. The efficiency, so all the measurements that I've shown was actually done with the coherent light of a laser. So it's a laser emitting basically coherent light, and you attenuate it all the way to the single photon level. And then what you see is that your photons will arrive in a Poisson distribution. So per time slot, you have a mean photon number, but the number of photons per given time slot is random. Yeah.
Thank you. Next question from your plot, Doppler shift of 10 nanometer exaggerated, I think in the parentheses, would result in a time of arrival difference of 1 nanosecond. So how can a free space network synchronize on a shot-by-shot basis unless the Doppler shift is perfectly constant?
Okay, I'm not sure if I understand that question. So, so first I thought maybe it was based on the time of flight measurement here when I saw this. Oh, so how can free space networks, sorry, Doppler shift, yes. It's pretty tough, I would say, on a shot-by-shot basis. I mean, if you're running at 10 megahertz, I don't see an easy way, if I understand the question correctly, to compensate for that, on a nanosecond scale. You probably would have to have systems that require less timing uncertainty. Yeah.
Thank you. And next question, how to synchronize entangled photon pairs before decoherence?
So I hope that answers the question. Oh, sorry, that goes the other way. So if you imagine, that these local oscillators drive your photon sources, then you can imagine the photon sources being synchronized with the local oscillators. Now, the problem here is that, in this particular study, we did not consider the jitter that could be added by, let's say, a pump laser or by the photon emission process itself. That, of course, is still an issue.
Thank you, Dr. Gerritz. I think there is no more questions. I don't see any other question. Thank you so much for this great presentation. I appreciate it.
Thank you. And thanks for having me.
Thank you.
It's been a great workshop, really.
Thanks so much. I appreciate that. Okay, so our last talk today is by Dr. Aditya Sharma from NIST on precision enhanced displacement measurements using correlated photon pairs. Okay, so I would like to invite Dr. Sharma, please.
Hi. Can you see my
presentation
screen?
Yes.
Okay. And now you can see the laser pointer?
Yes.
Okay, great. So thanks for the introduction, and thanks for the invitation. Also, it's been a really fun workshop and great to hear what everyone is working on. My name is Aditya Sharma. I work at the Joint Quantum Institute in the University of Maryland, and I'm going to be talking actually about two different research directions, which are really quite different from each other. So in the first part of this talk, I'll be discussing my current work at JQI, where we are working towards building a practical quantum memory. And then in the second part of the talk, I'll be talking about a precision metrology experiment, which I'm really glad to be able to present at this workshop, because I think it's really sort of in line with the theme of the workshop of trying to find ways that quantum or quantum-inspired techniques could benefit classical scenarios. But the first part of the talk is actually quite related to the last few. So first of all, this work was done at JQI, and I just want to, at the outset, mention the people that I worked with on this. So Zachary Levine did the theory for this work, and Martin Ritter in the lab, and of course the project leader, Alan McDowell. So we've heard quite a bit in the last few talks, especially Neil's, about why we might want to build a quantum network. So we also heard about the need for quantum memory. In this first part of the talk, it's going to be quite tutorial in nature. I think there have been some questions from the audience about how some more fundamental details about how quantum memory would work. So I will try to make those aspects a little clearer in this first part of the talk. And then I'll talk about a specific technique for quantum memory that we try to implement in our experiment, and how we do. Okay, so as we've heard in all of these talks so far, we already have optical networks, and this is a good framework for our future quantum networks, but we still need various new technologies. So specifically, when we think about these optical networks, they are susceptible to loss, and that loss goes exponentially in distance. So typically over a 15-kilometer fiber link, you'll have something like 50% loss. Now, in a classical setting, that's no problem. I don't know why my pictures are all coming out funny, so I'm gonna exit this show for a moment. Okay, that's better. So yeah, the loss is exponential in distance, and in a classical network, there's no problem because you simply use repeaters. Repeater is simply a device that takes your signal after it has been attenuated by propagation. It measures the signal, amplifies it, and then relays it further along the network so that when the signal reaches its destination, it's still strong enough for the recipient to read it. And the no cloning theorem has been mentioned also, first by Prem Kumar earlier in the session, and in the other talks about quantum networks. So the no cloning theorem, again, just states that it's not possible to make a perfect copy of a quantum state unless you actually know what it was to begin with. And that's not very useful. It's important to be able to copy any quantum state. So this whole idea of a classical repeater just doesn't work, fundamentally doesn't work. And it's not like it's a very fundamental aspect of quantum mechanics that you can't do this. So we need a totally different device, a quantum repeater. And here is another, so it's a cool quantum trick for basically sending quantum information called teleportation. And rather than actually sending your quantum information directly on this lossy transmission channel, supposing that the two communicating parties, in addition to the message that they want to send, start off with a shared resource. So they share an entangled state. So with this resource, they can do something, which is that the sender, Alice, can make a joint measurement of the two particles that she holds. And what I mean by that is that the outcome of that measurement is going to be one of these 4 entangled states. So she does that, she gets one of those 4 results probabilistically. And then she takes the outcome of the measurement, which is encoded 1, 2, 3, or 4, and sends it via a classical channel to Bob. So now Bob's state has in the meantime been projected into a completely unknown state. But when he gets this message, he can do one of 4 transformations in order to recover the state that Alice initially held. So this is another way to transport quantum information over a long distance, assuming you have that entangled resource to begin with. So we can try to think about how the loss scales here. So if the two parties are separated by a distance d, and there's some efficiency to your quantum channel, then the transmission probability will scale exponentially with the distance. If you have instead this teleportation scheme, well, it involved 2 things. First of all, it involved the entangled resource, and it also involved sending this classical message. Sending the classical message is easy. There's no loss issue, as we talked about. But how do they come to share the entanglement? Well, there has to be a central bank that's distributing those states. And if you think about it, there's going to be loss in those channels as well. And since you need both particles of the pair to simultaneously make it to their destinations, you don't actually get any improvement here, because if one of the photons is lost and the other is not, it's as good as a complete failure. So in fact, teleportation by itself does not actually help you with this problem. But if we now think about making many of these teleportation links, so we have multiple nodes between the two parties, Alice and Bob, each of which distributes entanglement. And in addition to that, we have this technology, a quantum memory. Now we can think about what we can do. So each of these entanglement sources will make an attempt to distribute entanglement. Now, sometimes that attempt will succeed, as it did on the right-hand side in this case, but sometimes it'll fail. But that's okay if we have this quantum memory, because now the quantum memory establishes a link when the transmission was successful. And now that intermediate link has been successfully connected. We can now wait and try again on the other links until the other link is also made. And once all the links are successfully established, we can do a teleportation, special case of teleportation called entanglement swapping, where we are now going to teleport the far end of this entanglement chain to the other end by a joint measurement of the intermediate nodes. And again, after a classical transmission, you can establish an entangled link between Alice and Bob. So the point is now that they share entanglement over this long distance, they can use that to send an unknown quantum state. So we use the term quantum repeater because it serves the same purpose ultimately as a classical repeater, but again, the mechanism is totally different. So if we think about the requirements for this quantum memory that I talked about, well, clearly it has to be able to store the unknown quantum state. So it should be able to store any quantum state you put in. So it should also, with high fidelity, give you back out the state that you put in. Ideally, you would like it to have a large bandwidth so that you can store a lot of information per photon. And ideally, you would like it to give you back your photon on demand, so that as soon as you have all the links established, you pull out the photon and you can establish the large long distance link. So that last requirement is interesting because Tom talked about it a little bit in the last talk, but there's this need to synchronize the nodes anyway. So in a sense, it's not really that crucial that you have this on-demand functionality, although it is better if you do. Okay, so there are a number of ways that people try to do quantum memory. Many of those ways involve taking your photon and storing it in some sort of matter, either some kind of matter that'll absorb the excitation. I'm going to be talking about a specific technique that uses rare earth doped crystals. So what I mean by rare earth doped crystal is you have a crystal lattice, and ideally that lattice is a perfectly repeating structure, but you have instead these dopant ions, which are basically defects in that structure. So instead of a blue, you get a red, and so that ion is a defect in the structure. But if you look at it a different way, actually that crystal structure is a matrix for the ions, the dopant ions, and that kind of situation has some nice properties. So if we think about one of those red ions in that crystal, if it has some transition from a ground to excited state, and we cool this crystal to a low temperature to make sure that things are not vibrating too much, then we can make sure that the transition energy from ground to excited state has a relatively small line width on the order of kilohertz. We call that the homogeneous broadening. It's the uncertainty in the absorption line of a single emitter. There's also this idea of inhomogeneous broadening, which is how much variation is there across the ensemble in terms of the transition energy. And because the different ions in this structure are in different places, they experience a different sort of electrostatic environment, so that inhomogeneous broadening can be quite large. In comparison with the kilohertz homogeneous broadening, you can have gigahertz broadening here. And finally, the last good property of these materials is that when you take a rare earth atom and you ionize it, you take the triply ionized atom, it happens that those valence electrons are actually shielded by larger orbitals. They're inside the atom. So as a result of that, you actually get very long coherence times, and you can have a ground state lifetime on the order of minutes. So now I'll talk about the specific material that we are looking at. It's praseodymium doped yttrium orthosilicate. And this particular material has been investigated a lot as a way to implement quantum memory. So if we think about those various characteristics I talked about on the last slide, in this case, the inhomogeneous broadening is on the order of 5 gigahertz. And so that means that is the range of frequencies over which we can actually have absorption. The homogeneous broadening is 1 kilohertz, and the ground state lifetime is about 30 seconds. So what this means, what the first two things mean, is that if I send in a relatively broad bandwidth photon, I can have the ensemble absorb it because I have this broad blue absorption spectrum. And because of the 1 kilohertz homogeneous broadening, I can still preserve the coherence of the different frequencies contained within that photon. So I can really store the quantum information that was in the photon. So in this particular material, the energy level structure looks like this. We have these hyperfine energy levels, which are, so there are 3 ground state levels, 3 excited state levels, and they're connected by an optical transition, which is this color, orange. Okay, so I've told you something about the characteristics of this material. Now, there are different ways, even if you're going to work with this PRYSO material, there are different ways that you could try to use it for quantum memory. I'm going to be talking about a scheme called the Atomic Frequency Comb Protocol, or AFC protocol. And this is, in fact, it was designed specifically for this kind of material. So the way it works is that we prepare an atomic frequency comb in the absorption spectrum of the material. What I mean by that is, you see, we have a slightly more complicated level structure here, but we have a ground state and we have a second ground state. So G and aux are both ground states. And then we have an excited state. And I'll talk about this S state later. But the G state, you see, for different absorption frequencies, has a series of peaks where the material will absorb. And that means basically that the population of the G state has this structure. And the missing parts have to go somewhere else. So those are kept in this other ground state aux. So that's the exact opposite of the ground state. So now if we send a single photon into this absorption structure, what's going to happen is the atoms that can absorb, because they're in the G state, will absorb at their respective detunings, and they will go up to the excited state. And this results in a collective excitation of all of the atoms that could absorb the photon. So your single photon becomes this collective excitation of one atom in one of these frequency teeth having absorbed your photon. You'll notice that there's a phase factor here, and I just want to focus on the first one for now. That phase factor has to do with the detuning of the atom that happened to absorb the photon, what frequency it absorbed it at. And because this structure is periodic, those phase factors will be periodic as well for the different terms in this state. So there's a time evolution associated with them. And after time 2 pi over delta, the tooth spacing of this comb, you'll have all of those terms rephase. And what happens when those terms rephase is that the photon will be re-emitted as what's called an echo pulse. So that's the basic part of the protocol. The key thing to take away from this is that if we are able to pattern the absorption structure this way and send in the photon, it will be re-emitted at a very specific time, 2 pi over delta. It's a fixed time delay. There's more to the protocol though. So remember, this is the state that we were looking at. So if we did want to implement a on-demand memory, you actually can do it with this scheme. And the idea is that when you have your atoms in this collective excitation, you can take the ones that are excited and move them to another ground state that we call S. And when the atoms are in that S state, the evolution temporarily pauses as long as they're kept in that state. So now all you need to do if you want to restart the evolution is move them back from the S state to the E state, finish the evolution, and then get them at the end of the fixed time delay. So this is a way to implement on-demand memory if you did want to. Another nice thing about it though is that if you did use these laser pulses, you can now look at this second phase term. So this second phase term has to do with the spatial distribution of the excitation. And in fact, it turns out that there's a bit of an issue that if you wait for your echo pulse to come out, it can always be reabsorbed by the medium, and then you lose it. So if you instead do this sort of control pulse idea in which you hold the pulse and then have it come out later, you can actually use your control pulses for backward emission by reversing this spatial phase distribution. And the nice thing about that is you time reverse the initial absorption, and you can actually, in principle, get 100% re-emission of the photon. So in that way, this is quite a promising idea. In practice, I believe the highest efficiencies that have actually been reached are only about 50%. And in general, if you want to do better, you need a high finesse frequency comb. These teeth need to be very sharp, and you need a high optical depth, high absorption. Okay, so one obstacle to actually making, so, one of the nice things I said about this material, PRYSO, is that you have this very large inhomogeneous broadening, which allows you to make a broadband atomic frequency comb. But actually, if you look at the energy level structure of the atom, of the PR ions, you see that the splittings here are actually not so big. They're only about 5 megahertz. And if you recall, when you prepare the initial atomic frequency comb, you need to take some of the atoms and put them into another state. And now those atoms will absorb at some other frequency. And in particular, that frequency is only going to be, in this case, 10 megahertz away. So actually, it's not generally possible to make an atomic frequency comb with this material that's much bigger than about 5 megahertz. So you can see this was, I believe, the first experiment that was done using this protocol on demand. And they're not able really to make a very broad AFC because of this limitation. Okay, so how do we make an AFC in the first place? I've talked about what we do once we have it, but I haven't actually talked about how we make it. So the trick is to do what's called spectral hole burning. And the idea here is that I can actually optically pump the atoms here. So if I turn on a laser that addresses one of these transitions, then the atoms that are in the ground state that I'm addressing will go up to an excited state, and then they'll decay probabilistically. They may come back to the same ground state, but then the laser is still on, so they'll likely go up again. And eventually they will decay to one of the other ground states. And because of the long ground state lifetime, they'll stay there for a while. So what's going to happen is that you pump atoms out of one ground state, and then the absorption at that frequency actually goes down. So you can actually change the absorption spectrum by just turning on the laser. And here what I'm showing is that there are 9 transitions for the atoms, for each atom in this material. And in addition, if I think about turning on the laser at a certain frequency, there are 9 different inhomogeneously broadened classes of atoms that I could be talking to. So I could be talking to the smallest transition on this kind of atom, or I could be talking to the largest transition on this other atom. As a result, if I turn on just a single frequency, I actually see a whole lot of features in this spectrum. And if you look at this, you see that actually there's already some periodicity to the spectrum. So this is related to the fact that the spacings between these excited state levels are both quite similar. So as a result, you get some sort of periodicity already. And this is what we are going to try to exploit. So in order to make the AFCs in our experiment, we start off with an optical frequency comb. So it's a beam that has frequencies at sharply defined values that are equally spaced. It looks like that. And this is the setup. So we have 2 beams going into our crystal, which is in a cryostat, because remember, we need to keep it cool to make sure that we have the low homogeneous broadening that we need. So in the first beam, we prepared this optical frequency comb, which burns the spectrum that we're looking for, ideally, in the crystal. And in the second beam, so the first beam is about 120 megahertz bandwidth optical frequency comb. And we can vary the tooth spacing of that optical frequency comb from 0.1 all the way up to 20 megahertz. So yes, as I said, ideally that optical frequency comb will be imprinted on the absorption spectrum of a crystal. And with the second beam, we make two different measurements. So the first measurement will be to sweep the frequency across the bandwidth just so we can measure the absorption spectrum of the ensemble. And in the second measurement, we can send in a pulse and try to retrieve it. So here's an example of a measurement. Okay, so in the top line, we're looking at an optical frequency comb with 5.5 megahertz tooth spacing. The bottom row is 5 megahertz, so not that different. And the blue curves show the absorption spectra that result from driving the crystal with those fields. So you can see there's really quite a dramatic difference. In the top case, 5.5 megahertz, it's not even a well-defined AFC. And in the second case, we can see the periodic structure that we're looking for. And we can also, as I said, send in a pulse. And again, you can see that in the top case, because there's no, the structure does not appear the way that we want. We don't see an echo pulse at all. And in the second case, we can actually see the echo pulse coming out at, again, 0.2 microseconds, which is just the inverse of the tooth spacing, 5 megahertz. So in general, what we found is that the quality of these AFCs that we produce depends very much on the tooth spacing of the optical frequency comb that we use to burn them. So you can see that in this range, from about 4 to 5 megahertz tooth spacing, there's like a discontinuous range of good AFCs. So it's not constantly good. In these red curves, we see that there's a sudden drop actually in the quality of the AFCs. But there is a finite range of good values. So you can also see, if we plot the strength of the echo pulse, how these different tooth spacings perform. So this is a suggestion for, it's a way that we can overcome the limitation on bandwidth in the AFC by choosing a suitable tooth spacing for the comb. So to summarize this first part of the talk, I talked about why we need quantum memory for quantum repeaters. And the AFC protocol is a specific way that we can realize that. And it's especially well suited to these inhomogeneously broadened media, which are in turn well suited to broadband applications. And PRYSO in particular is one promising material for doing this. But because of the hyperfine structure, we actually don't get the full broadband capabilities that we would like. Nevertheless, we can overcome that by looking at details of the hyperfine structure. And if we look at the performance of these AFCs that we've already looked at, the main limitation is really that the storage efficiency is still very bad, even in the cases that we burn high quality AFCs. The performance is not very good, and this is because we again need a large finesse in order to get high efficiency. And of course, if we can improve the bandwidth even further, we have 5 gigahertz to work with. So so that brings me to the end of this first part of the talk. I think it'll be good if I take questions now.
I don't see any questions right now in the Q&A.
Okay.
I think maybe after, if there is, I will let you know.
Okay, sounds good. Okay, so in the second presentation, it looks like there's something. Yeah.
Are you calling on me because I raised my hand?
I am, yes.
Cool. Am I allowed to ask you a question?
You are.
Excellent. So this isn't really a question, it's more of a possible question that other people may be wondering but are too shy to raise. In your first section where you did a very nice job of explaining why quantum memory is important and how it will work in the context of a quantum repeater, I thought perhaps you'd like to say a little bit about, in that overall scheme, how would one know when the first photon came in and when the second photon came in?
Yeah, so let's just go back. So you're asking, how do we know that we had a success on the right side, but not on the left side?
Or how do you know when you did get a success on the second side? Yes.
Yeah, so this particular protocol is not, that's not a strength of this one. So there are other protocols, notably like the DLCZ protocol for quantum repeaters, where there's a herald photon emitted when you have a successful absorption. In this case, you don't get that. So the major strength of this protocol, I think, is ideally the 100% efficiency, right? So if you can really have a very high chance of absorption, then you can maybe overcome this fact that you are not getting a herald. And it's going to end up in your error rate, I suppose, that you don't know when you're successful.
Okay, so I'll just repeat. In at least one of the protocols, people have to know separately that there's a single photon coming in order for this to work. That's what is meant by heralding. Yes. Over.
Hello?
Is there any other questions for now?
No, I don't think so. Please.
Okay, so yeah, in this second presentation, I'll be talking about beam displacement measurements. So this work, I am still Aditya Sharma from the Joint Quantum Institute, but this work was actually done at University of Illinois. And again, I want to highlight the people that I worked with directly on this. So Courtney Kravchik and Paul Kwiat. And so in this very workshop, we've seen a little bit about how correlations can be, correlations and actually entanglement specifically can be an advantage in metrology. So here I'm going to talk about a situation where correlations give you an advantage, and we are going to use entanglement. As it turns out, you get an advantage even with classical correlations. And we're going to look at this in the context of beam displacement measurements. So beam displacement measurements have a number of useful applications. And one that's quite common is in atomic force microscopy, where you can reflect a beam off of the cantilever, look at the displacement of that beam on a detector, and from that infer the angle at which the cantilever deflected. So for that particular application, and for a number of others, it's adequate to use a really simple technique for this measurement, which is to just take a detector that has two segments, a right segment, left segment, and look at the normalized difference between those signals, and you get you can infer the displacement of the beam from that. Now, in this scheme, of course, each photon you detect improves your estimate of the displacement. So you have a couple of options if you're trying to get a better measurement of the displacement. First, of course, you can just increase the number of photons you use. And for a number of applications, that's the best thing to do. But in other cases, if you want to actually optimize how much information you're getting per photon, then you have to think about a couple of things. First of all, you have to think about, if you're measuring a very small displacement, you can try to get a very high precision measurement by using a tightly focused beam, a beam that's very small on your detector. On the other hand, if you're potentially looking at rather large displacements, that small beam is not going to give you very much information when it's deflected by a lot. So, or when it's displaced by a lot. So for a high dynamic range, you need to actually have rather large beam. So a question I want to ask in this talk is, can you actually still achieve a high precision measurement if you start off with a beam that has a large width? And at first, I mean, the answer seems to be obviously no, but you could try to do coincidence detection of pairs of photons that are correlated. And this particular scheme was proposed some years ago, where you produce a pair of photons and they go to a mirror that can move. And so they both experience the same displacement. And then they're separated and sent to two different split detectors. And now, instead of just calculating the normalized difference of the position of one photon, you actually calculate the average position of the two photons. So if one photon hits the positive side of the detector and the other one also hits the positive side, you count that as +2. If they both hit the negative side, you count that as -2. And if they hit opposite sides, they cancel each other out. So this is how you use that coincidence detection. Now, the effectiveness of this technique depends on the positional relationship of those two photons that you used, what I'm going to call the joint position intensity. So not surprisingly, I guess, that if the two photons have no correlation to each other whatsoever, then you don't see any improvement. And we can see this by looking at the JPI, the joint position intensity, for those two uncorrelated photons. Now, I'm going to show a lot of pictures like this throughout the talk. In general, what I'm showing here is not a beam like you would see in the lab. What I'm showing you here actually is, on the horizontal axis, I'm plotting the horizontal position of photon number 1. And on the vertical axis, I'm plotting the horizontal position of photon number 2. And the intensity shows you the probability of detecting photon 1 at x1 and photon 2 at x2. So if the photons are uncorrelated, then you'll get this sort of isotropic distribution. And if they're both displaced by the same amount, then that JPI intensity plot will be displaced along the 45-degree direction. And because the width of the circle is the same thing as the width of the circle in any direction, any cross-section, the width of the JPI is also the width of one photon of the pair. So there's no improvement here. Now, if you had correlated photons, you could potentially do better, because now I can have this sort of squeezed distribution where the distribution is actually very thin along the direction that matters. So we're displacing along 45 degrees, and so we squeeze it along that direction. But if we look at the width of one of these photons, that's the marginal distribution, its projection onto x1, for example, and that's just as big as it was in the uncorrelated case. So in principle, it seems that we should be able to do better using correlated photons. So now I want to quantify that statement, doing better. But first, I'll have to define the quantities. So first of all, I've already mentioned the idea of an estimator. An estimator is simply something that you calculate. It's a formula for calculating and estimating the actual displacement that has occurred in your system based on whatever data you actually have. Okay, and I of D, which is often called the Fisher information, is the amount of information that you could, in principle, extract from the data that you have about the displacement that has occurred. So generally that I of D quantity will depend, it will involve some sort of calculation that's a sum over all the possible measurement outcomes that you could have had in the experiment. So if you imagine the case of infinite resolution detectors, then, you know, if I could know exactly the positions x1 and x2 where the photons landed, then I would have to integrate over x1 and x2. And, you know, the Fisher information formula involves the probability of that event at x1 and x2, and also the derivative of that probability with respect to the displacement. And in split detection, you have actually the opposite case of infinite resolution, if you think about it, because it's the minimal resolution you could have. You just have two possible outcomes. So instead of that integral, you have a sum over the two possible outcomes, and that's 4 outcomes actually for your 2 photons. The significance of this quantity, I of D, is that from a practical point of view, if I take its inverse, that's a lower bound on the variance for the estimator, that for any estimator that I could come up with for D. There are some caveats to that statement, but that's a pretty good way to understand it. So now, having defined these things, we can, you know, take another look at split detection. So first of all, split detection in general. It turns out it's actually really, you know, although it's very low resolution, you just have 2 possible outcomes for your measurement, it turns out it performs really well as long as you have a small displacement. So again, the pictures are kind of not showing up, so let me reset this. Okay, so first I'm going to define some lengths here. So there's the narrow width of this correlated JPI, which I'll define as epsilon, and the broad width, which I'll define as sigma. And so in this table, we're looking at, in the top row, uncorrelated photons with this broad width, sigma. Second row, uncorrelated photons with this narrow width, epsilon. And in the third row, the correlated pairs. And in the third column here, we're looking at the inverse Fisher information, which is also the bound on the variance of the measurement in the case of infinite resolution. And in the fourth row, we're looking at that inverse Fisher information in the lowest resolution case of split detection. So now there's quite a bit of information here. So actually the things to take away, I think, are that, first of all, correlated pairs do just as well as, you know, this really tightly focused uncorrelated pairs if you have perfect resolution. And the way to see this basically is that if you're moving along this diagonal axis and you have perfect resolution, it really doesn't matter whether the distribution is long or it's actually circular. And we also see that actually split detection is almost as good as perfect resolution if you're using uncorrelated pairs. So for typical applications, when people use split detection, it makes sense because you are actually doing very well anyway. But actually correlated pairs do quite a bit less well. They take a bigger hit when you go from perfect resolution to split detection, but nevertheless, they do much better than their beam width would suggest. Okay, so in this work, we use spontaneous parametric down conversion to produce the correlated pairs that we will work with. So in this process, we have nonlinear crystal. We send in a pump photon, and with a very small probability, you get this photon annihilates, and you get a pair of down conversion photons at half the energy. And this process actually very naturally produces position entangled photons, as long as you do it correctly. And the way to see that is that when you send in this beam, the beam has a finite transverse extent, and the width of that beam determines the marginal distribution here, how, where in space the first photon could be found. In our case, this value sigma is about 500 microns. And because both photons have to be produced in the same place, you also get this narrow distribution along the other 45-degree axis. In this case, because of the crystal thickness we used, we get about 24 microns. So this image was made by doing a scan of the JPI using slits. So any one pixel in this picture is 5 microns wide. Now, one thing you might notice is that actually this JPI is oriented the wrong way. The photons are correlated in position, not anti-correlated, based on these arguments that I've made. So that's not going to work for our split detector, which you may remember should actually be oriented in the minus 45-degree axis. So in order to make that happen, we take our 2 photons, we split them up, and we just apply one extra reflection, 1 photon to flip the distribution. And then we image those 2 photons onto our detection system. We have, as in the original proposal, a mirror that can be moved. And at the detection system, we can scan slits to measure the JPI, which is how we got that first image. Or we can actually move that mirror by a pre-calibrated amount and actually do the split detection measurement that I described earlier. So here's an example of an actual measurement. So here, as we vary in the horizontal axis of both plots, as we vary the displacement of that mirror, we can actually look at the mean of that 2-photon displacement estimator. And as you expected, it tracks with the displacement. And in this particular data, each estimate that we take involves 850 measurements. So we can take those 850 photons, repeat that 200 times, and calculate the mean of that estimator as we do on the left side, or the variance of that estimator as we do on the right. And in order to get these blue solid curves with error bars, we just do a Monte Carlo simulation of the same experiment. So we see that indeed we actually do quite a lot better for small displacements than we would if we use the same size uncorrelated beam, looking at the variance of these measurements at small displacements. Now, you might notice this detail that the estimator mean does roughly look like a line of slope 1, but there's something going on for very small displacements. And this is due to the fact that the mirrors that we use to implement our split detector are not perfect. So the edges, they're actually not that reflective. And that the width of those edges is about 15 microns. It's actually a pretty, they're not good in kind of an unusual way. It seems to be that they're actually wave vector dependent at the edges. So now, having done this, like we've seen that, I showed on that slide with the table that you can do a whole lot better if you have more pixels in your detector, right? It turns out like we didn't have multi-pixel detectors, but what you can do is just simulate what you would get, right? So here's again a picture of the JPI that we measured, but you might notice it's much bigger and it has lower resolution because we used larger slits. So what we can do is we can take many of these slit scans and take them again and again for different displacements and actually simulate what would happen if we had a multi-pixel detector. So the multi-pixel estimator is a little bit more complicated, but it can still be found based on this data. So you can compare what you get with the simulation using our data versus what you should get in theory. And you see that it lines up quite well. Generally, the idea is that the variance of these measurements, if we scale it by the maximum variance you could get in the perfect resolution limit, goes inversely with the number of pixels that you use. And this is, if you think about it intuitively, it's basically that if you have a certain density of pixels and then you double that, you're going to get double the information from that segment of the JPI, as long as your pixels are not getting smaller than the width of the JPI. But there's this little detail that, for 3 pixels, you actually do worse than for 2 pixels. And we thought that, maybe we can improve on that. So first of all, why is 3 worse than 2? Well, you realize, it's just a detail of the geometry of the JPI, right? So if I have a 3-pixel detector, I'm really not making very good use of this Gaussian distribution. There's no intensity at those intersections of the pixels. So if we think about this shape, this Gaussian shape, this came from the shape of the pump mode. So what we could do is just use a different pump mode. So if we do a simple mode conversion by just applying a pi phase shift to that pump beam, we can get something that's approximately Hermite-Gauss 1-0 beam. And then we get a Hermite-Gauss 1-0 profile in the JPI as well. So this kind of beam seems to be much better suited to this measurement. So if we repeat this kind of a measurement, we see that, in fact, for 2 segment detectors, the Hermite-Gauss 1-0 beam does very badly. And this is to be expected because it has the same problem as the Gaussian for 3 pixels. There's no intensity at the relevant place. But for 2 pixels, you can actually do much better. And this is just, this is an example for 3 pixels because you have this kind of very bad situation where you're actually doing worse. But in principle, you could repeat this for larger M and use higher order Hermite-Gauss modes. And you see that we have similar scaling in general for the higher pixel numbers, regardless of the mode. Okay, so to summarize, the techniques we've looked at here involve correlated photons, and that lets us exceed precision limits that are typically imposed by the beam width of the photons that are being used. And in the perfect resolution limit, it actually doesn't matter at all what the beam width is. If you have lower resolution like split detection where you have only 2 pixels, then the beam width does enter into the precision of your measurement, but it's not as strongly as it does otherwise. And finally, we saw that you can actually further improve the precision by tailoring the JPI. So the main practical takeaway, I think, from this is that we've shown that we can keep the incident intensity constant, but still improve the measurement precision. I think this is potentially useful for a lot of applications where you don't want to use high intensity to make your measurement, but you do want a precise measurement. So, I think the main question now is just, what sort of techniques can we use this for? And I'd be happy to hear any suggestions that people have for that. So thanks for your attention.
Thank you very much, Dr. Sharma. That was really great presentations. And is there any question? Please. I actually have some questions myself. I'm interested also to know more about the hardware that you use. For example, when you're directing the beam, are you using kind of a fast steering mirror probably?
Let me go back to this slide. So you're asking about this mirror?
One of those, yes, or the previous ones that are tilt and tip probably, or is this a linear stage or is it a rotary?
Yeah, this is a linear stage. So it's actually a displacement that's happening. And it's a pico motor is what it's called.
How about the rotary one? Is that a fast steering mirror by any chance? The ones that you showed initially?
Oh, well, so that was just a schematic. So I know that that's how it is. Hang on one second. So I think you're talking about this picture.
Something like that, yes.
Yeah, I mean, so here it's actually not this is not actually, this is what I'm trying to show here is a case of atomic force microscopy. So actually, what you would have is a cantilever tip that's actually moved by the sample that you're trying to characterize.
Yes.
And then that movement of the tip causes the mirror to deflect, and you detect that, and then you can infer the surface characterization of the that you're trying to do. So that's just a schematic. It's not an actual picture. But
sure. And then you also, in terms of the detection or detectors that you mentioned, so you already, I think, mentioned the type of detectors, but these are different from the single photon counter modules.
Yeah, so these are avalanche photodiodes.
But these are avalanche photodiodes, yes.
Right.
And
so, they only allow, so we don't get any spatial resolution. These typically also only have about 60% efficiency in our case. So, of course, if you want to do this practically, I mean, you would want to have very high efficiency detectors as well. But yeah.
Okay. So just to again following up on that. So I'm not the expert in this area, but is it some sort of like Excelitas detectors or different types?
This was a Perkin-Elmer detector.
Okay, so it's not Excelitas, those ones. No?
I don't think it was.
No, single photon. That's the one that we. So if we use those type of detectors, we cannot use this technique, I guess. No, these are different, I guess.
I guess you could. I don't see why not. I mean, here the main thing is that you need to be able to detect the single photons.
However you detect it is fine.
Right.
But then how do we get the screen that you're showing? Sorry, I missed that explanation.
Okay, so yeah, I think I perhaps didn't explain it clearly. So this is so first of all, this picture that I'm showing is the case of scanning slits, right? So there's a slit in front of each beam, and I can have that on a translation stage, and I first move one, and then I scan the other, and I make a two-dimensional measurement to get this JPI picture. Now, the second measurement, what I do is I take those slits out, and I instead put this what's called D-shaped mirror. It's basically a mirror with a straight edge, and so that straight edge cuts the beam halfway, and so half of the beam ideally goes straight to this detector, and half of the beam goes to this one. So now I can construct my 4 quadrants, right? So the plus, plus, minus, 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 plus, plus, minus.
Interesting. And then when you're detecting, these are all coincidences, yes? The white, they're all coincidences. They're all, so if you detect one on the top side, you also detect on the bottom detectors.
That's right.
At the same time, okay. And are you using like 10 nanosecond roughly for these, for the coincidence counting?
You mean like the window?
Yes, the window.
I don't remember what window we use, but I guess, it just depends on the, I mean, it's limited by the jitter of the detector.
I see. Okay. Perfect, thank you. I think there's one more question here. If yes. Can quad be better than a split detector? By Russell.
I think I can open the thing. So, so by that, do you mean like a 4-pixel detector? So yeah, I guess that's what I was trying to show on this slide. So here on the horizontal axis, I'm plotting the number of detector segments. So split detection, where I just have, my D-shaped mirror, which cuts the beam into 2 parts, that falls over here. And what I'm plotting on the vertical axis is the variance of the measurement. So if I get a small number, that's better. That means I have a more precise measurement of the displacement. So in the case of 2 pixels, you do so well. And if you go all the way up to 90, it's, it's much better. So I guess I don't have a data point for 4 specifically, but you can see for 5, it actually happens to come right back to about the same place. And this is because of this, well, I haven't plotted 4 on this picture. So the details do matter here. So as you can see, there's a big outlier at 3. I would expect that 4 would be pretty good. And the reason for that, where was I? Yeah, so 3 is an unusual case because you really put the pixel intersections, the segment intersections in totally the wrong place. If you have 2, then it's very good for Gaussian because you exactly intersect the most intense part of the beam. And if you have 4, again, because it's an even number, you're going to have 1 intersection at the middle, so it should be pretty good. So I hope that answers the question.
So sorry, you already explained again one more time. Why do you need the single slits in front of the detectors? I forgot about that.
Yeah, sure. So so the slits here, if you look at this, the slits are used in order to make this picture of the JPI. So what I do is, if I want to measure the coincidence probability, can you see my mouse?
Yes.
Okay, so if I want to measure the coincidence probability for this value of x1
yes,
on the horizontal axis,
okay,
and this value of x2, then I just put the slits x1 and x2 at that position, and I count for a little bit, and I see how many photons are there, and then that's what I've plotted here, basically. So you see the most coincidence events along that that minus 45-degree line.
Okay, so this is just a slit in any kind of typical kind of entanglement experiment, or is it for plotting the diagonal one?
So the slit, like, I'm not looking at a diffraction pattern or anything like that. If
I know,
yeah.
yeah.
Yeah, I'm just looking at the intensity, transmitted intensity.
Okay, I see. Yes. Okay, thank you. Is there any other question? Okay, thank you so much, Dr. Sharma. That was really great. Great presentation and very informative. And
thank you.
Okay, so now is just a general discussion. If anybody would like to talk, or I mean, all the attendees, if you would like to talk about anything or discuss anything, please feel free. I can allow, if you would like to discuss anything, let me know if you like to talk. I don't know how I can make the attendees, all of them at the same time, to be able to, if you like to unmute, I'm not sure, but if you let me know, I'll unmute if you would like to talk about it. So I just would like also to make one more final announcement about I'm going to share the screen one more time. The announcement about the special issue of the ASME Journal of Autonomous Vehicles and Systems. So here we are trying to promote any kind of application of quantum engineering that can be used in terms of application in autonomous vehicle, ground vehicle, space, or underwater vehicles in general. It can be algorithms, can be detections, sensors, communications, and so on. Anything that can be used in this area. This is one of our This is really one of its kind that in terms of bringing quantum in real mechanical engineering domain, or let's say aerospace engineering, which we would like to integrate quantum technologies in terms of software or hardware into mechanical systems. All right, so I also will post the link for submission in the chat. So please consider submitting your work to this journal. And so stop the share.